nature, that is, a circular motion, and ascend or descend when they have, in addition to this, a rectilinear motion by which they endeavor to get into their own place. But his disciples soon began to question the Aristotelian dogmas and to seek for sounder views by the use of their own reason. The great argument against this system, says Meislin, is that heavy bodies are said to move to the center of the universe and light bodies from the center. But I would ask, where do we get this experience of heavy and light bodies? And how is our knowledge on these subjects extended so far that we can reason with certainty concerning the center of the whole universe? Is not the only residence and home of all the things which are heavy and light to us, the earth and the air which surrounds it? And what is the earth and the ambient air with respect to the immensity of the universe? It is a point, a punctual, or something, if there be anything, still less. As our light and heavy bodies tend to 288, the center of our earth, it is credible that the sun, the moon, and the other lights have a similar affection, by which they remain round as we see them. But none of these centers is necessarily the center of the universe. The most obvious and important physical difficulty attendant upon the supposition of the motion of the earth was thus stated. If the earth move, how is it that a stone, dropped from the top of a high tower, falls exactly at the foot of the tower? Since the tower being carried from west to east by the diurnal revolution of the earth, the stone must be left behind to the west of the place from which it was let fall. The proper answer to this was that the motion which the falling body received from its tendency downwards was compounded with the motion which, before it fell, it had in virtue of the earth's rotation. But this answer could not be clearly made or apprehended till Galileo and his pupils had established the laws of such compositions of motion arising from different forces. Rothman, Kepler, and other defenders of the Copernican system gave their reply somewhat at a venture when they asserted that the motion of the earth was communicated to bodies at its surface. Still, the facts which indicate and establish this truth are obvious when the subject is steadily considered. And the Copernicans soon found that they had the superiority of argument on this point as well as others. The attacks upon the Copernican system by Duret, Morin, Riccioli, and the defense of it by Galileo, Landsberg, Gassendi, left on all candid reasoners a clear impression in favor of the system. Morin attempted to stop the motion of the earth, which he called breaking its wings. His Ali Terifracti was published in 1643 and answered by Gassendi. And Riccioli, as late as 1653, in his Almagestum Novum, enumerated 57 Copernican arguments and pretended to refute them all. But such reasonings now made no converts. And by this time the mechanical objections to the motion of the earth were generally seen to be baseless, as we shall relate when we come to speak of the progress of mechanics as a distinct science. In the meantime, the beauty and simplicity of the heliocentric theory were perpetually winning the admiration even of those who, from one cause or other, refused their assent to it. Thus Riccioli, the last of its considerable opponents, allows its superiority in these respects, and acknowledges, in 1653, that the Copernican belief appears rather to increase than diminish under the condemnation of the decrees of the cardinals. He applies to it the lines of Horace. 289, per damna percides, ob ipso sumit opes animum fero, untamed its pride, unchecked its course, from foes and wounds it gathers force. We have spoken of the influence of the motion of the earth on the motions of bodies at its surface. But the notion of a physical connection among the parts of the universe was taken up by Kepler in another point of view, which would probably have been considered as highly fantastical if the result had not been that it led to by far the most magnificent and most certain train of truths which the whole expanse of human knowledge can show. I speak of the persuasion of the existence of numerical and geometrical laws connecting the distances, times, and forces of the bodies, which revolve about the central sun. That steady and intense conviction of this governing principle, which made its development and verification the leading employment of Kepler's most active and busy life, cannot be considered otherwise than as an example of profound sagacity. That it was connected, though dimly and obscurely, with the notion of a central agency or influence of some sort, emanating from the sun, cannot be doubted. Kepler, in his first essay of this kind, the Mysterium Cosmographicum, says, The motion of the Earth, which Copernicus had proved by mathematical reasons, I wanted to prove by physical, or, if you prefer it, metaphysical. In the 20th chapter of that work, he endeavors to make out some relation between the distances of the planets from the Sun and their velocities. The inveterate yet vague notions of forces which preside in this attempt may be judged of by such passages as the following. We must suppose one of two things: either that the moving spirits, in proportion as they are more removed from the Sun, are more feeble, or that there is one moving spirit in the center of all the orbits, namely, in the Sun, which urges each body the more vehemently in proportion as it is nearer, but in more distant spaces, languishes in consequence of the remoteness and attenuation of its virtue. We must not forget, in reading such passages, that they were written under a belief that force was requisite to keep up, as well as to change the motion of each planet, and that a body moving in a circle would stop when the force of the central point ceased, instead of moving off in a tangent to the circle, as we now know it would do. The force which Kepler supposes is a tangential force in the direction of the body's motion and nearly perpendicular to the radius. The 290 force which modern philosophy has established is in the direction of the radius and nearly perpendicular to the body's path. Kepler was right no further than in his suspicion of a connection between the cause of motion and the distance from the center. Not only was his knowledge imperfect in all particulars, but his most general conception of the mode of action of a cause of motion was erroneous. With these general convictions and these physical notions in his mind, Kepler endeavored to detect numerical and geometrical relations among the parts of the solar system. After extraordinary labor, perseverance, and ingenuity, he was eminently successful in discovering such relations, but the glory and merit of interpreting them according to their physical meaning was reserved for his greater successor, Newton. Chapter 4. Inductive Epoch of Kepler. Sect, one intellectual character of Kepler. Several persons, especially in recent times, who have taken a view of the discoveries of Kepler, appear to have been surprised and somewhat discontented that conjectures, apparently so fanciful and arbitrary as his, should have led to important discoveries. They seem to have been alarmed at the moral that their readers might draw from the tale of a quest of knowledge, in which the hero, though fantastical and self-willed and violating in his conduct, as they conceived, all right rule and sound philosophy, is rewarded with the most signal triumphs. Perhaps one or two reflections may in some measure reconcile us to this result. 291. Note 30/5. Laplace praeses de L. Hist. Dast. P. 94. Il est affligent pour l'esprit humain de voir si grand homme, même dans ses derniers ouvrages, si complaire avec délices dans ses chimériques spéculations, et les regarder comme elle aime et la vie de l'astronomie. Hist. Of Ast. Luk. P. 53. This success may well inspire with dismay those who are accustomed to consider experiment and rigorous induction as the only means to interrogate nature with success. Life of Kepler, Luk. P. 14, Bad Philosophy. P. 15, Kepler's miraculous good fortune in seizing truths across the wildest and most absurd theories. P. 54, The danger of attempting to follow his method in the pursuit of truth. In the first place, we may observe that the leading thought which suggested and animated all Kepler's attempts was true, and we may add, sagacious and philosophical. Namely, that there must be some numerical or geometrical relations among the times, distances, and velocities of the revolving bodies of the solar system. This settled and constant conviction of an important truth regulated all the conjectures, apparently so capricious and fanciful, which he made and examined, respecting particular relations in the system. In the next place, we may venture to say that advances in knowledge are not commonly made without the previous exercise of some boldness and license in guessing. The discovery of new truths requires, undoubtedly, minds careful and scrupulous in examining what is suggested, but it requires, no less, such as are quick and fertile in suggesting. What is invention, except the talent of rapidly calling before us many possibilities and selecting the appropriate one? It is true that when we have rejected all the inadmissible suppositions, they are quickly forgotten by most persons, and few think it necessary to dwell on these discarded hypotheses, and on the process by which they were condemned, as Kepler has done. But all who discover truths must have reasoned upon many errors to obtain each truth. Every accepted doctrine must have been one selected out of many candidates. In making many conjectures, which on trial proved erroneous, Kepler was no more fanciful or unphilosophical than other discoverers have been. Discovery is not a cautious or rigorous process in the sense of abstaining from such suppositions. But there are great differences in different cases, in the facility with which guesses are proved to be errors, and in the degree of attention with which the error and the proof are afterwards dwelt on. Kepler certainly was remarkable for the labor which he gave to such self-refutations, and for the candor and copiousness with which he narrated them. His works are in this way extremely curious and amusing, and are a very instructive exhibition of the mental process of discovery. But in this respect, I venture to believe they exhibit to us the usual process, somewhat caricatured, of inventive minds. They rather exemplify the rule of genius than, as has generally been hitherto taught, the exception. We may add that if many of Kepler's guesses now appear fanciful and absurd, because time and observation have refuted them, others, which were at the time equally gratuitous, have been confirmed by succeeding discoveries in a manner which makes them appear marvelously sagacious. As, for instance, his assertion of the rotation of 292, the sun on his axis, before the invention of the telescope, and his opinion that the obliquity of the ecliptic was decreasing, but would, after a long-continued diminution, stop, and then increase again. Nothing can be more just, as well as more poetically happy, than Kepler's picture of the philosopher's pursuit of scientific truth, conveyed by means of an allusion to Virgil's shepherd and shepherdess. Malo me Galatea pedi, lasciva puella et fugit ad salix et si cupit anti vidri. Coy yet inviting, Galatea loves to sport in sight, then plunge into the groves. The challenge given, she darts along the green, will not be caught, yet would not run unseen. We may notice as another peculiarity of Kepler's reasonings, the length and laboriousness of the processes by which he discovered the errors of his first guesses. One of the most important talents requisite for a discoverer is the ingenuity and skill which devises means for rapidly testing false suppositions as they offer themselves. This talent Kepler did not possess. He was not even a good arithmetical calculator, often making mistakes, some of which he detected and laments, while others escaped him to the last. But his defects in this respect were compensated by his courage and perseverance in undertaking and executing such tasks. And, what was still more admirable, he never allowed the labor he had spent upon any conjecture to produce any reluctance in abandoning the hypothesis, as soon as he had evidence of its inaccuracy. The only way in which he rewarded himself for his trouble was by describing to the world, in his lively manner, his schemes, exertions, and feelings. The mystical parts of Kepler's opinions, as his belief in astrology, his persuasion that the earth was an animal, and many of the loose moral and spiritual as well as sensible analyses by which he represented to himself the powers which he supposed to prevail in the universe, do not appear to have interfered with his discovery, but rather to have stimulated his invention and animated his exertions. Indeed, where there are clear scientific ideas on one subject in the mind, it does not appear that mysticism on others is at all unfavorable to the successful prosecution of research. I conceive, then, that we may consider Kepler's character as containing the general features of the character of a scientific discoverer. 293, though some of the features are exaggerated, and some too feebly marked. His spirit of invention was undoubtedly very fertile and ready, and this and his perseverance served to remedy his deficiency in mathematical artifice and method. But the peculiar physiognomy is given to his intellectual aspect by his dwelling in a most prominent manner on those erroneous trains of thought which other persons conceal from the world, and often themselves forget, because they find means of stopping them at the outset. In the beginning of his book, Argumenta Capitum, he says, if Christopher Columbus, if Magellan, if the Portuguese, when they narrate their wanderings, are not only excused, but if we do not wish these passages omitted, and should lose much pleasure if they were, let no one blame me for doing the same. Kepler's talents were a kindly and fertile soil, which he cultivated with abundant toil and vigor, but with great scantiness of agricultural skill and implements. Weeds and the grain throve and flourished side by side, almost undistinguished, and he gave a peculiar appearance to his harvest by gathering and preserving the one class of plants with as much care and diligence as the other. Sect 2. Kepler's discovery of his third law. I shall now give some account of Kepler's speculations and discoveries. The first discovery which he attempted, the relation among the successive distances of the planets from the Sun, was a failure, his doctrine being without any solid foundation, although propounded by him with great triumph in a work which he called Mysterium Cosmographicum, and which was published in 1596. The account which he gives of the train of his thoughts on this subject, namely, the various suppositions assumed, examined, and rejected, is curious and instructive, for the reasons just stated. But we shall not dwell upon these essays, since they led only to an opinion now entirely abandoned. The doctrine which professed to give the true relation of the orbits of the different planets was thus delivered. The orbit of the Earth is a circle. Round the sphere to which this circle belongs, describe a dodecahedron. The sphere including this will give the orbit of Mars. Round Mars, describe a tetrahedron. The circle including this will be the orbit of Jupiter. Describe a cube round Jupiter's orbit. The circle including this will be the orbit of Saturn. Now inscribe in the Earth's orbit an icosahedron. The circle inscribed in it will be the orbit of Venus. 294. Inscribe an octahedron in the orbit of Venus. The circle inscribed in it will be Mercury's orbit. This is the reason of the number of the planets. The 5 kinds of polyhedral bodies here mentioned are the only regular solids. But though this part of the Mysterium Cosmographicum was a failure, the same researches continued to occupy Kepler's mind, and 22 years later led him to one of the important rules known to us as Kepler's laws, namely, to the rule connecting the mean distances of the planets from the Sun with the times of their revolutions. This rule is expressed in mathematical terms by saying that the squares of the periodic times are in the same proportion as the cubes of the distances, and was of great importance to Newton in leading him to the law of the Sun's attractive force. We may properly consider this discovery as the sequel of the train of thought already noticed. In the beginning of the Mysterium, Kepler had said, "In the year 1595, I brooded with the whole energy of my mind on the subject of the Copernican system. There were 3 things in particular of which I pertinaciously sought the causes why they are not other than they are: the number, the size, and the motion of the orbits." We have seen the nature of his attempt to account for the 2 first of these points. He had also made some essays to connect the motions of the planets with their distances, but with his success in this respect, he was not himself completely satisfied. But in the 5th book of the Harmonis Mundi, published in 1619, he says, "What I prophesied 22 years ago as soon as I had discovered the 5 solids among the heavenly bodies, what I firmly believed before I had seen the harmonics of Ptolemy, what I promised my friends in the title of this book, on the most perfect harmony of the celestial motions, which I named before I was sure of my discovery, what 16 years ago I regarded as a thing to be sought, that for which I joined Tycho Brahe, for which I settled in Prague, for which I have devoted the best part of my life to astronomical contemplations. At length I have brought to light, and have recognized its truth beyond my most sanguine expectations." The rule thus referred to is stated in the 3rd chapter of this 5th book. "It is," he says, "a most certain and exact thing that the proportion which exists between the periodic times of any 2 planets is precisely the sesquiplicate of the proportion of their mean distances, that is, of the radii of the orbits. Thus, the period of the Earth is 1 year, that of Saturn 30 years. If anyone trisect the proportion, that 295 is, take the cube root of it, and double the proportion so found, that is, square it, he will find the exact proportion of the distances of the Earth and of Saturn from the Sun. For the cube root of 1 is 1, and the square of this is 1. And the cube root of 30 is greater than 3, and therefore the square of it is greater than 9. And Saturn, at his mean distance from the Sun, is at a little more than 9 times the mean distance of the Earth. When we now look back at the time and exertions which the establishment of this law cost Kepler, we are tempted to imagine that he was strangely blind in not seeing it sooner. His object, we might reason, was to discover a law connecting the distances and the periodic times. What law of connection could be more simple and obvious, we might say, than that one of these quantities should vary as some power of the other or as some root, or as some combination of the two, which in a more general view may still be called a power. And if the problem had been viewed in this way, the question must have occurred, to what power of the periodic times are the distances proportional? And the answer must have been, the trial being made, that they are proportional to the square of the cube root. This ex post facto obviousness of discoveries is a delusion to which we are liable with regard to many of the most important principles. In the case of Kepler, we may observe that the process of connecting two classes of quantities by comparing their powers is obvious only to those who are familiar with general algebraical views, and that in Kepler's time, algebra had not taken the place of geometry as the most usual vehicle of mathematical reasoning. It may be added also that Kepler always sought his formal laws by means of physical reasonings, and these, though vague or erroneous, determined the nature of the mathematical connection which he assumed. Thus, in the Mysterium, he had been led by his notions of moving virtue of the sun to this conjecture, among others that, in the planets, the increase of the periods will be double of the difference of the distances, which supposition he found to give him an approach to the actual proportion of the distances, but one not sufficiently close to satisfy him. The greater part of the fifth book of the Harmonics of the Universe consists in attempts to explain various relations among the distances, times, and eccentricities of the planets, by means of the ratios which belong to certain concords and discords. This portion of the work is so complex and laborious that probably few modern readers have had courage to go through it. D'Alembert acknowledged that his patience, 296, often failed him during the task, and subscribes to the judgment of Bailey. After this sublime effort, Kepler replunges himself in the relations of music to the motions, the distance, and the eccentricities of the planets. In all these harmonic ratios, there is not one true relation. In a crowd of ideas, there is not one truth. He becomes a man after being a spirit of light. Certainly, these speculations are of no value, but we may look on them with toleration when we recollect that Newton has sought for analogies between the spaces occupied by the prismatic colors and the notes of the gamut. The numerical relations of concords are so peculiar that we can easily suppose them to have other bearings than those which first offer themselves. It does not belong to my present purpose to speak at length of the speculations concerning the forces producing the celestial motions by which Kepler was led to this celebrated law, or of those which he deduced from it, and which are found in the Epitome Astronomiae Copernicani, published in 1622. In that work also, p. 554, he extended this law, though in a loose manner, to the satellites of Jupiter. These physical speculations were only a vague and distant prelude to Newton's discoveries, and the law, as a formal rule, was complete in itself. We must now attend to the history of the other two laws with which Kepler's name is associated. Sect 3. Kepler's discovery of his first and second laws, elliptical theory of the planets. The propositions designated as Kepler's first and second laws are these: that the orbits of the planets are elliptical, and that the areas described or swept by lines drawn from the sun to the planet are proportional to the times employed in the motion. The occasion of the discovery of these laws was the attempt to reconcile the theory of Mars to the theory of eccentrics and epicycles. The event of it was the complete overthrow of that theory, and the establishment, in its stead, of the elliptical theory of the planets. Astronomy was now ripe for such a change. As soon as Copernicus had taught men that the orbits of the planets were to be referred to the sun, it obviously became a question: what was the true form of these orbits, and the rule of motion of each planet in its own orbit? Copernicus represented the motions in longitude by means of 297 eccentrics and epicycles, as we have already said, and the motions in latitude by certain librations, or alternate elevations and depressions of epicycles. If a mathematician had obtained a collection of true positions of a planet, the form of the orbit and the motion of the star would have been determined with reference to the sun as well as to the earth. But this was not possible, for though the geocentric position, or the direction in which the planet was seen, could be observed, its distance from the earth was not known. Hence, when Kepler attempted to determine the orbit of a planet, he combined the observed geocentric places with successive modifications of the theory of epicycles, till at last he was led, by one step after another, to change the epicyclical into the elliptical theory. We may observe, moreover, that at every step he endeavored to support his new suppositions by what he called, in his fanciful phraseology, sending into the field a reserve of new physical reasonings on the route and dispersion of the veterans. That is, by connecting his astronomical hypotheses with new imaginations, when the old ones became untenable. We find, indeed, that this is the spirit in which the pursuit of knowledge is generally carried on with success. Those men arrive at truth who eagerly endeavor to connect remote points of their knowledge, not those who stop cautiously at each point till something compels them to go beyond it. Note 35/5. I will insert this passage as a specimen of Kepler's fanciful mode of narrating the defeats which he received in the war which he carried on with Mars. Dum in hunc modum de Martis modibus triumpho, aec ut plane divicto tabularum carceres, et equationum compedes necto, diversus nunciator locis, feudalum victoriam, ut bellem tota mole recrudescere. Nam domi quidem hostis ut captivis contemptus, rupit omnia equationum vincula, carceresque tabularum effrigit. Foris speculators profligerunt mis causarum physicarum arcesitas copias, irumc jugum excusserunt resumpta libertate. Jamque parum obfuit quia hostis fugitivus seas, cum rebellibus suis conjungerit mec in desperationem adigerit. Nisi raptum, nover rationum physicarum subsidia, fusis et palantibus veteribus. Submississum, et quasi captivus proripuset, omni diligentia, et octus vestigiaes ipsius nulla mora interposita in Hesasarum. Kepler joined Tycho Brahe at Prague in 1600, and found him and Longomontanus busily employed in correcting the theory of Mars. And he also then entered upon that train of researches, which he published in 1609 in his extraordinary work on the motions of Mars. In this work, as in others, he gives an account not only of his success, but of his failures, explaining at length the various suppositions which he had made, the notions by which he had been led to invent or to entertain them, the processes by which he had proved their 298 falsehood, and the alternations of hope and sorrow, of vexation and triumph, through which he had gone. It will not be necessary for us to cite many passages of these kinds, curious and amusing as they are. One of the most important truths contained in the motions of man is the discovery that the plane of the orbit of the planet should be considered with reference to the sun itself, instead of referring it to any of the other centers of motion which the eccentric hypothesis introduced. And that, when so considered, it had none of the librations which Ptolemy and Copernicus had attributed to it. The 14th chapter of the second part asserts, plana eccentricorum s letter 1f00 tau alpha lambda alpha nu tau alpha, that the planes are unlibrating, retaining always the same inclination to the ecliptic and the same line of nodes. With this step Kepler appears to have been justly delighted. Copernicus, he says, not knowing the value of what he possessed, his system, undertook to represent Ptolemy rather than nature, to which, however, he had approached more nearly than any other person. For being rejoiced that the quantity of the latitude of each planet was increased by the approach of the Earth to the planet, according to his theory, he did not venture to reject the rest of Ptolemy's increase of latitude, but in order to express it, devised librations of the planes of the eccentric, depending not upon its own eccentric, but most improbably, upon the orbit of the Earth, which has nothing to do with it. I always fought against this impertinent tying together of two orbits, even before I saw the observations of Tycho, and I therefore rejoice much that in this, as in others of my preconceived opinions, the observations were found to be on my side. Kepler established his point by a fair and laborious calculation of the results of observations of Mars made by himself and Tycho Brahe, and had a right to exult when the result of these calculations confirmed his views of the symmetry and simplicity of nature. We may judge of the difficulty of casting off the theory of eccentrics and epicycles by recollecting that Copernicus did not do it at all, and that Kepler only did it after repeated struggles, the history of which occupies 39 chapters of his book. At the end of them he says, "This prolix disputation was necessary in order to prepare the way to the natural form of the equations, of which I am now to treat. My first error was that the path of a planet is a perfect circle, an opinion which was a more mischievous thief of my time. 299, in proportion as it was supported by the authority of all philosophers, and apparently agreeable to metaphysics. But before he attempts to correct this erroneous part of his hypothesis, he sets about discovering the law according to which the different parts of the orbit are described in the case of the Earth, in which case the eccentricity is so small that the effect of the oval form is insensible. The result of this inquiry was the rule that the time of describing any arc of the orbit is proportional to the area intercepted between the curve and two lines drawn from the Sun to the extremities of the arc. It is to be observed that this rule, at first, though it had the recommendation of being selected after the unavoidable abandonment of many, which were suggested by the notions of those times, was far from being adopted upon any very rigid or cautious grounds. A rule had been proved at the apsides of the orbit, by calculation from observations, and had then been extended by conjecture to other parts of the orbit. And the rule of the areas was only an approximate and inaccurate mode of representing this rule, employed for the purpose of brevity and convenience, in consequence of the difficulty of applying, geometrically, that which Kepler now conceived to be the true rule, and which required him to find the sum of the lines drawn from the Sun to every point of the orbit. When he proceeded to apply this rule to Mars, in whose orbit the oval form is much more marked, additional difficulties came in his way. And here again the true supposition that the oval is of that special kind called ellipse was adopted at first only in order to simplify calculation, and the deviation from exactness in the result was attributed to the inaccuracy of those approximate processes. The supposition of the oval had already been forced upon Purbach in the case of Mercury, and upon Reinhold in the case of the Moon. The center of the epicycle was made to describe an egg-shaped figure in the former case, and a lenticular figure in the latter. It may serve to show the kind of labor by which Kepler was led to his result, if we here enumerate, as he does in his 47th chapter, 6 hypotheses, on which he calculated the longitude of Mars, in order to see which best agreed with observation. The simple eccentricity. 2. The bisection of the eccentricity and the duplication of the superior part of the equation. 300. 3. The bisection of the eccentricity and a stationary point of equations, after the manner of Ptolemy. 4. The vicarious hypothesis by a free section of the eccentricity made to agree as nearly as possible with the truth. 5. The physical hypothesis on the supposition of a perfect circle. 6. The physical hypothesis on the supposition of a perfect ellipse. By the physical hypothesis, he meant the doctrine that the time of a planet's describing any part of its orbit is proportional to the distance of the planet from the Sun, for which supposition, as we have said, he conceived that he had assigned physical reasons. The two last hypotheses came the nearest to the truth, and differed from it only by about 8 minutes, the one in excess and the other in defect. And, after being much perplexed by this remaining error, it at last occurred to him that he might take another ellipsis, exactly intermediate between the former one and the circle, and that this must give the path and the motion of the planet. Making this assumption, and taking the areas to represent the times, he now saw that both the longitude and the distances of Mars would agree with observation to the requisite degree of accuracy. The rectification of the former hypothesis, when thus stated, may, perhaps, appear obvious, and Kepler informs us that he had nearly been anticipated in this step. See 55. David Fabricius, to whom I had communicated my hypothesis of Cap. 45 was able, by his observations, to show that it erred in making the distances too short at mean longitudes, of which he informed me by letter while I was laboring, by repeated efforts, to discover the true hypothesis. So nearly did he get the start of me in detecting the truth. But this was less easy than it might seem. When Kepler's first hypothesis was enveloped in the complex construction requisite in order to apply it to each point of the orbit, it was far more difficult to see where the error lay, and Kepler hit upon it only by noticing the coincidences of certain numbers, which, as he says, raised him as if from sleep and gave him a new light. We may observe, also, that he was perplexed to reconcile this new view according to which the planet described an exact ellipse, with his former opinion, which represented the motion by means of libration in an epicycle. This, he says, was my greatest trouble, that though I considered and reflected till I was almost mad, I could not find why the planet to which, with so much probability, and with such an exact 301 accordance of the distances, libration in the diameter of the epicycle was attributed, should, according to the indication of the equations, go in an elliptical path. What an absurdity on my part! As if libration in the diameter might not be a way to the ellipse. Another scruple respecting this theory arose from the impossibility of solving, by any geometrical construction, the problem to which Kepler was thus led, namely, to divide the area of a semicircle in a given ratio by a line drawn from any point of the diameter. This is still termed Kepler's problem, and is, in fact, incapable of exact geometrical solution. As, however, the calculation can be performed, and indeed was performed by Kepler himself, with a sufficient degree of accuracy to show that the elliptical hypothesis is true, the insolubility of this problem is a mere mathematical difficulty in the deductive process, to which Kepler's induction gave rise. Of Kepler's physical reasonings we shall speak more at length on another occasion. His numerous and fanciful hypotheses had discharged their office, when they had suggested to him his many lines of laborious calculation, and encouraged him under the exertions and disappointments to which these led. The result of this work was the formal laws of the motion of Mars, established by a clear induction, since they represented, with sufficient accuracy, the best observations. And we may allow that Kepler was entitled to the praise which he claims in the motto on his first leaf. Ramus had said that if anyone would construct an astronomy without hypothesis, he would be ready to resign to him his professorship in the University of Paris. Kepler quotes this passage and adds, "It is well, Ramus, that you have run from this pledge, by quitting life and your professorship. If you held it still, I should with justice claim it." This was not saying too much, since he had entirely overturned the hypothesis of eccentrics and epicycles, and had obtained a theory which was a mere representation of the motions and distances as they were observed. 302. Chapter 5. Sequel to the Epoch of Kepler. Reception, verification, and extension of the elliptical theory. Sect 1. Application of the elliptical theory to the planets. The extension of Kepler's discoveries concerning the orbit of Mars to the other planets obviously offered itself as a strong probability, and was confirmed by trial. This was made in the first place upon the orbit of Mercury, which planet, in consequence of the largeness of its eccentricity, exhibits more clearly than the others the circumstances of the elliptical motion. These and various other supplementary portions of the views to which Kepler's discoveries had led appeared in the latter part of his Epitome Astronomiae Copernicanae, published in 1622. The real verification of the new doctrine concerning the orbits and motions of the heavenly bodies was, of course, to be found in the construction of tables of those motions, and in the continued comparison of such tables with observation. Kepler's discoveries had been founded, as we have seen, principally on Tycho's observations. Longomontanus, so called as being a native of Langberg in Denmark, published in 1621 in his Astronomia Danica, tables founded upon the theories as well as the observations of his countrymen. Kepler in 1627 published his tables of the planets, which he called Rudolphine tables, the result and application of his own theory. In 1633, Landsberg, a Belgian, published also Tabulae Perpetui, a work which was ushered into the world with considerable pomp and pretension, and in which the author cavils very keenly at Kepler and Brahe. We may judge of the impression made upon the astronomical world in general by these rival works, from the account which our countryman Jeremy Horrocks has given of their effect on him. He had been seduced by the magnificent promises of Landsberg, and the praises of his admirers, which are prefixed to the work, and was persuaded that the common opinion which preferred Tycho and Kepler to him was a prejudice. In 1636, however, he became acquainted with Crabtree, another young 303 astronomer who lived in the same part of Lancashire. By him, Horrocks was warned that Landsberg was not to be depended on, that his hypotheses were vicious, and his observations falsified or forced into agreement with his theories. He then read the works and adopted the opinions of Kepler, and after some hesitation which he felt at the thought of attacking the object of his former idolatry, he wrote a dissertation on the points of difference between them. It appears that, at one time, He intended to offer himself as the umpire who was to adjudge the prize of excellence among the three rival theories of Longomontanus, Kepler, and Landsberg. And, in allusion to the story of ancient mythology, his work was to have been called Paris Astronomicus. We easily see that he would have given the golden apple to the Keplerian goddess. Succeeding observations confirmed his judgment, and the Rudolphine tables, thus published 76 years after the Prutenic, which were founded on the doctrines of Copernicus, were for a long time those universally used. Sect 2. Application of the elliptical theory to the moon. The reduction of the moon's motions to rule was a harder task than the formation of planetary tables, if accuracy was required, for the moon's motion is affected by an incredible number of different and complex inequalities, which, till their law is detected, appear to defy all theory. Still, however, progress was made in this work. The most important advances were due to Tycho Brahe. In addition to the first and second inequalities of the moon, the equation of the center, known very early, and the evection, which Ptolemy had discovered, Tycho proved that there was another inequality, which he termed the variation, which depended on the moon's position with respect to the sun, and which at its maximum was 40 minutes and a half, about a quarter of the evection. He also perceived, though not very distinctly, the necessity of another correction of the moon's place depending on the sun's longitude, which has since been termed the annual equation. Note 45/5. We have seen, chapter Roman 3, that a Baalweffe in the 10th century had already noticed this inequality, but his discovery had been entirely forgotten long before the time of Tycho and has only recently been brought again into notice. These steps concern the longitude of the moon. Tycho also made important advances in the knowledge of the latitude. The inclination of the orbit had hitherto been assumed to be the same at all 304 times, and the motion of the node had been supposed uniform. He found that the inclination increased and diminished by 20 minutes according to the position of the line of nodes, and that the nodes, though they regress upon the whole, sometimes go forwards and sometimes go backwards. Tycho's discoveries concerning the moon are given in his Progymnasmata, which was published in 1603, 2 years after the author's death. He represents the moon's motion in longitude by means of certain combinations of epicycles and eccentrics. But after Kepler had shown that such devices are to be banished from the planetary system, it was impossible not to think of extending the elliptical theory to the moon. Horrocks succeeded in doing this, and in 1638 sent this essay to his friend Crabtree. It was published in 1673, with the numerical elements requisite for its application added by Flamsteed. Flamsteed had also, in 1671, compared this theory with observation, and found that it agreed far more nearly than the Philolaic tables of Bullialdus or the Carolinian tables of Street, Epilogis ad tabulas. Moreover, Horrocks, by making the center of the ellipse revolve in an epicycle, gave an explanation of the evection, as well as of the equation of the center. Note 46/5. Horrocks, as he himself spelt his name, gave a first sketch of his theory in letters to his friend Crabtree in 1638, in which the variation of the eccentricity is not alluded to. But in Crabtree's letter to Gascoigne in 1642, he gives Horrocks's rule concerning it, and Flamsteed in his epilogue to the tables, published by Wallis along with Horrocks's works in 1673, gave an explanation of the theory which made it amount very nearly to a revolution of the center of the ellipse in an epicycle. Halley afterwards made a slight alteration, but hardly, I think, enough to justify Newton's assertion. Princip. Lib. Roman 3. Prop 35 Schol. Hallia centrum ellipsios in epicyclo locavit. See Bailey's Flamsteed, p. 683. Modern astronomers, by calculating the effects of the perturbing forces of the solar system and comparing their calculations with observation, have added many new corrections or equations to those known at the time of Horrocks. And since the motions of the heavenly bodies were even then affected by these variations, as yet undetected, it is clear that the tables of that time must have shown some errors when compared with observation. These errors much perplexed astronomers, and naturally gave rise to the question whether the motions of the heavenly bodies really were exactly regular, or whether they were not affected by accidents as little reducible to rule as wind and weather. Kepler had held the opinion of the casualty of such errors, But Horrocks, far more philosophically, argues against this opinion, though he, 305, allows that he is much embarrassed by the deviations. His arguments show a singularly clear and strong apprehension of the features of the case and their real import. He says, "These errors of the tables are alternately in excess and defect. How could this constant compensation happen if they were casual? Moreover, the alternation from excess to defect is most rapid in the Moon, most slow in Jupiter and Saturn, in which planets the error continues sometimes for years. If the errors were casual, why should they not last as long in the Moon as in Saturn? But if we suppose the tables to be right in the mean motions, but wrong in the equations, these facts are just what must happen. Since Saturn's inequalities are of long period, while those of the Moon are numerous and rapidly changing. It would be impossible, at the present moment, to reason better on this subject. And the doctrine that all the apparent irregularities of the celestial motions are really regular was one of great consequence to establish at this period of the science. Sect 3 Causes of the further progress of astronomy. We are now arrived at the time when theory and observation sprang forwards with emulous energy. The physical theories of Kepler and the reasonings of other defenders of the Copernican theory led inevitably, after some vagueness and perplexity, to a sound science of mechanics, and this science in time gave a new face to astronomy. But in the meantime, while mechanical mathematicians were generalizing from the astronomy already established, astronomers were accumulating new facts, which pointed the way to new theories and new generalizations. Copernicus, while he had established the permanent length of the year, had confirmed the motion of the sun's apogee, and had shown that the eccentricity of the Earth's orbit and the obliquity of the ecliptic were gradually, though slowly, diminishing. Tycho had accumulated a store of excellent observations. These, as well as the laws of the motions of the Moon and planets already explained, were materials on which the mechanics of the universe was afterwards to employ its most matured powers. In the meantime, the telescope had opened other new subjects of notice and speculation, not only confirming the Copernican doctrine by the phases of Venus and the analogical examples of Jupiter and Saturn, which, with their satellites, 306, appeared like models of the solar system, but disclosing unexpected objects as the ring of Saturn and the spots of the sun. The art of observing made rapid advances, both by the use of the telescope and by the sounder notions of the construction of instruments which Tycho introduced. Copernicus had laughed at Rheticus when he was disturbed about single minutes, and declared that if he could be sure to 10 minutes of space, he should be as much delighted as Pythagoras was when he discovered the property of the right-angled triangle. But Kepler founded the revolution which he introduced on a quantity less than this. Since, he says, the divine goodness has given us in Tycho an observer so exact that this error of 8 minutes is impossible, we must be thankful to God for this, and turn it to account. And these 8 minutes, which we must not neglect, will, of themselves, enable us to reconstruct the whole of astronomy. In addition to other improvements, the art of numerical calculation made an inestimable advance by means of Napier's invention of logarithms, and the progress of other parts of pure mathematics was proportional to the calls which astronomy and physics made upon them. The exactness which observation had attained enabled astronomers both to verify and improve the existing theories and to study the yet unsystematized facts. The science was, therefore, forced along by a strong impulse on all sides, and its career assumed a new character. Up to this point, the history of European astronomy was only the sequel of the history of Greek astronomy. For the heliocentric system, as we have seen, had had a place among the guesses, at least, of the inventive and acute intellects of the Greek philosophers. But the discovery of Kepler's laws, accompanied, as from the first they were, with a conviction that the relations thus brought to light were the effects and exponents of physical causes, led rapidly and irresistibly to the mechanical science of the skies, and collaterally to the mechanical science of the other parts of nature, sound and light and heat, and magnetism and electricity and chemistry. The history of these sciences, thus treated, forms the sequel of the present work, and will be the subject of the succeeding volumes. And since, as I have said, our main object in this work is to deduce, from the history of science, the philosophy of scientific discovery, it may be regarded as fortunate for our purpose that the history, after this point, so far changes its aspect as to offer new materials for such speculations. The details of 307, a history of astronomy, such as the history of astronomy since Newton has been, though interesting to the special lovers of that science, would be too technical, and the features of the narrative too monotonous and unimpressive to interest the general reader or to suggest a comprehensive philosophy of science. But when we pass from the ideas of space and time to the ideas of force and matter, of mediums by which action and sensation are produced, and of the intimate constitution of material bodies, we have new fields of inquiry open to us. And when we find that in these fields, as well as in astronomy, there are large and striking trains of unquestioned discovery to be narrated, we may gird ourselves afresh to the task of writing, and I hope, of reading, the remaining part of the history of the inductive sciences, in the trust that it will in some measure help us to answer the important questions: what is truth? And how is it to be discovered? 309, Book 6. The Mechanical Sciences. History of Mechanics, including Fluid Mechanics. Capro Alpha Tau Omicron Sigma, Beta Alpha Tau Epsilon. Sigma Phi letter 1 FF7, Nu Mu letter 1 F72, Nu letter 1 F10. Nu Tau Omicron Lambda letter 1 F74, Delta Iota letter 1 F78, Sigma letter 1 F14 Chi Epsilon Iota, Tau Epsilon Lambda Omicron Sigma, Delta letter 1 F74. Kappa Omicron letter 1 F50, Delta letter 1 F72, Nu letter 1 F10, Mu Pi Omicron Delta letter 1 FF6, Nu letter 1 F14 Tau Gota Aeschylus. Prom, Vinct. 13. You, force and power, have done your destined task, and naught impedes the work of other hands. 311, Introduction. We enter now upon a new region of the human mind. In passing from astronomy to mechanics, we make a transition from the formal to the physical sciences, from time and space to force and matter, from phenomena to causes. Hitherto, we have been concerned only with the paths and orbits, the periods and cycles, the angles and distances of the objects to which our sciences applied, namely, the heavenly bodies. How these motions are produced, by what agencies, impulses, powers they are determined to be what they are, of what nature are the objects themselves, are speculations which we have hitherto not dwelt upon. The history of such speculations now comes before us, but in the first place, we must consider the history of speculations concerning motion in general, terrestrial as well as celestial. We must first attend to mechanics and afterwards return to physical astronomy. In the same way in which the development of pure mathematics, which began with the Greeks, was a necessary condition of the progress of formal astronomy, the creation of the science of mechanics now became necessary to the formation and progress of physical astronomy. Geometry and mechanics were studied for their own sakes, but they also supplied ideas, language, and reasoning to other sciences. If the Greeks had not cultivated conic sections, Kepler could not have superseded Ptolemy. If the Greeks had cultivated dynamics, Kepler might have anticipated Newton. 312. Note 1/6. Dynamics is the science which treats of the motions of bodies. Statics is the science which treats of the pressure of bodies which are in equilibrium and therefore at rest. Chapter 1. Prelude to the Epoch of Galileo. Sect 1. Prelude to the science of statics. Some steps in the science of motion, or rather in the science of equilibrium, had been made by the ancients, as we have seen. Archimedes established satisfactorily the doctrine of the lever, some important properties of the center of gravity, and the fundamental proposition of hydrostatics. But this beginning led to no permanent progress. Whether the distinction between the principles of the doctrine of equilibrium and of motion was clearly seen by Archimedes, we do not know, but it never was caught hold of by any of the other writers of antiquity or by those of the stationary period. What was still worse, the point which Archimedes had won was not steadily maintained. We have given some examples of the general ignorance of the Greek philosophers on such subjects. In noticing the strange manner in which Aristotle refers to mathematical properties in order to account for the equilibrium of a lever and the attitude of a man rising from a chair. And we have seen, in speaking of the indistinct ideas of the stationary period, that the attempts which were made to extend the statical doctrine of Archimedes failed in such a manner as to show that his followers had not clearly apprehended the idea on which his reasoning altogether depended. The clouds which he had, for a moment, cloven in his advance, closed after him, and the former dimness and confusion settled again on the land. This dimness and confusion, with respect to all subjects of mechanical reasoning, prevailed still at the period we now have to consider, namely, the period of the first promulgation of the Copernican opinions. This is so important a point that I must illustrate it further. Certain general notions of the connection of cause and effect in motion exist in the human mind at all periods of its development, and are implied in the formation of language and in the most familiar employments of men's thoughts. But these do not constitute a science of 313 mechanics, any more than the notions of square and round make a geometry, or the notions of months and years make an astronomy. The unfolding these notions into distinct ideas, on which can be founded principles and reasonings, is further requisite in order to produce a science. And, with respect to the doctrines of motion, this was long in coming to pass. Men's thoughts remained long entangled in their primitive and unscientific confusion. We may mention one or two features of this confusion, such as we find in authors belonging to the period now under review. We have already, in speaking of the Greek school philosophy, noticed the attempt to explain some of the differences among motions by classifying them into natural motions and violent motions. And we have spoken of the assertion that heavy bodies fall quicker in proportion to their greater weight. These doctrines were still retained, yet the views which they implied were essentially erroneous and unsound, for they did not refer distinctly to a measurable force as the cause of all motion or change of motion, and they confounded the causes which produce and those which preserve motion. Hence, such principles did not lead immediately to any advance of knowledge, though efforts were made to apply them, in the cases both of terrestrial mechanics and of the motions of the heavenly bodies. The effect of the inclined plane was one of the first, as it was one of the most important propositions on which modern writers employed themselves. It was found that a body, when supported on a sloping surface, might be sustained or raised by a force or exertion which would not have been able to sustain or raise it without such support. And hence, the inclined plane was placed in the list of mechanical powers, or simple machines, by which the efficacy of forces is increased. The question was, in what proportion this increase of efficiency takes place. It is easily seen that the force requisite to sustain a body is smaller, as the slope on which it rests is smaller. Cardan, whose work, De Proportionibus Numerorum, Motuum, Ponderum, and c. was published in 1545, asserts that the force is double when the angle of inclination is double, and so on for other proportions. This is probably a guess, and is an erroneous one. Guido Ubaldi of Marchmont published at Pesaro in 1577 a work which he called Mechanicorum Liber, in which he endeavors to prove that an acute wedge will produce a greater mechanical effect than an obtuse one, without determining in what proportion. There is, he observes, a certain repugnance between the direction in which the side of the wedge tends to 314, move the obstacle, and the direction in which it really does move. Thus the wedge and the inclined plane are connected in principle. He also refers the screw to the inclined plane and the wedge in a manner which shows a just apprehension of the question. Benedetti, 1585, treats the wedge in a different manner, not exact, but still showing some powers of thought on mechanical subjects. Michael Varro, whose Tractatus de Motu was published at Geneva in 1584, deduces the wedge from the composition of hypothetical motions, in a way which may appear to some persons an anticipation of the doctrine of the composition of forces. There is another work on subjects of this kind, of which several editions were published in the 16th century, and which treats this matter in nearly the same way as Varro, and in favor of which a claim has been made, I think an unfounded one, as if it contained the true principle of this problem. The work is Jordanus Numerarius de Ponderositate. The date and history of this author were probably even then unknown, for in 1599, Benedetti, correcting some of the errors of Tartaglia, says they are taken a Giordano quadam antiquo. The book was probably a kind of school book, and much used, for an edition printed at Frankfurt in 1533 is stated to become Gratia et Praevalgio Imperiali, Petro e piano mathematico ingolstadiano ad xxx annos concesso. But this addition does not contain the inclined plane. Though those who compiled the work assert in words something like the inverse proportion of weights and their velocities, they had not learnt at that time how to apply this maxim to the inclined plane, nor were they ever able to render a sound reason for it. In the edition of Venice, 1565, however, such an application is attempted. The reasonings are founded on the Aristotelian assumption that bodies descend more quickly in proportion as they are heavier. To this principle are added some others, as that a body is heavier in proportion as it descends more directly to the center, and that, in proportion as a body descends more obliquely, the intercepted part of the direct descent is smaller. By means of these principles, the descending force of bodies on inclined planes was compared by a process, which, so far as it forms a line of proof at all, is a somewhat curious example of confused and vicious reasoning. When two bodies are supported on two inclined planes and are connected by a string passing over the junction of the planes, so that when one descends the other ascends, 315, they must move through equal spaces on the planes. But on the plane which is more oblique, that is, more nearly horizontal, the vertical descent will be smaller in the same proportion in which the plane is longer. Hence, by the Aristotelian principle, the weight of the body on the longer plane is less, and to produce an equality of effect, the body must be greater in the same proportion. We may observe that the Aristotelian principle is not only false, but is here misapplied. For its genuine meaning is that when bodies fall freely by gravity, they move quicker in proportion as they are heavier. But the rule is here applied to the motions which bodies would have if they were moved by a force extraneous to their gravity. The proposition was supposed by the Aristotelians to be true of actual velocities. It is applied by Jordanus to virtual velocities, without his being aware what he was doing. This confusion being made, the result is got at by taking for granted that bodies thus proved to be equally heavy have equal powers of descent on the inclined planes, whereas, in the previous part of the reasoning, the weight was supposed to be proportional to the descent in the vertical direction. It is obvious in all this that though the author had adopted the false Aristotelian principle, he had not settled in his own mind whether the motions of which it spoke were actual or virtual motions, motions in the direction of the inclined plane, or of the intercepted parts of the vertical, corresponding to these, nor whether the descending force of a body was something different from its weight. We cannot doubt that, if he had been required to point out, with any exactness, the cases to which his reasoning applied, he would have been unable to do so, not possessing any of those clear fundamental ideas of pressure and force, on which alone any real knowledge on such subjects must depend. The whole of Jordanus's reasoning is an example of the confusion of thought of his period, and of nothing more. It no more supplied the want of some man of genius, who should give the subject a real scientific foundation, than Aristotle's knowledge of the proportion of the weights on the lever superseded the necessity of Archimedes's proof of it. Note 2/6, Mr. Drinkwater's Life of Galileo in the Lib, Usef, KNP 83. We are not, therefore, to wonder that, though this pretended theorem was copied by other writers, as by Tartaglia, in his Caecidi et Inventioni Diversi, published in 1554, no progress was made in the real solution of any one mechanical problem by means of it. Guido Ubaldi, who, in 1577, writes in such a manner as to show that he had taken a good hold of his subject for his time, refers to Pappus's solution of the problem of the inclined plane, but makes no mention of that of 316, Jordanus, and Tartaglia. No progress was likely to occur till the mathematicians had distinctly recovered the genuine idea of pressure, as a force producing equilibrium, which Archimedes had possessed, and which was soon to reappear in Stevinus. Note 3/6, Ubaldi mentions and blames Jordanus's way of treating the lever. See his preface. The properties of the lever had always continued known to mathematicians, although, in the dark period, the superiority of the proof given by Archimedes had not been recognized. We are not to be surprised if reasonings like those of Jordanus were applied to demonstrate the theories of the lever with apparent success. Writers on mechanics were, as we have seen, so vacillating in their mode of dealing with words and propositions that their maxims could be made to prove anything which was already known to be true. We proceed to speak of the beginning of the real progress of mechanics in modern times. Sect 2. Revival of the scientific idea of pressure, Stevinus, equilibrium of oblique forces. The doctrine of the center of gravity was the part of the mechanical speculations of Archimedes which was most diligently prosecuted after his time. Pappus and others, among the ancients, had solved some new problems on this subject, and Commandinus, in 1565, published De Centro Gravitatis Solidorum. Such treatises contained, for the most part, only mathematical consequences of the doctrines of Archimedes, but the mathematicians also retained a steady conviction of the mechanical property of the center of gravity, namely, that all the weight of the body might be collected there, without any change in the mechanical results. A conviction which is closely connected with our fundamental conceptions of mechanical action. Such a principle, also, will enable us to determine the result of many simple mechanical arrangements. For instance, if a mathematician of those days had been asked whether a solid ball could be made of such a form, that, when placed on a horizontal plane, it should go on rolling forwards without limit merely by the effect of its own weight, he would probably have answered that it could not. For that the center of gravity of the ball would seek the lowest position it could find, and that, when it had found this, the ball could have no tendency to roll any further. And in making this assertion, the supposed reasoner would not be 317, anticipating any wider proof of the impossibility of a perpetual motion drawn from principles subsequently discovered, but would be referring the question to certain fundamental convictions, which, whether put into axioms or not, inevitably accompany our mechanical conceptions. In the same way, Stevinus of Bruges in 1586, when he published his Beghinsellen der Waagkunst Principles of Equilibrium, had been asked why a loop of chain hung over a triangular beam could not, as he asserted it could not, go on moving round and round perpetually by the action of its own weight, he would probably have answered that the weight of the chain, if it produced motion at all, must have a tendency to bring it into some certain position, and that when the chain had reached this position, it would have no tendency to go any further, and thus he would have reduced the impossibility of such a perpetual motion to the conception of gravity as a force tending to produce equilibrium, a principle perfectly sound and correct. Upon this principle thus applied, Stevinus did establish the fundamental property of the inclined plane. He supposed a loop of string, loaded with 14 equal balls at equal distances, to hang over a triangular support which was composed of two inclined planes with a horizontal base, and whose sides, being unequal in the proportion of 2 to 1, supported 4 and 2 balls respectively. He showed that this loop must hang at rest, because any motion would only bring it into the same condition in which it was at first, and that the festoon of 8 balls which hung down below the triangle might be removed without disturbing the equilibrium, so that 4 balls on the longer plane would balance 2 balls on the shorter plane, or in other words, the weights would be as the lengths of the planes intercepted by the horizontal line. Stevinus showed his firm possession of the truth contained in this principle, by deducing from it the properties of forces acting in oblique directions under all kinds of conditions. In short, he showed his entire ability to found upon it a complete doctrine of equilibrium. And upon his foundations, and without any additional support, the mathematical doctrines of statics might have been carried to the highest pitch of perfection they have yet reached. The formation of the science was finished. The mathematical development and exposition of it were alone open to extension and change. Simon Stevin of Bruges, as he usually designates himself in the title page of his work, has lately become an object of general interest in his own country, and it has been resolved to erect a 318 statue in honor of him in one of the public places of his native city. He was born in 1548, as I learn from M. Quetelet's notice of him, and died in 1620. Montucla says that he died in 1633, misled apparently by the preface to Albert Gerard's edition of Stevin's works, which was published in 1634 and which speaks of a death which took place in the preceding year. But on examination, it will be seen that this refers to Gerard, not to Stevin. I ought to have mentioned, in consideration of the importance of the proposition, that Stevin distinctly states the triangle of forces, namely, that three forces which act upon a point are in equilibrium when they are parallel and proportional to the three sides of any plane triangle. This includes the principle of the composition of statical forces. Stevin also applies his principle of equilibrium to cordage, pulleys, funicular polygons, and especially to the bits of bridles, a branch of mechanics which he calls Chalon-ellipsis. He has also the merit of having seen very clearly the distinction of statical and dynamical problems. He remarks that the question, what force will support a loaded wagon on an inclined plane, is a statical question depending on simple conditions, but that the question, what force will move the wagon, requires additional considerations to be introduced. In Chapter 4 of this book, I have noticed Stevin's share in the rediscovery of the laws of the equilibrium of fluids. He distinctly explains the hydrostatic paradox, of which the discovery is generally ascribed to Pascal. Earlier than Stevinus, Leonardo da Vinci must have a place among the discoverers of the conditions of equilibrium of oblique forces. He published no work on this subject, but extracts from his manuscripts have been published by Venturi in his Essai sur les ouvrages physico-mathématiques de Léonard de Vinci, avec des fragments tirés de ses manuscrits apportés d'Italie, Paris, 1797, and by Libri in his Hist. des Sc. Math. En Italy, 1839. I have also myself examined these manuscripts in the Royal Library at Paris. It appears that, as early as 1499, Leonardo gave a perfectly correct statement of the proportion of the forces exerted by a cord which acts obliquely and supports a weight on a lever. He distinguishes between the real lever and the potential levers, that is, the perpendiculars drawn from the center upon the directions of the forces. This is quite sound and satisfactory. These views must in all probability have been sufficiently promulgated in Italy to influence the speculations of Galileo. 319, whose reasonings respecting the lever much resemble those of Leonardo da Vinci, also anticipated Galileo in asserting that the time of descent of a body down an inclined plane is to the time of descent down its vertical length in the proportion of the length of the plane to the height. But this cannot, I think, have been more than a guess. There is no vestige of a proof given. The contemporaneous progress of the other branch of mechanics, the doctrine of motion, interfered with this independent advance of statics, and to that we must now turn. We may observe, however, that true propositions respecting the composition of forces appear to have rapidly diffused themselves. The Tractatus de Motu of Michael Varro of Geneva, already noticed, printed in 1584, had asserted that the forces which balance each other, acting on the sides of a right-angled triangular wedge, are in the proportion of the sides of the triangle. And although this assertion does not appear to have been derived from a distinct idea of pressure, the author had hence rightly deduced the properties of the wedge and the screw. And shortly after this time, Galileo also established the same results on different principles. In his treatise Del Sciens Mechanisch, 1592, he refers the inclined plane to the lever in a sound and nearly satisfactory manner, imagining a lever so placed that the motion of a body at the extremity of one of its arms should be in the same direction as it is upon the plane. A slight modification makes this an unexceptionable proof. Sect 3, Prelude to the Science of Dynamics attempts at the first law of motion. We have already seen that Aristotle divided motions into natural and violent. Cardan endeavored to improve this division by making three classes: voluntary motion, which is circular and uniform, and which is intended to include the celestial motions; natural motion, which is stronger towards the end, as the motion of a falling body. This is in a straight line, because it is motion to an end, and nature seeks her ends by the shortest road. And thirdly, violent motion, including in this term all kinds different from the former two. Cardan was aware that such violent motion might be produced by a very small force. Thus he asserts that a spherical body resting on a horizontal plane may be put in motion by any force which is sufficient to cleave the air. For which, however, he erroneously assigns as a reason, 320, the smallness of the point of contact. But the most common mistake of this period was that of supposing that as force is requisite to move a body, so a perpetual supply of force is requisite to keep it in motion. The whole of what Kepler called his physical reasoning depended upon this assumption. He endeavored to discover the forces by which the motions of the planets about the Sun might be produced. But in all cases, he considered the velocity of the planet as produced by, and exhibiting the effect of, a force which acted in the direction of the motion. Kepler's essays, which are in this respect so feeble and unmeaning, have sometimes been considered as disclosing some distant anticipation of Newton's discovery of the existence and law of central forces. There is, however, in reality, no other connection between these speculations than that which arises from the use of the term force by the two writers in two utterly different meanings. Kepler's forces were certain imaginary qualities which appeared in the actual motion which the bodies had. Newton's forces were causes which appeared by the change of motion. Kepler's forces urged the bodies forwards. Newton's deflected the bodies from such a progress. If Kepler's forces were destroyed, the body would instantly stop. If Newton's were annihilated, the body would go on uniformly in a straight line. Kepler compares the action of his forces to the way in which a body might be driven round by being placed among the sails of a windmill. Newton's forces would be represented by a rope pulling the body to the center. Newton's force is merely mutual attraction. Kepler's is something quite different from this, for though he perpetually illustrates his views by the example of a magnet, he warns us that the Sun differs from the magnet in this respect, that its force is not attractive, but directive. Kepler's essays may, with considerable reason, be asserted to be an anticipation of the vortices of Descartes, but they can with no propriety whatever be said to anticipate Newton's dynamical theory. Note 4/6. In speaking of the force which would draw a body up an inclined plane, he observes that per communum animi sententiam, when the plane becomes horizontal, the requisite force is nothing. The confusion of thought which prevented mathematicians from seeing the difference between producing and preserving motion was, indeed, fatal to all attempts at progress on this subject. We have already noticed the perplexity in which Aristotle involved himself, by his endeavors to find a reason for the continued motion of a stone, 321, after the moving power had ceased to act, and that he had ascribed it to the effect of the air or other medium in which the stone moves. Tartaglia, whose Nuova Scienza is dated 1550, though a good pure mathematician, is still quite in the dark on mechanical matters. One of his propositions, in the work just mentioned, is b.I. Prop 3, the more a heavy body recedes from the beginning or approaches the end of violent motion, the slower and more inertly it goes, which he applies to the horizontal motion of projectiles. In like manner, most other writers about this period conceive that a cannonball goes forwards till it loses all its projectile motion and then falls downwards. Benedetti, who has already been mentioned, must be considered as one of the first enlightened opponents of this and other Aristotelian errors or puzzles. In his Speculationum Liber, Venice, 1585, he opposes Aristotle's mechanical opinions with great expressions of respect, but in a very sweeping manner. His chapter 24 is headed, "Whether this eminent man was right in his opinion concerning violent and natural motion." And after stating the Aristotelian opinion just mentioned, that the body is impelled by the air, he says that the air must impede rather than impel the body, and that the motion of the body, separated from the mover, arises by a certain natural impression from the impetuosity, ex impetuositate, received from the mover. He adds that in natural motions this impetuosity continually increases by the continued action of the cause, namely, the propension of going to the place assigned it by nature, and that thus the velocity increases as the body moves from the beginning of its path. This statement shows a clearness of conception with regard to the cause of accelerated motion, which Galileo himself was long in acquiring. Though Benedetti was thus on the way to the first law of motion, that all motion is uniform and rectilinear, except so far as it is affected by extraneous forces, this law was not likely to be either generally conceived or satisfactorily proved till the other laws of motion, by which the action of forces is regulated, had come into view. Hence, though a partial apprehension of this principle had preceded the discovery of the laws of motion, we must place the establishment of the principle in the period when those laws were detected and established, the period of Galileo and his followers. 322. Chapter 2. Inductive epoch of Galileo discovery of the laws of motion in simple cases. Sect 1. Establishment of the first law of motion. After mathematicians had begun to doubt or reject the authority of Aristotle, they were still some time in coming to the conclusion that the distinction of natural and violent motions was altogether untenable, that the velocity of a body in motion increased or diminished in consequence of the action of extrinsic causes, not of any property of the motion itself, and that the apparently universal fact of bodies growing slower and slower, as if by their own disposition, till they finally stopped, from which motions had been called violent, arose from the action of external obstacles not immediately obvious, as the friction and the resistance of the air when a ball runs on the ground, and the action of gravity when it is thrown upwards. But the truth to which they were at last led was that such causes would account for all the diminution of velocity which bodies experience when apparently left to themselves, and that without such causes, the motion of all bodies would go on forever, in a straight line and with a uniform velocity. Who first announced this law in a general form, it may be difficult to point out. Its exact or approximate truth was necessarily taken for granted in all complete investigations on the subject of the laws of motion of falling bodies, and of bodies projected so as to describe curves. In Galileo's first attempt to solve the problem of falling bodies, he did not carry his analysis back to the notion of force, and therefore this law does not appear. In 1604, he had an erroneous opinion on this subject, and we do not know when he was led to the true doctrine which he published in his Discorso in 1638. In his third dialogue, he gives the instance of water in a vessel, for the purpose of showing that circular motion has a tendency to continue. And in his first dialogue on the Copernican system, published in 1630, he asserts 323 circular motion alone to be naturally uniform, and retains the distinction between natural and violent motion. In the Dialogues on Mechanics, however, published in 1638, but written apparently at an earlier period, in treating of projectiles, he asserts the true law. Mobile superplanum horizontal projectum ment concipio omni secluso impedimento. Jam constat ex his qui fusius alibi dicta sunt, Elias modum equibilum et perpetuum super ipso plano futurum esse, si planum in infinitum extendetur. Conceive a movable body upon a horizontal plane, and suppose all obstacles to motion to be removed. It is then manifest, from what has been said more at large in another place, that the body's motion will be uniform and perpetual upon the plane, if the plane be indefinitely extended. His pupil Borelli in 1667, in the treatise De Roman VI Percussionis, states the proposition generally that velocity is, by its nature, uniform and perpetual. And this opinion appears to have been, at that time, generally diffused, as we find evidence in Wallis and others. It is commonly said that Descartes was the first to state this generally. His Principia were published in 1644, but his proofs of this first law of motion are rather of a theological than of a mechanical kind. His reason for this law is the immutability and simplicity of the operation by which God preserves motion in matter. For he only preserves it precisely as it is in that moment in which he preserves it, taking no account of that which may have been previously. Reasoning of this abstract and a priori kind, though it may be urged in favor of true opinions after they have been inductively established, is almost equally capable of being called in on the side of error, as we have seen in the case of Aristotle's philosophy. We ought not, however, to forget that the reference to these abstract and a priori principles is an indication of the absolute universality and necessity which we look for in complete sciences, and a result of those faculties by which such science is rendered possible and suitable to man's intellectual nature. The induction by which the first law of motion is established consists, as induction consists in all cases, in conceiving clearly the law and in perceiving the subordination of facts to it. But the law speaks of bodies not acted upon by any external force case, which never occurs in fact. And the difficulty of the step consisted in bringing all the common cases in which motion is gradually extinguished, under the notion of the action of a retarding force. In order to do this, 324 Hooke and others showed that, by diminishing the obvious resistances, the retardation also became less. And men were gradually led to a distinct appreciation of the resistance, friction, and c, which, in all terrestrial motions, prevent the law from being evident. And thus they at last established by experiment a law which cannot be experimentally exemplified. The natural uniformity of motion was proved by examining all kinds of cases in which motion was not uniform. Men culled the abstract rule out of the concrete experiment, although the rule was, in every case, mixed with other rules, and each rule could be collected from the experiment only by supposing the others known. The perfect simplicity, which we necessarily seek for in a law of nature, enables us to disentangle the complexity, which this combination appears at first sight to occasion. The first law of motion asserts that the motion of a body, when left to itself, will not only be uniform, but rectilinear also. This latter part of the law is indeed obvious of itself as soon as we conceive a body detached from all special reference to external points and objects. Yet, as we have seen, Galileo asserted that the naturally uniform motion of bodies was that which takes place in a circle. Benedetti, however, in 1585, had entertained sound notions on this subject. In commenting on Aristotle's question, why we obtain an advantage in throwing by using a sling, he says that the body, when whirled round, tends to go on in a straight line. In Galileo's second dialogue, he makes one of his interlocutors, Simplicio, when appealed to on this subject, after thinking intently for a little while, give the same opinion. And the principle is, from this time, taken for granted by the authors who treat of the motion of projectiles. Descartes, as might be supposed, gives the same reason for this as for the other part of the law, namely, the immutability of the deity. Note 10:6, Corpus velit recta iter periger, asterisk speculationum liber, p. 160. Sect. 2. Formation and application of the notion of accelerating force, laws of falling bodies. We have seen how rude and vague were the attempts of Aristotle and his followers to obtain a philosophy of bodies falling downwards or thrown in any direction. If the first law of motion had been clearly known, it would then, perhaps, have been seen that the way to understand and analyze the motion of any body is to consider the 325 causes of change of motion which at each instant operate upon it. And thus men would have been led to the notion of accelerating forces, that is, forces which act upon bodies already in motion and accelerate, retard, or deflect their motions. It was, however, only after many attempts that they reached this point. They began by considering the whole motion with reference to certain ill-defined abstract notions, instead of considering, with a clear apprehension of the conditions of causation, the successive parts of which the motion consists. Thus, they spoke of the tendency of bodies to the center or to their own place, of projecting force, of impetus, of retraction, with little or no profit to knowledge. The indistinctness of their notions may, perhaps, be judged of from their speculations concerning projectiles. Sandbach, in 1561, imagined that a body thrown with great velocity, as, for instance, a ball from a cannon, went in a straight line till all its velocity was exhausted, and then fell directly downwards. He has written a treatise on gunnery, founded on this absurd assumption. To this succeeded another doctrine, which, though not much more philosophical than the former, agreed much better with the phenomena. Niccolo Tartaglia, Nuova Scienza, Venice, 1550. Caecidi et Inventioni Diversi, 1554, and Gualter Rivius, Architectura, and c. Basel, 1582, represented the path of a cannonball as consisting, first of a straight line in the direction of the original projection, then of an arc of a circle in which it went on till its motion became vertical downwards, and then of a vertical line in which it continued to fall. The latter of these writers, however, was aware that the path must from the first be a curve, and treated it as a straight line only because the curvature is very slight. Even Sandbach's figure represents the path of the ball as partially descending before its final fall, but then it descends by steps, not in a curve. Sandbach, therefore, did not conceive the composition of the effect of gravity with the existing motion, but supposed them to act alternately. Rivius, however, understood this composition and saw that gravity must act as a deflecting force at every point of the path. Galileo, in his second dialogue, makes Simplicius come to the same conclusion. Since, he says, there is nothing to support the body, when it quits that which projects it, it cannot be but that its proper gravity must operate, and it must immediately begin to decline downwards. 326. Note 11/6. Problematum astronomicorum et geometricorum sections Roman 7, and C Octor Daniel Santbach, Novaya Mago. Basili, 1561. The force of gravity, which thus produces deflection and curvature in the path of a body thrown obliquely, constantly increases the velocity of a body when it falls vertically downwards. The universality of this increase was obvious, both from reasoning and in fact. The law of it could only be discovered by closer consideration, and the full analysis of the problem required a distinct measure of the quantity of accelerating force. Galileo, who first solved this problem, began by viewing it as a question of fact, but conjectured the solution by taking for granted that the rule must be the simplest possible. Bodies, he says, will fall in the most simple way, because natural motions are always the most simple. When a stone falls, if we consider the matter attentively, we shall find that there is no addition, no increase of the velocity more simple than that which is always added in the same manner. That is, when equal additions take place in equal times, which we shall easily understand if we attend to the close connection of motion and time. From this law, thus assumed, he deduced that the spaces described from the beginning of the motion must be as the squares of the times. And again, assuming that the laws of descent for balls rolling down inclined planes must be the same as for bodies falling freely, he verified this conclusion by experiment. It will, perhaps, occur to the reader that this argument, from the simplicity of the assumed law, is somewhat insecure. It is not always easy for us to discern what that greatest simplicity is, which nature adopts in her laws. Accordingly, Galileo was led wrong by this way of viewing the subject before he was led right. He at first supposed that the velocity which the body had acquired at any point must be proportional to the space described from the point where the motion began. This false law is as simple in its enunciation as the true law that the velocity is proportional to the time. It had been asserted as the true law by M. Varro, De Motu Tractatus, Genevae, 1584, and by Baliani, a gentleman of Genoa, who published it in 1638. It was, however, soon rejected by Galileo, though it was afterwards taken up and defended by Casrius, one of Galileo's opponents. It so happens, indeed, that the false law is not only at variance with fact, but with itself. It involves a mathematical self-contradiction. This circumstance, however, was accidental. It would be easy to state laws of the increase of velocity which should be simple, and yet false in fact, though quite possible in their own nature. 327. The law of velocity was hitherto, as we have seen, treated as a law of phenomena without reference to the causes of the law. The cause of the acceleration of the motions of falling bodies is not, Galileo observes, a necessary part of the investigation. Opinions are different. Some refer it to the approach to the center. Others say that there is a certain extension of the centrical medium which, closing behind the body, pushes it forwards. For the present, it is enough for us to demonstrate certain properties of accelerated motion, the acceleration being according to the very simple law that the velocity is proportional to the time. And if we find that the properties of such motion are verified by the motions of bodies descending freely, we may suppose that the assumption agrees with the laws of bodies falling freely by the action of gravity. It was, however, an easy step to conceive this acceleration as caused by the continual action of gravity. This account had already been given by Benedetti, as we have seen. When it was once adopted, gravity was considered as a constant or uniform force. On this point, indeed, the adherents of the law of Galileo and of that of Casrius were agreed, but the question was, what is a uniform force? The answer which Galileo was led to give was obviously this. That is a uniform force which generates equal velocities in equal successive times. And this principle leads at once to the doctrine that forces are to be compared by comparing the velocities generated by them in equal times. Though, however, this was a consequence of the rule by which gravity is represented as a uniform force, the subject presents some difficulty at first sight. It is not immediately obvious that we may thus measure forces by the velocity added in a given time, without taking into account the velocity they have already. If we communicate velocity to a body by the hand, or by a spring, the effect we produce in a second of time is lessened, when the body has already a velocity which withdraws it from the pressure of the agent. But it appears that this is not so in the case of gravity. The velocity added in 1 second is the same, whatever downward motion the body already possesses. A body falling from rest acquires a velocity, in 1 second, of 32 feet. And if a cannonball were shot downwards with a velocity of 1,000 feet a second, it would equally, at the end of 1 second, have received an accession of 32 feet to its velocity. This conception of gravity as a uniform force as constantly, and 328, equally increasing the velocity of a descending body, will become clear by a little attention, but it undoubtedly presents difficulty at first. Accordingly, we find that Descartes did not accept it. It is certain, he says, that a stone is not equally disposed to receive a new motion or increase of velocity when it is already moving very quickly and when it is moving slowly. Descartes showed, by other expressions, that he had not caught hold of the true notion of accelerating force. Thus, he says in a letter to Mersenne, "I am astonished at what you tell me of having found, by experiment, that bodies thrown up in the air take neither more nor less time to rise than to fall again. And you will excuse me if I say that I look upon the experiment as a very difficult one to make accurately. Yet it is clear from the notion of a constant force that, omitting the resistance of the air, this equality must take place. For the force which will gradually destroy the whole velocity in a certain time in ascending, will, in the same time, generate again the same velocity by the same gradations inverted, and therefore the same space will be passed over in the same time in the descent and in the ascent." Another difficulty arose from a necessary consequence of the laws of falling bodies thus established. The proposition, namely, that in acquiring its motion, a body passes through every intermediate degree of velocity, from the smallest conceivable up to that which it at last acquires. When a body falls from rest, it begins to fall with no velocity. The velocity increases with the time, and in 1,000th part of a second, the body has only acquired 1,000th part of the velocity which it has at the end of 1 second. This is certain and manifest on consideration. Yet there was at first much difficulty raised on the subject of this assertion, and disputes took place concerning the velocity with which a body begins to fall. On this subject also Descartes did not form clear notions. He writes to a correspondent, "I have been revising my notes on Galileo, in which I have not said expressly that falling bodies do not pass through every degree of slowness, but I said that this cannot be known without knowing what weight is, which comes to the same thing. As to your example, I grant that it proves that every degree of velocity is infinitely divisible, but not that a falling body actually passes through all these divisions." The principles of the motion of falling bodies being thus established by Galileo, the deduction of the principal mathematical consequences was, as is usual, effected with great rapidity, and is to be found, 329 in his works, and in those of his scholars and successors. The motion of bodies falling freely was, however, in such treatises, generally combined with the motion of bodies falling along inclined planes, a part of the theory of which we have still to speak. The notion of accelerating force and of its operation, once formed, was naturally applied in other cases than that of bodies falling freely. The different velocities with which heavy and light bodies fall were explained by the different resistance of the air, which diminishes the accelerating force, and it was boldly asserted that in a vacuum a lock of wool and a piece of lead would fall equally quickly. It was also maintained that any falling body, however large and heavy, would always have its velocity in some degree diminished by the air in which it falls, and would at last be reduced to a state of uniform motion, as soon as the resistance upwards became equal to the accelerating force downwards. Though the law of progress of a body to this limiting velocity was not made out till the Principia of Newton appeared, the views on which Galileo made this assertion are perfectly sound, and show that he had clearly conceived the nature and operation of accelerating and retarding force. When uniform accelerating forces had once been mastered, there remained only mathematical difficulties in the treatment of variable forces. A variable force was measured by the limit of the increment of the velocity, compared with the increment of the time, just as a variable velocity was measured by the limit of the increment of the space compared with that of the time. With this introduction of the notion of limits, we are, of course, led to the higher geometry, either in its geometrical or its analytical form. The general laws of bodies falling by the action of any variable forces were given by Newton in the 7th section of the Principia. The subject is there, according to Newton's preference of geometrical methods, treated by means of the quadrature of curves, the doctrine of limits being exhibited in a peculiar manner in the first section of the work, in order to prepare the way for such applications of it. Leibniz, the Bernoullis, Euler, and since their time, many other mathematicians have treated such questions by means of the analytical method of limits, the differential calculus. The rectilinear motion of bodies acted upon by variable forces is, of course, a simpler problem than their curvilinear motion, to which we have now to proceed. But at 330 may be remarked that Newton, having established the laws of curvilinear motion independently, has, in a great part of his 7th section, deduced the simpler case of the rectilinear motion from the move complex problem, by reasonings of great ingenuity and beauty. Sect 3 Establishment of the second law of motion, curvilinear motions. A slight degree of distinctness in men's mechanical notions enabled them to perceive, as we have already explained, that a body which traces a curved line must be urged by some force, by which it is constantly made to deviate from that rectilinear path, which it would pursue if acted upon by no force. Thus, when a body is made to describe a circle, as when a stone is whirled round in a sling, we find that the string does exert such a force on the stone, for the string is stretched by the effort, and if it be too slender, it may thus be broken. This centrifugal force of bodies moving in circles was noticed even by the ancients. The effect of force to produce curvilinear motion also appears in the paths described by projectiles. We have already seen that though Tartaglia did not perceive this correctly, Rivius, about the same time, did. To see that a transverse force would produce a curve was one step, to determine what the curve is was another step, which involved the discovery of the second law of motion. This step was made by Galileo. In his Dialogues on Motion, he asserts that a body projected horizontally will retain a uniform motion in the horizontal direction, and will have, compounded with this, a uniformly accelerated motion downwards, that is, the motion of a body falling vertically from rest, and will thus describe the curve called a parabola. The second law of motion consists of this assertion in a general form, namely, that in all cases the motion which the force will produce is compounded with the motion which the body previously has. This was not obvious, for Cardan had maintained that if a body is moved by two motions at once, it will come to the place resulting from their composition slower than by either of them. The proof of the truth of the law to Galileo's mind was, so far as we collect from the dialogue itself, the simplicity of the supposition, and his clear perception of the causes which, in some cases, produced an obvious deviation in practice, 331, from this theoretical result. For it may be observed that the curvilinear paths ascribed to military projectiles by Rivius and Tartaglia, and by other writers who followed them, as Digges and Norton in our own country, though utterly different from the theoretical form, the parabola do, in fact, approach nearer the true paths of a cannon or musket ball than a parabola would do. And this approximation more especially exists in that which at first sight appears most absurd in the old theory. Namely, the assertion that the ball, which ascends in a sloping direction, finally descends vertically. In consequence of the resistance of the air, this is really the path of a projectile, and when the velocity is very great, as in military projectiles, the deviation from the parabolic form is very manifest. This cause of discrepancy between the theory, which does not take resistance into the account, and the fact Galileo perceived, and accordingly he says that the velocities of the projectiles in such cases may be considered as excessive and supernatural. With the due allowance to such causes, he maintained that his theory was verified and might be applied in practice. Such practical applications of the doctrine of projectiles no doubt had a share in establishing the truth of Galileo's views. We must not forget, however, that the full establishment of this second law of motion was the result of the theoretical and experimental discussions concerning the motion of the earth. Its fortunes were involved in those of the Copernican system, and it shared the triumph of that doctrine. This triumph was already decisive, indeed, in the time of Galileo, but not complete till the time of Newton. Sect 4. Generalization of the laws of equilibrium, principle of virtual velocities. It was known, even as early as Aristotle, that the two weights which balance each other on the lever, if they move at all, move with velocities which are in the inverse proportions of the weights. The peculiar resources of the Greek language, which could state this relation of inverse proportionality in a single word, letter 1 f00 nu tau oda pi epsilon pi omicron u theta epsilon u, fixed it in men's minds and prompted them to generalize from this property. Such attempts were at first made with indistinct ideas and on conjecture only, and had therefore no scientific value. This is the judgment which we must pass on the book of Jordanus Numerarius, which 332 we have already mentioned. Its reasonings are professedly on Aristotelian principles and exhibit the common Aristotelian absence of all distinct mechanical ideas. But in Varro, whose Tractatus de Motu appeared in 1584, we find the principle, in a general form, not satisfactorily proved indeed, but much more distinctly conceived. This is his first theorem. Duorum virium connexarum quarum, si movinter, modus erunt ipsis letter 1 f00, nu tau iota pi epsilon pi omicron nu theta letter 1 ff6 sigma proportionals, neutra alteram movabit, sed equilibrium facient. The proof offered of this is that the resistance to a force is as the motion produced, and, as we have seen, the theorem is rightly applied in the example of the wedge. From this time, it appears to have been usual to prove the properties of machines by means of this principle. This is done, for instance, in Les Racines des Forces Mouvantes, the production of Solomon de Caus, engineer to the Elector Palatine, published at Antwerp in 1616, in which the effect of toothed wheels and of the screw is determined in this manner, but the inclined plane is not treated of. The same is the case in Bishop Wilkins's Mathematical Magic in 1648. When the true doctrine of the inclined plane had been established, the laws of equilibrium for all the simple machines or mechanical powers, as they had usually been enumerated in books on mechanics, were brought into view. For it was easy to see that the wedge and the screw involved the same principle as the inclined plane, and the pulley could obviously be reduced to the lever. It was also not difficult for a person with clear mechanical ideas to perceive how any other combination of bodies, on which pressure and traction are exerted, may be reduced to these simple machines, so as to disclose the relation of the forces. Hence, by the discovery of Stevinus, all problems of equilibrium were essentially solved. The conjectural generalization of the property of the lever, which we have just mentioned, enabled mathematicians to express the solution of all these problems by means of one proposition. This was done by saying that in raising a weight by any machine, we lose in time what we gain in force. The weight raised moves as much slower than the power as it is larger than the power. This was explained with great clearness by Galileo in the preface to his treatise on mechanical science, published in 1592. The motions, however, which we here suppose the parts of the machine to have, are not motions which the forces produce. For at present we are dealing with the case in which the forces balance each other, and therefore produce no motion. But we ascribe to the 333 weights and powers hypothetical motions, arising from some other cause. And then, by the construction of the machine, the velocities of the weights and powers must have certain definite ratios. These velocities, being thus hypothetically supposed and not actually produced, are called virtual velocities. And the general law of equilibrium is that in any machine, the weights which balance each other are reciprocally to each other as their virtual velocities. This is called the principle of virtual velocities. This principle, which was afterwards still further generalized, is, by some of the admirers of Galileo, dwelt upon as one of his great services to mechanics. But if we examine it more nearly, we shall see that it has not much importance in our history. It is a generalization, but a generalization established rather by enumeration of cases than by any induction proceeding upon one distinct idea, like those generalizations of facts by which laws are primarily established. It rather serves verbally to conjoin laws previously known than to exhibit a connection in them. It is rather a help for the memory than a proof for the reason. The principle of virtual velocities is so far from implying any clear possession of mechanical ideas that anyone who knows the property of the lever, whether he is capable of seeing the reason for it or not, can see that the greater weight moves slower in the exact proportion of its greater magnitude. Accordingly, Aristotle, whose entire want of sound mechanical views we have shown, has yet noticed this truth. When Galileo treats of it, instead of offering any reasons which could independently establish this principle, he gives his readers a number of analogies and illustrations, many of them very loose ones. Thus, the raising a great weight by a small force, he illustrates by supposing the weight broken into many small parts, and conceiving those parts raised one by one. By other persons, the analogy, already intimated, of gain and loss is referred to as an argument for the principle in question. Such images may please the fancy, but they cannot be accepted as mechanical reasons. Since Galileo neither first enunciated this rule, nor ever proved it as an independent principle of mechanics, we cannot consider the discovery of it as one of his mechanical achievements. Still less can we compare his reference to this principle with Stevinus's proof of the inclined plane, which, as we have seen, was rigorously inferred from the sound axiom that a body cannot put itself in motion. If we were to assent to the really self-evident axioms of Stevinus, only in virtue 334 of the unproved verbal generalization of Galileo, we should be in great danger of allowing ourselves to be referred successively from one truth to another, without any reasonable hope of ever arriving at anything ultimate and fundamental. But though this principle of virtual velocity cannot be looked upon as a great discovery of Galileo, it is a highly useful rule, and the various forms under which he and his successors urged it tended much to dissipate the vague wonder with which the effects of machines had been looked upon, and thus to diffuse sounder and clearer notions on such subjects. The principle of virtual velocities also affected the progress of mechanical science in another way. It suggested some of the analogies by the aid of which the third law of motion was made out, leading to the adoption of the notion of momentum as the arithmetical product of weight and velocity. Since on a machine on which a weight of 2 pounds at one part balances 3 pounds at another part, the former weight would move through 3 inches while the latter would move through 2 inches. We see, since 3 multiplied into 2 is equal to 2 multiplied into 3, that the product of the weight and the velocity is the same for the two balancing weights. And if we call this product momentum, the law of equilibrium is that when two weights balance on a machine, the momentum of the two would be the same if they were put in motion. The notion of momentum was here employed in connection with virtual velocities, but it also came under consideration in treating of actual velocities, as we shall soon see. Sect 5 attempts at the third law of motion notion of momentum. In the questions we have hitherto had to consider respecting motion, no regard is had to the size of the body moved, but only to the velocity and direction of the motion. We must now trace the progress of knowledge respecting the mode in which the mass of the body influences the effect of force. This is a more difficult and complex branch of the subject, but it is one which requires to be noticed as obviously as the former. Questions belonging to this department of mechanics, as well as to the others, occur in Aristotle's mechanical problems. Why, says he, is it that neither very small nor very large bodies go far when we throw them, but in order that this may, 335, happen, the thing thrown must have a certain proportion to the agent which throws it? Is it that what is thrown or pushed must react against that which pushes it, and that a body so large as not to yield at all, or so small as to yield entirely, and not to react, produces no throw or push? The same confusion of ideas prevailed after his time, and mechanical questions were in vain discussed by means of general and abstract terms, employed with no distinct and steady meaning, such as impetus, power, momentum, virtue, energy, and the like. From some of these speculations, we may judge how thorough the confusion in men's heads had become. Cardan perplexes himself with the difficulty, already mentioned, of the comparison of the forces of bodies at rest and in motion. If the force of a body depends on its velocity, as it appears to do, how is it that a body at rest has any force at all, and how can it resist the slightest effort or exert any pressure? He flatters himself that he solves the question by asserting that bodies at rest have an occult motion. Corpus moviter occulto modu quiescendo. Another puzzle, with which he appears to distress himself rather more wantonly, is this. If one man can draw half of a certain weight, and another man also one half, when the two act together, these proportions should be compounded, so that they ought to be able to draw one half of one half, or 1/4 only. The talent which ingenious men had for getting into such perplexities was certainly at one time very great. Arriaga, who wrote in 1639, is troubled to discover how several flat weights, lying one upon another on a board, should produce a greater pressure than the lowest one alone produces, since that alone touches the board. Among other solutions, he suggests that the board affects the upper weight, which it does not touch, by determining its ubication or wearness. Aristotle's doctrine that a body 10 times as heavy as another will fall 10 times as fast is another instance of the confusion of statical and dynamical forces. The force of the greater body, while at rest, is 10 times as great as that of the other, but the force as measured by the velocity produced is equal in the two cases. The two bodies would fall downwards with the same rapidity, except so far as they are affected by accidental causes. The merit of proving this by experiment, and thus refuting the Aristotelian dogma, is usually ascribed to Galileo, who made his experiment from the famous Leaning Tower of Pisa, about 1590. But others about the same time had not 336 overlooked so obvious a factef. Piccolomini, in his Liber Scientiae Natura, published at Padua in 1597, says, "On the subject of the motion of heavy and light bodies, Aristotle has put forth various opinions, which are contrary to sense and experience, and has delivered rules concerning the proportion of quickness and slowness, which are palpably false. For a stone twice as great does not move twice as fast." And Stevinus, in the appendix to his Statics, describes his having made the experiment and speaks with great correctness of the apparent deviations from the rule, arising from the resistance of the air. Indeed, the result followed by very obvious reasoning. For 10 bricks, in contact with each other, side by side, would obviously fall in the same time as one, and these might be conceived to form a body 10 times as large as one of them. Accordingly, Benedetti, in 1585, reasons in this manner with regard to bodies of different size, though he retains Aristotle's error as to the different velocity of bodies of different density. The next step in this subject is more clearly due to Galileo. He discovered the true proportion which the accelerating force of a body falling down an inclined plane bears to the accelerating force of the same body falling freely. This was at first a happy conjecture. It was then confirmed by experiments, and, finally, after some hesitation, it was referred to its true principle, the third law of motion, with proper elementary simplicity. The principle here spoken of is this, that for the same body, the dynamical effect of force is as the statical effect. That is, the velocity which any force generates in a given time when it puts the body in motion is proportional to the pressure which the same force produces in a body at rest. The principle, so stated, appears very simple and obvious, yet this was not the form in which it suggested itself either to Galileo or to other persons who sought to prove it. Galileo, in his Dialogues on Motion, assumes, as his fundamental proposition on this subject, one much less evident than that we have quoted, but one in which that is involved. His postulate is that when the same body falls down different planes of the same height, the velocities acquired are equal. He confirms and illustrates this by a very ingenious experiment on a pendulum, showing that the weight swings to the same height whatever path it be compelled to follow. Torricelli, in his treatise published 1644, says that he had heard that Galileo had, towards the end of his life, proved his 337 assumption, but that not having seen the proof, he will give his own. In this he refers us to the right principle, but appears not distinctly to conceive the proof, since he estimates momentum indiscriminately by the statical pressure of a body, and by its velocity when in motion, as if these two quantities were self-evidently equal. Huygens, in 1673, expresses himself dissatisfied with the proof, by which Galileo's assumption was supported in the later editions of his works. His own proof rests on this principle, that if a body fall down one inclined plane and proceed up another with the velocity thus acquired, it cannot, under any circumstances, ascend to a higher position than that from which it fell. This principle coincides very nearly with Galileo's experimental illustration. In truth, however, Galileo's principle, which Huygens thus slights, may be looked upon as a satisfactory statement of the true law, namely, that in the same body the velocity produced is as the pressure which produces it. We are agreed, he says, that in a movable body the impetus, energy, momentum, or propension to motion is as great as is the force or least resistance which suffices to support it. The various terms here used, both for dynamical and statical force, show that Galileo's ideas were not confused by the ambiguity of any one term, as appears to have happened to some mathematicians. The principle thus announced is, as we shall see, one of great extent and value, and we read with interest the circumstances of its discovery, which are thus narrated. When Viviani was studying with Galileo, he expressed his dissatisfaction at the want of any clear reason for Galileo's postulate respecting the equality of velocities acquired down inclined planes of the same heights. The consequence of which was that Galileo, as he lay, the same night, sleepless through indisposition, discovered the proof which he had long sought in vain, and introduced it in the subsequent editions. It is easy to see, by looking at the proof, that the discoverer had had to struggle, not for intermediate steps of reasoning between remote notions, as in a problem of geometry, but for a clear possession of ideas which were near each other, and which he had not yet been able to bring into contact, because he had not yet a sufficiently firm grasp of them. Such terms as momentum and force had been sources of confusion from the time of Aristotle, and it required considerable steadiness of thought to compare the forces of bodies at rest and in motion under the obscurity and vacillation thus produced. 338. The term momentum had been introduced to express the force of bodies in motion, before it was known what that effect was. Galileo, in his Discorso intorno alle cose che stanno in su l'acqua, says that momentum is the force, efficacy, or virtue, with which the motion moves and the body moved resists, depending not upon weight only, but upon the velocity, inclination, and any other cause of such virtue. When he arrived at more precision in his views, he determined, as we have seen, that, in the same body, the momentum is proportional to the velocity, and hence it was easily seen that in different bodies it was proportional to the velocity and mass jointly. The principle thus enunciated is capable of very extensive application, and, among other consequences, leads to a determination of the results of the mutual percussion of bodies. But though Galileo, like others of his predecessors and contemporaries, had speculated concerning the problem of percussion, he did not arrive at any satisfactory conclusion, and the problem remained for the mathematicians of the next generation to solve. We may here notice Descartes and his laws of motion, the publication of which is sometimes spoken of as an important event in the history of mechanics. This is saying far too much. The Principia of Descartes did little for physical science. His assertion of the laws of motion, in their most general shape, was perhaps an improvement in form, but his third law is false in substance. Descartes claimed several of the discoveries of Galileo and others of his contemporaries, but we cannot assent to such claims when we find that, as we shall see, he did not understand, or would not apply, the laws of motion when he had them before him. If we were to compare Descartes with Galileo, we might say that of the mechanical truths which were easily attainable in the beginning of the 17th century, Galileo took hold of as many, and Descartes of as few, as was well possible for a man of genius. The following remarks of M. Libri appear to be just. After giving an account of the doctrines put forth on the subject of astronomy, mechanics, and other branches of science, by Leonardo da Vinci, Fracastoro, Maurolicus, Commandinus, Benedetti, he adds Hist. Des Sciences Mathématiques en Italie, T. Roman 3. p. 131. This short analysis is sufficient to show that, at the period at which we are arrived, Aristotle no longer reigned unquestioned in the Italian schools. If we had to write the history of philosophy, we should prove by a multitude of facts that it was the Italians who overthrew the ancient idol of philosophers. Men go on incessantly repeating that the 339 struggle was begun by Descartes, and they proclaim him the legislator of modern philosophers. But when we examine the philosophical writings of Fracastoro, of Benedetti, of Cardan, and above all, those of Galileo, when we see on all sides energetic protests raised against the peripatetic doctrines, we ask what there remained for the inventor of vortices to do in overturning the natural philosophy of Aristotle. In addition to this, the memorable labors of the school of Cosenza, of Telesius, of Giordano Bruno, of Campanella, the writings of Patricius, who was, besides, a good geometer, of Nizolius, whom Leibniz esteemed so highly, and of the other metaphysicians of the same epoch, prove that the ancient philosophy had already lost its empire on that side the Alps, when Descartes threw himself upon the enemy now put to the rout. The yoke was cast off in Italy, and all Europe had only to follow the example, without its being necessary to give a new impulse to real science. In England, we are accustomed to hear Francis Bacon, rather than Descartes, spoken of as the first great antagonist of the Aristotelian schools and the legislator of modern philosophy. But it is true, both of one and the other, that the overthrow of the ancient system had been effectively begun before their time by the practical discoverers here mentioned, and others who, by experiment and reasoning, established truths inconsistent with the received Aristotelian doctrines. Gilbert in England, Kepler in Germany, as well as Benedetti and Galileo in Italy, gave a powerful impulse to the cause of real knowledge, before the influence of Bacon and Descartes had produced any general effect. What Bacon really did was this, that by the august image which he presented of a future philosophy, the rival of the Aristotelian, and far more powerful and extensive, he drew to it the affections and hopes of all men of comprehensive and vigorous minds, as well as of those who attended to special trains of discovery. He announced a new method, not merely a correction of special current errors. He thus converted the insurrection into a revolution and established a new philosophical dynasty. Descartes had, in some degree, the same purpose, and in addition to this, he not only proclaimed himself the author of a new method, but professed to give a complete system of the results of the method. His physical philosophy was put forth as complete and demonstrative, and thus involved the vices of the ancient dogmatism. Telesius and Campanella had also grand notions of an entire reform in the method of philosophizing, as I have noticed in the Philosophy of the Inductive Sciences, Book 12. 340. Chapter 3. Sequel to the epoch of Galileo period of verification and deduction. The evidence on which Galileo rested the truth of the laws of motion which he asserted was, as we have seen, the simplicity of the laws themselves and the agreement of their consequences with facts, proper allowances being made for disturbing causes. His successors took up and continued the task of making repeated comparisons of the theory with practice, till no doubt remained of the exactness of the fundamental doctrines. They also employed themselves in simplifying, as much as possible, the mode of stating these doctrines, and in tracing their consequences in various problems by the aid of mathematical reasoning. These employments led to the publication of various treatises on falling bodies, inclined planes, pendulums, projectiles, spouting fluids, which occupied a great part of the 17th century. The authors of these treatises may be considered as the school of Galileo. Several of them were, indeed, his pupils or personal friends. Caselli was his disciple and astronomical assistant at Florence, and afterwards his correspondent. Torricelli was at first a pupil of Caselli, but became the inmate and amanuensis of Galileo in 1641, and succeeded him in his situation at the court of Florence on his death, which took place a few months afterwards. Viviani formed one of his family during the 3 last years of his life, and surviving him and his contemporaries, for Viviani lived even into the 18th century, has a manifest pleasure and pride in calling himself the last of the disciples of Galileo. Gassendi, an eminent French mathematician and professor, visited him in 1628, and it shows us the extent of his reputation when we find Milton referring thus to his travels in Italy. There it was that I found and visited the famous Galileo, grown old, a prisoner in the Inquisition, for thinking in astronomy otherwise than the Franciscan and Dominican licensers thought. Besides the above writers, we may mention, as persons who pursued and illustrated Galileo's doctrines, Borelli, who was professor at Florence and Pisa; Mersenne, the correspondent of Descartes, who was 341 professor at Paris; Wallis, who was appointed Savilian professor at Oxford in 1649, his predecessor being ejected by the parliamentary commissioners. It is not necessary for us to trace the progress of purely mathematical inventions, which constitute a great part of the works of these authors, but a few circumstances may be mentioned. The question of the proof of the second law of motion was, from the first, identified with the controversy respecting the truth of the Copernican system. For this law supplied the true answer to the most formidable of the objections against the motion of the Earth, namely, that if the Earth were moving, bodies which were dropped from an elevated object would be left behind by the place from which they fell. This argument was reproduced in various forms by the opponents of the new doctrine, and the answers to the argument, though they belong to the history of astronomy and form part of the sequel to the Epoch of Copernicus, belong more peculiarly to the history of mechanics and are events in the sequel to the discoveries of Galileo. So far, indeed, as the mechanical controversy was concerned, the advocates of the second law of motion appealed, very triumphantly, to experiment. Gassendi made many experiments on this subject publicly, of which an account is given in his Epistolae 3 de motu impresso a motor translato. It appeared in these experiments that bodies let fall downwards, or cast upwards, forwards, or backwards from a ship or chariot or man, whether at rest or in any degree of motion, had always the same motion relatively to the motor. In the application of this principle to the system of the world, indeed, Gassendi and other philosophers of his time were greatly hampered, for the deference which religious scruples required did not allow them to say that the Earth really moved, but only that the physical reasons against its motion were invalid. This restriction enabled Riccioli and other writers on the geocentric side to involve the subject in metaphysical difficulties. But the conviction of men was not permanently shaken by these, and the second law of motion was soon assumed as unquestioned. The laws of the motion of falling bodies, as assigned by Galileo, were confirmed by the reasonings of Gassendi and Fermat and the experiments of Riccioli and Grimaldi, and the effect of resistance was pointed out by Mersenne and Dichales. The parabolic motion of projectiles was more especially illustrated by experiments on the jet, which spouts from an orifice in a vessel full of fluid. This mode of experimenting, 342, is well adapted to attract notice, since the curve described, which is transient and invisible in the case of a single projectile, becomes permanent and visible when we have a continuous stream. The doctrine of the motions of fluids has always been zealously cultivated by the Italians. Caselli's treatise, Della Misura del Equicorrente, 1638, is the first work on this subject, and Montucla with justice calls him the creator of a new branch of hydraulics, although he mistakenly supposed the velocity of efflux to be as the depth of the orifice from the surface. Mersenne and Torricelli also pursued this subject, and after them, many others. Galileo's belief in the near approximation of the curve described by a cannonball or musket ball to the theoretical parabola was somewhat too obsequiously adopted by succeeding practical writers on artillery. They underrated, as he had done, the effect of the resistance of the air, which is in effect so great as entirely to change the form and properties of the curve. Notwithstanding this, the parabolic theory was employed, as in Anderson's Art of Gunnery, 1674, and Blondel, in his Art de jeter les bombes, 1688, not only calculated tables on this supposition, but attempted to answer the objections which had been made respecting the form of the curve described. It was not till a later period, 1740, when Robbins made a series of careful and sagacious experiments on artillery, and when some of the most eminent mathematicians calculated the curve, taking into account the resistance, that the theory of projectiles could be said to be verified in fact. The third law of motion was still in some confusion when Galileo died, as we have seen. The next great step made in the school of Galileo was the determination of the laws of the motions of bodies in their direct impact, so far as this impact affects the motion of translation. The difficulties of the problem of percussion arose, in part, from the heterogeneous nature of pressure of a body at rest, and momentum of a body in motion, and, in part, from mixing together the effects of percussion on the parts of a body, as, for instance, cutting, bruising, and breaking, with its effect in moving the whole. The former difficulty had been seen with some clearness by Galileo himself. In a posthumous addition to his mechanical dialogues, he says, "There are two kinds of resistance in a movable body, one internal, as when we say it is more difficult to lift a weight of 1,000 pounds than a weight of 100. Another respecting space, as 343, when we say that it requires more force to throw a stone 100 paces than 50. Reasoning upon this difference, he comes to the conclusion that the momentum of percussion is infinite, since there is no resistance, however great, which is not overcome by a force of percussion, however small. He further explains this by observing that the resistance to percussion must occupy some portion of time, although this portion may be insensible. This correct mode of removing the apparent incongruity of continuous and instantaneous force was a material step in the solution of the problem. The laws of the mutual impact of bodies were erroneously given by Descartes in his Principia, and appear to have been first correctly stated by Wren, Wallis, and Huygens, who about the same time, 1669, sent papers to the Royal Society of London on the subject. In these solutions, we perceive that men were gradually coming to apprehend the third law of motion in its most general sense, namely, that the momentum, which is proportional to the mass of the body and its velocity jointly, may be taken for the measure of the effect, so that this momentum is as much diminished in the striking body by the resistance it experiences as it is increased in the body struck by the impact. This was sometimes expressed by saying that the quantity of motion remains unaltered, quantity of motion being used as synonymous with momentum. Newton expressed it by saying that action and reaction are equal and opposite, which is still one of the most familiar modes of expressing the third law of motion. In this mode of stating the law, we see an example of a propensity which has prevailed very generally among mathematicians, namely, a disposition to present the fundamental laws of rest and of motion as if they were equally manifest, and, indeed, identical. The close analogy and connection which exists between the principles of equilibrium and of motion often led men to confound the evidence of the two. And this confusion introduced an ambiguity in the use of words, as we have seen in the case of momentum, force, and others. The same may be said of action and reaction, which have both a statical and a dynamical signification. And by this means, the most general statements of the laws of motion are made to coincide with the most general statical propositions. For instance, Newton deduced from his principles the conclusion that by the mutual action of bodies, the motion of their center of gravity cannot be affected. Marriott, in his Traité de la 344 Percussion, 1684, had asserted this proposition for the case of direct impact. But by the reasoners of Newton's time, the dynamical proposition, that the motion of the center of gravity is not altered by the actual free motion and impact of bodies, was associated with the statical proposition, that when bodies are in equilibrium, the center of gravity cannot be made to ascend or descend by the virtual motions of the bodies. This latter is a proposition which was assumed as self-evident by Torricelli, but which may more philosophically be proved from elementary statical principles. This disposition to identify the elementary laws of equilibrium and of motion led men to think too slightingly of the ancient solid and sufficient foundation of statics, the doctrine of the lever. When the progress of thought had opened men's minds to a more general view of the subject, it was considered as a blemish in the science to found it on the properties of one particular machine. Descartes says in his letters that it is ridiculous to prove the pulley by means of the lever. And Varignon was led by similar reflections to the project of his Nouvelle Mécanique, in which the whole of statics should be founded on the composition of forces. This project was published in 1687, but the work did not appear till 1725, after the death of the author. Though the attempt to reduce the equilibrium of all machines to the composition of forces is philosophical and meritorious, the attempt to reduce the composition of pressures to the composition of motions, with which Varignon's work is occupied, was a retrograde step in the subject, so far as the progress of distinct mechanical ideas was concerned. Thus, at the period at which we have now arrived, the principles of elementary mechanics were generally known and accepted, and there was in the minds of mathematicians a prevalent tendency to reduce them to the most simple and comprehensive form of which they admitted. The execution of this simplification and extension which we term the generalization of the laws, is so important an event that though it forms part of the natural sequel of Galileo, we shall treat of it in a separate chapter. But we must first bring up the history of the mechanics of fluids to the corresponding point. 345. Chapter 4. Discovery of the mechanical principles of fluids. Sect 1. Rediscovery of the laws of equilibrium of fluids. We have already said that the true laws of the equilibrium of fluids were discovered by Archimedes and rediscovered by Galileo and Stevinus, the intermediate time having been occupied by a vagueness and confusion of thought on physical subjects, which made it impossible for men to retain such clear views as Archimedes had disclosed. Stevinus must be considered as the earliest of the authors of this rediscovery, for his work, Principles of Static and Hydrostatic, was published in Dutch about 1585, and in this, his views are perfectly distinct and correct. He restates the doctrines of Archimedes and shows that, as a consequence of them, it follows that the pressure of a fluid on the bottom of a vessel may be much greater than the weight of the fluid itself. This he proves by imagining some of the upper portions of the vessel to be filled with fixed solid bodies, which take the place of the fluid, and yet do not alter the pressure on the base. He also shows what will be the pressure on any portion of a base in an oblique position, and hence, by certain mathematical artifices which make an approach to the infinitesimal calculus, he finds the whole pressure on the base in such cases. This mode of treating the subject would take in a large portion of our elementary hydrostatics as the science now stands. Galileo saw the properties of fluids no less clearly, and explained them very distinctly in 1612 in his discourse on floating bodies. It had been maintained by the Aristotelians that form was the cause of bodies floating, and collaterally that ice was condensed water, apparently from a confusion of thought between rigidity and density. Galileo asserted, on the contrary, that ice is rarefied water, as appears by its floating, and in support of this, he proved, by various experiments, that the floating of bodies does not depend on their form. The happy genius of Galileo is the more remarkable in this case, as the controversy was a good deal perplexed by the mixture of phenomena of another kind, due to what is usually called capillary or molecular attraction. Thus it is a fact that a ball 346 of ebony sinks in water, while a flat slip of the same material lies on the surface, and it required considerable sagacity to separate such cases from the general rule. Galileo's opinions were attacked by various writers, as Nozzolini, Vincenzio di Grazia, Ludovico del Collam, and defended by his pupil Caselli, who published a reply in 1615. These opinions were generally adopted and diffused, but somewhat later, Pascal pursued the subject more systematically and wrote his treatise of the equilibrium of fluids in 1653, in which he shows that a fluid enclosed in a vessel necessarily presses equally in all directions by imagining two pistons or sliding plugs, applied at different parts, the surface of one being centuple that of the other. It is clear, as he observes, that the force of one man acting at the first piston will balance the force of 100 men acting at the other. And thus, says he, it appears that a vessel full of water is a new principle of mechanics, and a new machine which will multiply force to any degree we choose. Pascal also referred the equilibrium of fluids to the principle of virtual velocities, which regulates the equilibrium of other machines. This, indeed, Galileo had done before him. It followed from this doctrine that the pressure which is exercised by the lower parts of a fluid arises from the weight of the upper parts. In all this there was nothing which was not easily assented to, but the extension of these doctrines to the air required an additional effort of mechanical conception. The pressure of the air on all sides of us and its weight above us were two truths which had never yet been apprehended with any kind of clearness. Seneca, indeed, talks of the gravity of the air, and of its power of diffusing itself when condensed as the causes of wind, but we can hardly consider such propriety of phraseology in him as more than a chance, for we see the value of his philosophy by what he immediately adds. Do you think that we have forces by which we move ourselves, and that the air is left without any power of moving, when even water has a motion of its own, as we see in the growth of plants? We can hardly attach much value to such a recognition of the gravity and elasticity of the air. Yet the effects of these causes were so numerous and obvious that the Aristotelians had been obliged to invent a principle to account for them, namely, nature's horror of a vacuum. To this principle were referred many familiar phenomena, as suction, breathing, the 347 action of a pair of bellows, its drawing water if immersed in water, its refusing to open when the rent is stopped up. The action of a cupping instrument in which the air is rarefied by fire. The fact that water is supported when a full inverted bottle is placed in a basin, or when a full tube, open below and closed above, is similarly placed. The running out of the water, in this instance, when the top is opened. The action of a siphon, of a syringe, of a pump, the adhesion of two polished plates, and other facts were all explained by the fuga vacui. Indeed, we must contend that the principle was a very good one, inasmuch as it brought together all these facts which are really of the same kind, and referred them to a common cause. But when urged as an ultimate principle, it was not only unphilosophical, but imperfect and wrong. It was unphilosophical because it introduced the notion of an emotion horror as an account of physical facts. It was imperfect because it was at best only a law of phenomena, not pointing out any physical cause, and it was wrong because it gave an unlimited extent to the effect. Accordingly, it led to mistakes. Thus Mersenne, in 1644, speaks of a siphon which shall go over a mountain, being ignorant then that the effect of such an instrument was limited to a height of 34 feet. A few years later, however, he had detected this mistake, and in his third volume, published in 1647, he puts his siphon in his emendanda, and speaks correctly of the weight of air as supporting the mercury in the tube of Torricelli. It was, indeed, by finding this horror of a vacuum to have a limit at the height of 34 feet that the true principle was suggested. It was discovered that when attempts were made to raise water higher than this, nature tolerated a vacuum above the water which rose. In 1643, Torricelli tried to produce this vacuum at a smaller height by using, instead of water, the heavier fluid, quicksilver, an attempt which shows that the true explanation, the balance of the weight of the water by another pressure, had already suggested itself. Indeed, this appears from other evidence. Galileo had already taught that the air has weight, and Baglioni, writing to him in 1630, says, "If we were in a vacuum, the weight of the air above our heads would be felt." Descartes also appears to have some share in this discovery, for in a letter of the date of 1631, he explains the suspension of mercury in a tube, closed at top, by the pressure of the column of air reaching to the clouds. 348. Still men's minds wanted confirmation in this view, and they found such confirmation when, in 1647, Pascal showed practically that if we alter the length of the superincumbent column of air by going to a high place, we alter the weight which it will support. This celebrated experiment was made by Pascal himself on a church steeple in Paris, the column of mercury in the Torricellian tube being used to compare the weights of the air. But he wrote to his brother-in-law, who lived near the high mountain of Puy de Dôme in Auvergne, to request him to make the experiment there, where the result would be more decisive. "You see," he says, "that if it happens that the height of the mercury at the top of the hill be less than at the bottom, which I have many reasons to believe, though all those who have thought about it are of a different opinion, it will follow that the weight and pressure of the air are the sole cause of this suspension, and not the horror of a vacuum, since it is very certain that there is more air to weigh on it at the bottom than at the top, while we cannot say that nature abhors a vacuum at the foot of a mountain more than on its summit." M. Perrier, Pascal's correspondent, made the observation as he had desired, and found a difference of 3 inches of mercury, which, he says, ravished us with admiration and astonishment. When the least obvious case of the operation of the pressure and weight of fluids had thus been made out, there were no further difficulties in the progress of the theory of hydrostatics. When mathematicians began to consider more general cases than those of the action of gravity, there arose differences in the way of stating the appropriate principles. But none of these differences imply any different conception of the fundamental nature of fluid equilibrium. Sect 2. Discovery of the laws of motion of fluids. The art of conducting water in pipes and of directing its motion for various purposes is very old. When treated systematically, it has been termed hydraulics, but hydrodynamics is the general name of the science of the laws of the motions of fluids under those or other circumstances. The art is as old as the commencement of civilization. The science does not ascend higher than the time of Newton, though attempts on such subjects were made by Galileo and his scholars. When a fluid spouts from an orifice in a vessel, Caselli saw that the velocity of efflux depends on the depth of the orifice below the 349 surface, but he erroneously judged the velocity to be exactly proportional to the depth. Torricelli found that the fluid, under the inevitable causes of defect which occur in the experiment, would spout nearly to the height of the surface. He therefore inferred that the full velocity is that which a body would acquire in falling through the depth, and that it is consequently proportional to the square root of the depth. This, however, he stated only as a result of experience or law of phenomena at the end of his treatise, De Motu Naturaliter Accelerado, printed in 1643. Newton treated the subject theoretically in the Principia, 1687, but we must allow, as Lagrange says, that this is the least satisfactory passage of that great work. Newton, having made his experiments in another manner than Torricelli, namely, by measuring the quantity of the efflux instead of its velocity, found a result inconsistent with that of Torricelli. The velocity inferred from the quantity discharged was only that due to half the depth of the fluid. In the first edition of the Principia, Newton gave a train of reasoning by which he theoretically demonstrated his own result, going upon the principle that the momentum of the issuing fluid is equal to the momentum which the column vertically over the orifice would generate by its gravity. But Torricelli's experiments, which had given the velocity due to the whole depth, were confirmed on repetition. How was this discrepancy to be explained? Newton explained the discrepancy by observing the contraction which the jet, or vein of water, undergoes just after it leaves the orifice, and which he called the vena contracta. At the orifice, the velocity is that due to half the height; at the vena contracta it is that due to the whole height. The former velocity regulates the quantity of the discharge, the latter, the path of the jet. This explanation was an important step in the subject, but it made Newton's original proof appear very defective, to say the least. In the second edition of the Principia, 1714, Newton attacked the problem in a manner altogether different from his former investigation. He there assumed that when a round vessel containing fluid has a hole in its bottom, the descending fluid may be conceived to be a conoidal mass, which has its base at the surface of the fluid and its narrow end at the orifice. This portion of the fluid he calls the cataract, and supposes that while this part descends, the surrounding 350 parts remain immovable, as if they were frozen. In this way, he finds a result agreeing with Torricelli's experiments on the velocity of the efflux. We must allow that the assumptions by which this result is obtained are somewhat arbitrary, and those which Newton introduces in attempting to connect the problem of issuing fluids with that of the resistance to a body moving in a fluid are no less so. But even up to the present time, mathematicians have not been able to reduce problems concerning the motions of fluids to mathematical principles and calculations without introducing some steps of this arbitrary kind. And one of the uses of experiments on this subject is to suggest those hypotheses which may enable us, in the manner most consonant with the true state of things, to reduce the motions of fluids to those general laws of mechanics, to which we know they must be subject. Hence the science of the motion of fluids, unlike all the other primary departments of mechanics, is a subject on which we still need experiments to point out the fundamental principles. Many such experiments have been made, with a view either to compare the results of deduction and observation, or, when this comparison failed, to obtain purely empirical rules. In this way, the resistance of fluids and the motion of water in pipes, canals, and rivers has been treated. Italy has possessed from early times a large body of such writers. The earlier works of this kind have been collected in 16 quarto volumes. Leccai and Michelotti about 1765, by Doan more recently, have pursued these inquiries. Bossut, Buet, Hachette, in France, have labored at the same task, as have Coulomb and Prony, Gerard and Poncelet. Idelween's German treatise, Hydraulic, contains an account of what others and himself have done. Many of these trains of experiments, both in France and Italy, were made at the expense of governments, and on a very magnificent scale. In England, less was done in this way during the last century than in most other countries. The Philosophical Transactions, for instance, scarcely contain a single paper on this subject founded on experimental investigations. Dr. Thomas Young, who was at the head of his countrymen in so many branches of science, was one of the first to call back attention to this. And Mr. Rennie and others have recently made valuable experiments. In many of the questions now spoken of, the accordance which engineers are able to obtain between their calculated and observed results, 351, is very great. But these calculations are performed by means of empirical formulae, which do not connect the facts with their causes and still leave a wide space to be traversed in order to complete the science. In the meantime, all the other portions of mechanics were reduced to general laws and analytical processes, and means were found of including hydrodynamics, notwithstanding the difficulties which attend its special problems, in this common improvement of form. This progress we must relate. The hydrodynamical problems referred to above are the laws of a fluid issuing from a vessel, the laws of the motion of water in pipes, canals, and rivers, and the laws of the resistance of fluids. To these may be added, as an hydrodynamical problem important in theory, in experiment, and in the comparison of the two, the laws of waves. Newton gave in the Principia an explanation of the waves of water, Lib Roman 2. Prop 44, which appears to proceed upon an erroneous view of the nature of the motion of the fluid, but in his solution of the problem of sound, appeared, for the first time, a correct view of the propagation of an undulation in a fluid. The history of this subject, as bearing upon the theory of sound, is given in Book 8. But I may here remark that the laws of the motion of waves have been pursued experimentally by various persons, as Bremontier recherches sur le mouvement des ondes, 1809, Mi du mouvement des ondes, 1831, the Webers Wellenlayer, 1825, and by Mr. Scott Russell, Reports of the British Association, 1844. The analytical theory has been carried on by Poisson, Cauchy, and among ourselves by Prof. Kelland Eden. Trans and Mr. Airy in the article Tides in the Encyclopedia Metropolitana. And though theory and experiment have not yet been brought into complete accordance, great progress has been made in that work, and the remaining chasm between the two is manifestly due only to the incompleteness of both. Perhaps the most remarkable case of fluid motion recently discussed is one which Mr. Scott Russell has presented experimentally, and which, though novel, is easily seen to follow from known principles, namely, the great solitary wave. A wave may be produced, which shall move along a canal unaccompanied by any other wave, and the simplicity of this case makes the mathematical conditions and consequences more simple than they are in most other problems of hydrodynamics. 352. Chapter 5. Generalization of the principles of mechanics. Sect 1. Generalization of the second law of motion, central forces. The second law of motion being proved for constant forces which act in parallel lines, and the third law for the direct action of bodies, it still required great mathematical talent and some inductive power to see clearly the laws which govern the motion of any number of bodies, acted upon by each other, and by any forces anyhow varying in magnitude and direction. This was the task of the generalization of the laws of motion. Galileo had convinced himself that the velocity of projection and that which gravity alone would produce are both maintained without being altered, perturbed, or impeded in their mixture. It is to be observed, however, that the truth of this result depends upon a particular circumstance, namely, that gravity at all points acts in lines which, as to sense, are parallel. When we have to consider cases in which this is not true, as when the force tends to the center of a circle, the law of composition cannot be applied in the same way. And, in this case, mathematicians were met by some peculiar difficulties. One of these difficulties arises from the apparent inconsistency of the statical and dynamical measures of force. When a body moves in a circle, the force which urges the body to the center is only a tendency to motion, for the body does not, in fact, approach to the center, and this mere tendency to motion is combined with an actual motion, which takes place in the circumference. We appear to have to compare two things which are heterogeneous. Descartes had noticed this difficulty, but without giving any satisfactory solution of it. If we combine the actual motion to or from the center with the transverse motion about the center, we obtain a result which is false on mechanical principles. Galileo endeavored in this way to find the curve described by a body which falls towards the Earth's center, and is, at the same time, carried 353 round by the motion of the Earth, and obtained an erroneous result. Kepler and Fermat attempted the same problem, and obtained solutions different from that of Galileo, but not more correct. Even Newton, at an early period of his speculations, had an erroneous opinion respecting this curve, which he imagined to be a kind of spiral. Hooke animadverted upon this opinion when it was laid before the Royal Society of London in 1679, and stated, more truly, that supposing no resistance, it would be an eccentric ellipsoid. That is, a figure resembling an ellipse. But though he had made out the approximate form of the curve, in some unexplained way, we have no reason to believe that he possessed any means of determining the mathematical properties of the curve described in such a case. The perpetual composition of a central force with the previous motion of the body could not be successfully treated without the consideration of the doctrine of limits or something equivalent to that doctrine. The first example which we have of the right solution of such a problem occurs, so far as I know, in the theorems of Huygens concerning circular motion, which were published, without demonstration, at the end of his Horologium Oscillatorium in 1673. It was there asserted that when equal bodies describe circles, if the times are equal, the centrifugal forces will be as the diameters of the circles. If the velocities are equal, the forces will be reciprocally as the diameters, and so on. In order to arrive at these propositions, Huygens must, virtually at least, have applied the second law of motion to the limiting elements of the curve, according to the way in which Newton, a few years later, gave the demonstration of the theorems of Huygens in the Principia. The growing persuasion that the motions of the heavenly bodies about the sun might be explained by the action of central forces gave a peculiar interest to these mechanical speculations at the period now under review. Indeed, it is not easy to state separately, as our present object requires us to do, the progress of mechanics and the progress of astronomy. Yet the distinction which we have to make is, in its nature, sufficiently marked. It is, in fact, no less marked than the distinction between speaking logically and speaking truly. The framers of the science of motion were employed in establishing those notions, names, and rules, in conformity to which all mechanical truth must be expressed. But what was the truth with regard to the mechanism of the universe remained to be determined by other means. Physical astronomy, at the period of which we speak, eclipsed and overlaid 354 theoretical mechanics, as, a little previously, dynamics had eclipsed and superseded statics. The laws of variable force and of curvilinear motion were not much pursued, till the invention of fluxions and of the differential calculus again turned men's minds to these subjects, as easy and interesting exercises of the powers of these new methods. Newton's Principia, of which the first two books are purely dynamical, is the great exception to this assertion, inasmuch as it contains correct solutions of a great variety of the most general problems of the science, and indeed is, even yet, one of the most complete treatises which we possess upon the subject. We have seen that Kepler, in his attempts to explain the curvilinear motions of the planets by means of a central force, failed in consequence of his belief that a continued transverse action of the central body was requisite to keep up a continual motion. Galileo had founded his theory of projectiles on the principle that such an action was not necessary. Yet Borelli, a pupil of Galileo, when in 1666 he published his theory of the Medicean stars, the satellites of Jupiter, did not keep quite clear of the same errors which had vitiated Kepler's reasonings. In the same way, though Descartes is sometimes spoken of as the first promulgator of the first law of motion, yet his theory of vortices must have been mainly suggested by a want of an entire confidence in that law. When he represented the planets and satellites as owing their motions to oceans of fluid diffused through the celestial spaces, and constantly whirling round the central bodies, he must have felt afraid of trusting the planets to the operation of the laws of motion in free space. Sounder physical philosophers, however, began to perceive the real nature of the question. As early as 1666, we read, in the journals of the Royal Society, that there was read a paper of Mr. Hooke's explicating the inflection of a direct motion into a curve by a supervening attractive principle. And before the publication of the Principia in 1687, Huygens, as we have seen in Holland and in our own country, Wren, Halley, and Hooke, had made some progress in the true mechanics of circular motion, and had distinctly contemplated the problem of the motion of a body in an ellipse by a central force, though they could not solve it. Halley went to Cambridge in 1684 for the express purpose of consulting Newton upon the subject of the production of the elliptical motion of the planets by means of a central 355 force, and, on the 10th of December, announced to the Royal Society that he had seen Mr. Newton's book, De Motu Corporum. The feeling that mathematicians were on the brink of discoveries, such as are contained in this work, was so strong that Dr. Halley was requested to remind Mr. Newton of his promise of entering them in the register of the Society, for securing the invention to himself till such time as he can be at leisure to publish it. The manuscript, with the title Philosophiae Naturalis Principia Mathematica, was presented to the Society, to which it was dedicated, on the 28th of April, 1686. Dr. Vincent, who presented it, spoke of the novelty and dignity of the subject, and the president, Sir J. Hoskins, added, with great truth, that the method was so much the more to be prized as it was both invented and perfected at the same time. The reader will recollect that we are here speaking of the Principia as a mechanical treatise only. We shall afterwards have to consider it as containing the greatest discoveries of physical astronomy. As a work on dynamics, its merit is that it exhibits a wonderful store of refined and beautiful mathematical artifices applied to solve all the most general problems which the subject offered. The Principia can hardly be said to contain any new inductive discovery respecting the principles of mechanics, for though Newton's axioms or laws of motion, which stand at the beginning of the book, are a much clearer and more general statement of the grounds of mechanics than had yet appeared, they do not involve any doctrines which had not been previously stated or taken for granted by other mathematicians. The work, however, besides its unrivaled mathematical skill, employed in tracing out, deductively, the consequences of the laws of motion, and its great cosmical discoveries, which we shall hereafter treat of, had great philosophical value in the history of dynamics, as exhibiting a clear conception of the new character and functions of that science. In his preface, Newton says, "Rational mechanics must be the science of the motions which result from any forces, and of the forces which are required for any motions, accurately propounded and demonstrated. For many things induce me to suspect that all natural phenomena may depend upon some forces by which the particles of bodies are either drawn towards each other, and cohere, or repel and recede from each other. And these forces being hitherto unknown, philosophers have pursued their researches in vain. And I hope, 356, that the principles expounded in this work will afford some light, either to this mode of philosophizing or to some mode which is more true. Before we pursue this subject further, we must trace the remainder of the history of the third law. Sect 2. Generalization of the third law of motion center of oscillation, Huygens. The third law of motion, whether expressed according to Newton's formula, by the equality of action and reaction, or in any other of the ways employed about the same time, easily gave the solution of mechanical problems in all cases of direct action. That is, when each body acted directly on others. But there still remain the problems in which the action is indirect, when bodies in motion act on each other by the intervention of levers or in any other way. If a rigid rod, passing through two weights, be made to swing about its upper point, so as to form a pendulum, each weight will act and react on the other by means of the rod, considered as a lever turning about the point of suspension. What, in this case, will be the effect of this action and reaction? In what time will the pendulum oscillate by the force of gravity? Where is the point at which a single weight must be placed to oscillate in the same time? In other words, where is the center of oscillation? Such was the problem and example only of the general problem of indirect action which mathematicians had to solve. That it was by no means easy to see in what manner the law of the communication of motion was to be extended from simpler cases to those where rotatory motion was produced, is shown by this, that Newton, in attempting to solve the mechanical problem of the precession of the equinoxes, fell into a serious error on this very subject. He assumed that, when a part has to communicate rotatory movement to the whole, as the protuberant portion of the terrestrial spheroid, attracted by the sun and moon, communicates a small movement to the whole mass of the Earth. The quantity of the motion, modus, will not be altered by being communicated. This principle is true if by motion we understand what is called moment of inertia, a quantity in which both the velocity of each particle and its distance from the axis of rotation are taken into account. But Newton, in his calculations of its amount, considered the velocity only, thus making motion, in this case, identical with the momentum which he introduces in treating of the simpler case, 357, of the third law of motion, when the action is direct. This error was retained even in the later editions of the Principia. The question of the center of oscillation had been proposed by Mersenne somewhat earlier, in 1646. And though the problem was out of the reach of any principles at that time known and understood, some of the mathematicians of the day had rightly solved some cases of it by proceeding as if the question had been to find the center of percussion. The center of percussion is the point about which the momenta of all the parts of a body balance each other when it is in motion about any axis, and is stopped by striking against an obstacle placed at that center. Roberval found this point in some easy cases. Descartes also attempted the problem. Their rival labors led to an angry controversy. And Descartes was, as in his physical speculations he often was, very presumptuous, though not more than half right. Huygens was hardly advanced beyond boyhood when Mersenne first proposed this problem, and, as he says, could see no principle which even offered an opening to the solution, and had thus been repelled at the threshold. When, however, he published his Horologium Oscillatorium in 1673, the fourth part of that work was on the center of oscillation or agitation. And the principle which he then assumed, though not so simple and self-evident as those to which such problems were afterwards referred, was perfectly correct and general, and led to exact solutions in all cases. The reader has already seen repeatedly in the course of this history complex and derivative principles presenting themselves to men's minds before simple and elementary ones. The hypothesis assumed by Huygens was this: that if any weights are put in motion by the force of gravity, they cannot move so that the center of gravity of them all shall rise higher than the place from which it descended. This being assumed, it is easy to show that the center of gravity will, under all circumstances, rise as high as its original position, and this consideration leads to a determination of the oscillation of a compound pendulum. We may observe, in the principle thus selected, a conviction that, in all mechanical action, the center of gravity may be taken as the representative of the whole system. This conviction, as we have seen, may be traced in the axioms of Archimedes and Stevinus, and Huygens, when he proceeds upon it, undertakes to show that he assumes only this, that a heavy body cannot, of itself, move upwards. 358. Clear as Huygens' principle appeared to himself, it was, after some time, attacked by the Abbé Catalan, a zealous Cartesian. Catalan also put forth principles which he conceived were evident, and deduced from them conclusions contradictory to those of Huygens. His principles, now that we know them to be false, appear to us very gratuitous. They are these: that in a compound pendulum, the sum of the velocities of the component weights is equal to the sum of the velocities which they would have acquired if they had been detached pendulums, and that the time of the vibration of a compound pendulum is an arithmetic mean between the times of the vibrations of the weights, moving as detached pendulums. Huygens easily showed that these suppositions would make the center of gravity ascend to a greater height than that from which it fell, and after some time, James Bernoulli stepped into the arena and ranged himself on the side of Huygens. As the discussion thus proceeded, it began to be seen that the question really was, in what manner the third law of motion was to be extended to cases of indirect action, whether by distributing the action and reaction according to statical principles, or in some other way. I propose it to the consideration of mathematicians, says Bernoulli in 1686. What law of the communication of velocity is observed by bodies in motion, which are sustained at one extremity by a fixed fulcrum, and at the other by a body also moving, but more slowly? is the excess of velocity, which must be communicated from the one body to the other to be distributed in the same proportion in which a load supported on the lever would be distributed. He adds that if this question be answered in the affirmative, Huygens will be found to be in error. But this is a mistake. The principle that the action and reaction of bodies thus moving are to be distributed according to the rules of the lever is true, but Bernoulli mistook in estimating this action and reaction by the velocity acquired at any moment, instead of taking, as he should have done, the increment of velocity which gravity tended to impress in the next instant. This was shown by the Marquis de L'Hopital, who adds with justice, "I conceive that I have thus fully answered the call of Bernoulli when he says, I propose it to the consideration of mathematicians, and see." We may, from this time, consider as known, but not as fully established, the principle that, when bodies in motion affect each other, the action and reaction are distributed according to the laws of statics. Although there were still found occasional difficulties in the 359 generalization and application of the rule. James Bernoulli, in 1703, gave a general demonstration of the center of oscillation, drawn from the nature of the lever. In this demonstration, he takes as a fundamental principle that bodies in motion, connected by levers, balance when the products of their momenta and the lengths of the levers are equal in opposite directions. For the proof of this proposition, he refers to Marriott, who had asserted it of weights acting by percussion, and in order to prove it, had balanced the effect of a weight on a lever by the effect of a jet of water, and had confirmed it by other experiments. Moreover, says Bernoulli, there is no one who denies it. Still, this kind of proof was hardly satisfactory or elementary enough. John Bernoulli took up the subject after the death of his brother James, which happened in 1705. The former published in 1714 his Meditatio de Natura Centri Oscillationis. In this memoir, he assumes, as his brother had done, that the effects of forces on a lever in motion are distributed according to the common rules of the lever. The principal generalization which he introduced was that he considered gravity as a force soliciting to motion, which might have different intensities in different bodies. At the same time, Brooke Taylor in England solved the problem, upon the same principles as Bernoulli. And the question of priority on this subject was one point in the angry intercourse which, about this time, became common between the English mathematicians and those of the continent. Hermann also, in his Phoronomia, published in 1716, gave a proof which, as he informs us, he had devised before he saw John Bernoulli's. This proof is founded on the statical equivalence of the solicitations of gravity and the vicarious solicitations, which correspond to the actual motion of each part, or, as it has been expressed by more modern writers, the equilibrium of the impressed and effective forces. It was shown by John Bernoulli and Hermann, and was indeed easily proved, that the proposition assumed by Huygens as the foundation of his solution was, in fact, a consequence of the elementary principles which belong to this branch of mechanics. But this assumption of Huygens was an example of a more general proposition, which by some mathematicians at this time had been put forward as an original and elementary law, and as a principle which ought to supersede the usual measure of the forces of bodies in motion. This principle they called the conservation of vis viva. The attempt to 360 make this change was the commencement of one of the most obstinate and curious of the controversies which form part of the history of mechanical science. The celebrated Leibniz was the author of the new opinion. In 1686, he published, in the Leipzig Acts, a short demonstration of a memorable error of Descartes and others, concerning the natural law by which they think that God always preserves the same quantity of motion, in which they pervert mechanics. The principle that the same quantity of motion, and therefore of moving force, is always preserved in the world, follows from the equality of action and reaction, though Descartes had, after his fashion, given a theological reason for it. Leibniz allowed that the quantity of moving force remains always the same, but denied that this force is measured by the quantity of motion or momentum. He maintained that the same force is requisite to raise a weight of 1 pound through 4 feet, and a weight of 4 pounds through 1 foot, though the momenta in this case are as 1 to 2. This was answered by the Abbé de Conti, who truly observed that allowing the effects in the two cases to be equal, this did not prove the forces to be equal. Since the effect, in the first case, was produced in a double time, and therefore it was quite consistent to suppose the force only half as great. Leibniz, however, persisted in his innovation, and in 1695 laid down the distinction between vires mortui, or pressures, and vires vivi, the name he gave to his own measure of force. He kept up a correspondence with John Bernoulli, whom he converted to his peculiar opinions on this subject, or rather, as Bernoulli says, made him think for himself, which ended in his proving directly that which Leibniz had defended by indirect reasons. Among other arguments, he had pretended to show, what is certainly not true, that if the common measure of forces be adhered to, a perpetual motion would be possible. It is easy to collect many cases which admit of being very simply and conveniently reasoned upon by means of the vis viva, that is, by taking the force to be proportional to the square of the velocity, and not to the velocity itself. Thus, in order to give the arrow twice the velocity, the bow must be 4 times as strong. And in all cases in which no account is taken of the time of producing the effect, we may conveniently use similar methods. But it was not till a later period that the question excited any general notice. The Academy of Sciences of Paris in 1724 proposed, 361, as a subject for their prize dissertation, the laws of the impact of bodies. Bernoulli, as a competitor, wrote a treatise upon Leibnizian principles, which, though not honored with the prize, was printed by the Academy with commendation. The opinions which he here defended and illustrated were adopted by several mathematicians. The controversy extended from the mathematical to the literary world, at that time more attentive than usual to mathematical disputes, in consequence of the great struggle then going on between the Cartesian and the Newtonian system. It was, however, obvious that by this time the interest of the question, so far as the progress of dynamics was concerned, was at an end, for the combatants all agreed as to the results in each particular case. The laws of motion were now established, and the question was, by means of what definitions and abstractions could they be best expressed, a metaphysical, not a physical discussion, and therefore one in which the paper philosophers, as Galileo called them, could bear a part. In the first volume of the Transactions of the Academy of St. Petersburg, published in 1728, there are 3 Leibnizian memoirs by Hermann, Bulfinger, and Wolff. In England, Clarke was an angry assailant of the German opinion, which Esgravesand maintained. In France, Marin attacked the vis viva in 1728, with strong and victorious reasons, as the Marquise du Châtelet declared in the first edition of her treatise on fire. But shortly after this praise was published, the Château de Sillery, where the Marquise usually lived, became a school of Leibnizian opinions and the resort of the principal partisans of the vis viva. Soon, observes Marin, their language was changed. The vis viva was enthroned by the side of the monads. The Marquise tried to retract or explain away her praises. She urged arguments on the other side. Still, the question was not decided. Even her friend Voltaire was not converted. In 1741, he read a memoir on the measure and nature of moving forces, in which he maintained the old opinion. Finally, D'Alembert in 1743 declared it to be, as it truly was, a mere question of words, and by the turn which dynamics then took, it ceased to be of any possible interest or importance to mathematicians. The representation of the laws of motion and of the reasonings depending on them, in the most general form, by means of analytical language, cannot be said to have been fully achieved till the time of D'Alembert. But as we have already seen, the discovery of these laws, 362, had taken place somewhat earlier. And that law which is more particularly expressed in D'Alembert's principle, the equality of the action gained and lost, was, it has been seen, rather led to by the general current of the reasoning of mathematicians about the end of the 17th century than discovered by anyone. Huygens, Marriott, the 2 Bernoullis, L. Hospital, Taylor, and Hermann have each of them their name in the history of this advance. But we cannot ascribe to any of them any great real inductive sagacity shown in what they thus contributed, except to Huygens, who first seized the principle in such a form as to find the center of oscillation by means of it. Indeed, in the steps taken by the others, language itself had almost made the generalization for them at the time when they wrote, and it required no small degree of acuteness and care to distinguish the old cases, in which the law had already been applied, from the new cases, in which they had to apply it. Chapter 6. Sequel to the generalization of the principles of mechanics, period of mathematical deduction analytical mechanics. We have now finished the history of the discovery of mechanical principles, strictly so called. The three laws of motion, generalized in the manner we have described, contain the materials of the whole structure of mechanics, and in the remaining progress of the science, we are led to no new truth which was not implicitly involved in those previously known. It may be thought, therefore, that the narrative of this progress is of comparatively small interest. Nor do we maintain that the application and development of principles is a matter of so much importance to the philosophy of science as the advance towards and to them. Still, there are many circumstances in the latter stages of the progress of the science of mechanics which well deserve notice and make a rapid survey of that part of its history indispensable to our purpose. The laws of motion are expressed in terms of space and number. The development of the consequences of these laws must, therefore, be performed by means of the reasonings of mathematics, and the science, 363, of mechanics may assume the various aspects which belong to the different modes of dealing with mathematical quantities. Mechanics, like pure mathematics, may be geometrical or may be analytical. That is, it may treat space either by a direct consideration of its properties or by a symbolical representation of them. Mechanics, like pure mathematics, may proceed from special cases to problems and methods of extreme generality, may summon to its aid the curious and refined relations of symmetry, by which general and complex conditions are simplified, may become more powerful by the discovery of more powerful analytical artifices, may even have the generality of its principles further expanded, inasmuch as symbols are a more general language than words. We shall very briefly notice a series of modifications of this kind. 1. Geometrical mechanics. Newton, and see the first great systematical treatise on mechanics in the most general sense, is the two first books of the Principia of Newton. In this work, the method employed is predominantly geometrical. Not only space is not represented symbolically or by reference to number, but numbers, as for instance, those which measure time and force, are represented by spaces, and the laws of their changes are indicated by the properties of curve lines. It is well known that Newton employed, by preference, methods of this kind in the exposition of his theorems, even where he had made the discovery of them by analytical calculations. The intuitions of space appeared to him, as they have appeared to many of his followers, to be a more clear and satisfactory road to knowledge than the operations of symbolical language. Hermann, whose Phoronomia was the next great work on this subject, pursued a like course, employing curves which he calls the scale of velocities, of forces, and C methods nearly similar were employed by the two first Bernoullis and other mathematicians of that period, and were indeed so long familiar that the influence of them may still be traced in some of the terms which are used on such subjects. As, for instance, when we talk of reducing a problem to quadratures, that is, to the finding the area of the curves employed in these methods. 2. Analytical mechanics. Euler. As analysis was more cultivated, it gained a predominancy over geometry, being found to be a far more powerful instrument for obtaining results, and possessing a beauty and an evidence which, though different from those of geometry, had great attractions for minds to which they became familiar. The person who did most to give to analysis the generality and 364 symmetry which are now its pride, was also the person who made mechanics analytical, I mean Euler. He began his execution of this task in various memoirs, which appeared in the Transactions of the Academy of Sciences at St. Petersburg, commencing with its earliest volumes. And in 1736, he published there his Mechanics, or the Science of Motion analytically expounded, in the way of a supplement to the Transactions of the Imperial Academy of Sciences. In the preface to this work, he says that though the solutions of problems by Newton and Hermann were quite satisfactory, yet he found that he had a difficulty in applying them to new problems, differing little from theirs, and that, therefore, he thought it would be useful to extract an analysis out of their synthesis. 3. Mechanical problems in reality, however, Euler has done much more than merely give analytical methods, which may be applied to mechanical problems. He has himself applied such methods to an immense number of cases. His transcendent mathematical powers, his long and studious life, and the interest with which he pursued the subject led him to solve an almost inconceivable number and variety of mechanical problems. Such problems suggested themselves to him on all occasions. One of his memoirs begins by stating that, happening to think of the line of Virgil, "Ancora deprora jaceter stant litter pups," the anchor drops, the rushing keel is stayed. He could not help inquiring what would be the nature of the ship's motion under the circumstances here described. And in the last few days of his life, after his mortal illness had begun, having seen in the newspapers some statements respecting balloons, he proceeded to calculate their motions, and performed a difficult integration in which this undertaking engaged him. His memoirs occupy a very large portion of the Petropolitan transactions during his life, from 1728 to 1783, and he declared that he should leave papers which might enrich the publications of the Academy of Petersburg for 20 years after his death, a promise which has been more than fulfilled. For up to 1818, the volumes usually contain several memoirs of his. He and his contemporaries may be said to have exhausted the subject, for there are few mechanical problems which have been since treated, which they have not in some manner touched upon. I do not dwell upon the details of such problems. For the next great step in analytical mechanics, the publication of D'Alembert's 365 principle in 1743, in a great degree superseded their interest. The transactions of the academies of Paris and Berlin, as well as St. Petersburg, are filled, up to this time, with various questions of this kind. They require, for the most part, the determination of the motions of several bodies, with or without weight, which pull or push each other by means of threads or levers to which they are fastened, or along which they can slide, and which, having a certain impulse given them at first, are then left to themselves, or are compelled to move in given lines and surfaces. The postulate of Huygens, respecting the motion of the center of gravity, was generally one of the principles of the solution. But other principles were always needed in addition to this, and it required the exercise of ingenuity and skill to detect the most suitable in each case. Such problems were, for some time, a sort of trial of strength among mathematicians. The principle of D'Alembert put an end to this kind of challenges by supplying a direct and general method of resolving, or at least of throwing into equations, any imaginable problem. The mechanical difficulties were in this way reduced to difficulties of pure mathematics. For D'Alembert's principle. D'Alembert's principle is only the expression, in the most general form, of the principle upon which John Bernoulli, Hermann, and others had solved the problem of the center of oscillation. It was thus stated: the motion impressed on each particle of any system by the forces which act upon it may be resolved into two, the effective motion and the motion gained or lost. The effective motions will be the real motions of the parts, and the motions gained and lost will be such as would keep the system at rest. The distinction of statics, the doctrine of equilibrium, and dynamics, the doctrine of motion, was, as we have seen, fundamental, and the difference of difficulty and complexity in the two subjects was well understood and generally recognized by mathematicians. D'Alembert's principle reduces every dynamical question to a statical one, and hence, by means of the conditions which connect the possible motions of the system, we can determine what the actual motions must be. The difficulty of determining the laws of equilibrium, in the application of this principle in complex cases, is, however, often as great as if we apply more simple and direct considerations. 5. Motion in resisting media. Ballistics. We shall notice more particularly the history of some of the problems of mechanics, though John Bernoulli always spoke with admiration of Newton's Principia, and of its author, he appears to have been well disposed to point out 366 real or imagined blemishes in the work. Against the validity of Newton's determination of the path described by a body projected in any part of the solar system, Bernoulli urges a cavil which it is difficult to conceive that a mathematician, such as he was, could seriously believe to be well-founded. On Newton's determination of the path of a body in a resisting medium, his criticism is more just. He pointed out a material error in this solution. This correction came to Newton's knowledge in London, in October 1712, when the impression of the second edition of the Principia was just drawing to a close under the care of Coates at Cambridge, and Newton immediately cancelled the leaf and corrected the error. This problem of the motion of a body in a resisting medium led to another collision between the English and the German mathematicians. The proposition to which we have referred gave only an indirect view of the nature of the curve described by a projectile in the air. And it is probable that Newton, when he wrote the Principia, did not see his way to any direct and complete solution of this problem. At a later period, in 1718, when the quarrel had waxed hot between the admirers of Newton and Leibniz, Whewell, who had come forward as a champion on the English side, proposed this problem to the foreigners as a challenge. Whewell probably imagined that what Newton had not discovered, no one of his time would be able to discover. But the sedulous cultivation of analysis by the Germans had given them mathematical powers beyond the expectations of the English, who, whatever might be their talents, had made little advance in the effective use of general methods, and for a long period seemed to be fascinated to the spot in their admiration of Newton's excellence. Bernoulli speedily solved the problem, and reasonably enough, according to the law of honor of such challenges, called upon the challenger to produce his solution. Whewell was unable to do this, and after some attempts at procrastination, was driven to very paltry evasions. Bernoulli then published his solution, with very just expressions of scorn towards his antagonist, and this may, perhaps, be considered as the first material addition which was made to the Principia by subsequent writers. 6 constellation of mathematicians we pass with admiration along the great series of mathematicians, by whom the science of theoretical mechanics has been cultivated, from the time of Newton to our own. There is no group of men of science whose fame is 367 higher or brighter. The great discoveries of Copernicus, Galileo, Newton had fixed all eyes on those portions of human knowledge on which their successors employed their labors. The certainty belonging to this line of speculation seemed to elevate mathematicians above the students of other subjects, and the beauty of mathematical relations and the subtlety of intellect which may be shown in dealing with them were fitted to win unbounded applause. The successors of Newton and the Bernoullis, as Euler, Clairaut, D'Alembert, Lagrange, Laplace, not to introduce living names, have been some of the most remarkable men of talent which the world has seen. That their talent is, for the most part, of a different kind from that by which the laws of nature were discovered, I shall have occasion to explain elsewhere. For the present, I must endeavor to arrange the principal achievements of those whom I have mentioned. The series of persons is connected by social relations. Euler was the pupil of the first generation of Bernoullis and the intimate friend of the second generation, and all these extraordinary men, as well as Hermann, were of the city of Basel, in that age a spot fertile of great mathematicians to an unparalleled degree. In 1740, Clairaut and Maupertuis visited John Bernoulli, at that time the Nestor of mathematicians, who died, full of age and honors, in 1748. Euler, several of the Bernoullis, Maupertuis, Lagrange, among other mathematicians of smaller note, were called into the north by Catharine of Russia and Frederick of Prussia, to inspire and instruct academies which the brilliant fame then attached to science had induced those monarchs to establish. The prizes proposed by these societies, and by the French Academy of Sciences, gave occasion to many of the most valuable mathematical works of the century. 7. The problem of 3 bodies in 1747, Clairaut and D'Alembert sent, on the same day, to this body, their solutions of the celebrated problem of 3 bodies, which, from that time, became the great object of attention of mathematicians, the bow in which each tried his strength, and endeavored to shoot further than his predecessors. This problem was, in fact, the astronomical question of the effect produced by the attraction of the sun in disturbing the motions of the moon about the earth, or by the attraction of one planet, disturbing the motion of another planet about the sun, but being expressed generally as referring to one body which disturbs any 2 others, it became a mechanical problem, and the history of it belongs to the present subject. 368. One consequence of the synthetical form adopted by Newton in the Principia was that his successors had the problem of the solar system to begin entirely anew. Those who would not do this made no progress, as was long the case with the English. Clairaut says that he tried for a long time to make some use of Newton's labors, but that, at last, he resolved to take up the subject in an independent manner. This, accordingly, he did, using analysis throughout, and following methods not much different from those still employed. We do not now speak of the comparison of this theory with observation, except to remark that both by the agreements and by the discrepancies of this comparison, Clairaut and other writers were perpetually driven on to carry forwards the calculation to a greater and greater degree of accuracy. One of the most important of the cases in which this happened was that of the movement of the apogee of the moon. And in this case, a mode of approximating to the truth, which had been depended on as nearly exact, was, after having caused great perplexity, found by Clairaut and Euler to give only half the truth. This same problem of three bodies was the occasion of a memoir of Clairaut, which gained the prize of the Academy of St. Petersburg in 1751, and, finally, of his Théorie de la Lune, published in 1765. D'Alembert labored at the same time on the same problem, and the value of their methods and the merit of the inventors unhappily became a subject of controversy between those two great mathematicians. Euler also, in 1753, published a theory of the moon, which was, perhaps, more useful than either of the others, since it was afterwards the basis of Mayer's method and of his tables. It is difficult to give the general reader any distinct notion of these solutions. We may observe that the quantities which determine the moon's position are to be determined by means of certain algebraical equations, which express the mechanical conditions of the motion. The operation, by which the result is to be obtained, involves the process of integration, which, in this instance, cannot be performed in an immediate and definite manner, since the quantities thus to be operated on depend upon the moon's position, and thus require us to know the very thing which we have to determine by the operation. The result must be got at, therefore, by successive approximations. We must first find a quantity near the truth, and then, by the help of this, one nearer still, and so on, and, in this manner, the moon's place will be given by a converging series of terms. The form of these terms depends upon the relations of position between the sun, 369, and moon, their apogees, the moon's nodes, and other quantities, and by the variety of combinations of which these admit, the terms become very numerous and complex. The magnitude of the terms depends also upon various circumstances, as the relative force of the sun and earth, the relative times of the solar and lunar revolutions, the eccentricities and inclinations of the two orbits. These are combined so as to give terms of different orders of magnitudes, and it depends upon the skill and perseverance of the mathematician how far he will continue this series of terms. For there is no limit to their number, and though the methods of which we have spoken do theoretically enable us to calculate as many terms as we please, the labor and the complexity of the operations are so serious that common calculators are stopped by them. None but very great mathematicians have been able to walk safely any considerable distance into this avenue, so rapidly does it darken as we proceed. And even the possibility of doing what has been done depends upon what we may call accidental circumstances, the smallness of the inclinations and eccentricities of the system, and the like. If nature had not favored us in this way, Lagrange used to say, there would have been an end of the geometers in this problem. The expected return of the comet of 1682 in 1759 gave a new interest to the problem, and Clairaut proceeded to calculate the case which was thus suggested. When this was treated by the methods which had succeeded for the moon, it offered no prospect of success, in consequence of the absence of the favorable circumstances just referred to, and, accordingly, Clairaut, after obtaining the 6 equations to which he reduces the solution, adds, integrate them who can, integer maintenent qui pora. New methods of approximation were devised for this case. The problem of three bodies was not prosecuted in consequence of its analytical beauty or its intrinsic attraction, but its great difficulties were thus resolutely combated from necessity, because in no other way could the theory of universal gravitation be known to be true or made to be useful. The construction of tables of the moon, an object which offered a large pecuniary reward, as well as mathematical glory, to the successful adventurer, was the main purpose of these labors. The theory of the planets presented the problem of three bodies in a new form and involved in peculiar difficulties. For the 370, approximations which succeed in the lunar theory fail here. Artifices somewhat modified are required to overcome the difficulties of this case. Euler had investigated, in particular, the motions of Jupiter and Saturn, in which there was a secular acceleration and retardation, known by observation, but not easily explicable by theory. Euler's memoirs, which gained the prize of the French Academy in 1748 and 1752, contained much beautiful analysis, and Lagrange published also A Theory of Jupiter and Saturn, in which he obtained results different from those of Euler. Laplace, in 1787, showed that this inequality arose from the circumstance that 2 of Saturn's years are very nearly equal to 5 of Jupiter's. The problems relating to Jupiter's satellites were found to be even more complex than those which refer to the planets, for it was necessary to consider each satellite as disturbed by the other 3 at once, and thus there occurred the problem of 5 bodies. This problem was resolved by Lagrange. Again, the newly discovered small planets, Juno, Ceres, Vesta, Pallas, whose orbits almost coincide with each other, and are more inclined and more eccentric than those of the ancient planets, give rise, by their perturbations, to new forms of the problem and require new artifices. In the course of these researches respecting Jupiter, Lagrange and Laplace were led to consider particularly the secular inequalities of the solar system. That is, those inequalities in which the duration of the cycle of change embraces very many revolutions of the bodies themselves. Euler in 1749 and 1755, and Lagrange in 1766, had introduced the method of the variation of the elements of the orbit, which consists in tracing the effect of the perturbing forces, not as directly altering the place of the planet, but as producing a change from one instant to another in the dimensions and position of the elliptical orbit which the planet describes. Taking this view, he, 371, determines the secular changes of each of the elements or determining quantities of the orbit. In 1773, Laplace also attacked this subject of secular changes and obtained expressions for them. On this occasion, he proved the celebrated proposition that the mean motions of the planets are invariable. That is, that there is, in the revolutions of the system, no progressive change which is not finally stopped and reversed, no increase which is not, after some period, changed into decrease, no retardation which is not at last succeeded by acceleration, although in some cases millions of years may elapse before the system reaches the turning point. Thomas Simpson noticed the same consequence of the laws of universal attraction. In 1774 and 1776, Lagrange still labored at the secular equations, extending his researches to the nodes and inclinations, and showed that the invariability of the mean motions of the planets, which Laplace had proved, neglecting the fourth powers of the eccentricities and inclinations of the orbits, was true, however far the approximation was carried, so long as the squares of the disturbing masses were neglected. He afterwards improved his methods, and in 1783 he endeavored to extend the calculation of the changes of the elements to the periodical equations, as well as the secular. Note 52/6. In the first edition of this history, I had ascribed to Lagrange the invention of the method of variation of elements in the theory of perturbations. But justice to Euler requires that we should assign this distinction to him, at least, next to Newton, whose mode of representing the paths of bodies by means of a revolving orbit in the 9th section of the Principia may be considered as an anticipation of the method of variation of elements. In the 5th volume of the Mécanique Céleste, Liver Roman 15, p. 305 is an abstract of Euler's paper of 1749, where Laplace adds, "C'est le premier essai de la méthode de la variation des constants arbitraires." And in page 310 is an abstract of the paper of 1756. And speaking of the method, Laplace says, it consists in regarding the elements of the elliptical motion as variable in virtue of the perturbing forces. Those elements are 1. The axis major, 2. The epoch of the body being at the apse, 3. The eccentricity, 4. The movement of the apse, 5. The inclination, 6. The longitude of the node, and he then proceeds to show how Euler did this. It is possible that Lagrange knew nothing of Euler's paper. See Make. Sale, volume VP 312. But Euler's conception and treatment of the method are complete, so that he must be looked upon as the author of it. Mécanique Céleste and C. Laplace also resumed the consideration of the secular changes, and finally undertook his vast work, the Mécanique Céleste, which he intended to contain a complete view of the existing state of this splendid department of science. We may see, in the exultation which the author obviously feels at the thought of erecting this monument of his age, the enthusiasm which had been excited by the splendid course of mathematical successes of which I have given a sketch. The two first volumes of this great work appeared in 1799. The third and fourth volumes were published in 1802 and 1805, respectively. Since its publication, little has been added to the solution of the great problems of which it treats. In 1808, Laplace presented to the French Bureau des Longitudes a supplement to the Mécanique Céleste, the object of which was to improve still further, 372, the mode of obtaining the secular variations of the elements. Poisson and Lagrange proved the invariability of the major axes of the orbits, as far as the second order of the perturbing forces. Various other authors have since labored at this subject. Burckhardt in 1808 extended the perturbing function as far as the sixth order of the eccentricities. Gauss, Hansen, and Bessel, Ivory, Lubbock, Plana, Pontécoulant, and Airy have, at different periods up to the present time, either extended or illustrated some particular part of the theory or applied it to special cases, as in the instance of Professor Airy's calculation of an inequality of Venus and the Earth, of which the period is 240 years. The approximation of the Moon's motions has been pushed to an almost incredible extent by M. Damiso, and, finally, Plana has once more attempted to present, in a single work, 3 thick quarto volumes, all that has hitherto been executed with regard to the theory of the Moon. I give only the leading points of the progress of analytical dynamics. Hence, I have not spoken in detail of the theory of the satellites of Jupiter, a subject on which Lagrange gained a prize for a memoir in 1766, and in which Laplace discovered some most curious properties in 1784. Still less have I referred to the purely speculative question of tautochronous curves in a resisting medium, though it was a subject of the labors of Bernoulli, Euler, Fontaine, D'Alembert, Lagrange, and Laplace. The reader will rightly suppose that many other curious investigations are passed over in utter silence. Although the analytical calculations of the great mathematicians of the last century had determined, in a demonstrative manner, a vast series of inequalities to which the motions of the sun, moon, and planets were subject in virtue of their mutual attraction, there were still unsatisfactory points in the solutions thus given of the great mechanical problems suggested by the system of the universe. One of these points was the want of any evident mechanical significance in the successive members of these series. Lindenau relates that Lagrange, near the end of his life, expressed his sorrow that the methods of approximation employed in physical astronomy rested on arbitrary processes and not on any insight into the results of mechanical action. But something was subsequently done to remove the ground of this complaint. In 1818, Gauss pointed out that secular equations may be conceived to result from the disturbing body being distributed along its orbit so as to form a ring, and thus made the result conceivable more distinctly than as a mere result of calculation. And it appears, 373, to me, that Professor Airy's treatise entitled Gravitation, published at Cambridge in 1834, is of great value in supplying similar modes of conception with regard to the mechanical origin of many of the principal inequalities of the solar system. Bessel in 1824 and Hansen in 1828 published works which are considered as belonging, along with those of Gauss, to a new era in physical astronomy. Gauss's Theoria Motuum Corporum Celestium, which had Lalland's medal assigned to it by the French Institute, had already, 1810, resolved all problems concerning the determination of the place of a planet or comet in its orbit in function of the elements. The value of Hansen's labors respecting the perturbations of the planets was recognized by the Astronomical Society of London, which awarded to them its gold medal. Note 56/6, Abhand der Akad, Die Wissenschaft, zu Berlin, 1824, and Disquisitions circa Theorem Perturbationum. See John, Jesch der Astron, p. 84. The investigations of M. Damiso and of Mplana and Carlini on the problem of the lunar theory, followed nearly the same course as those of their predecessors. In these, as in the Mécanique céleste and in preceding works on the same subject, the moon's coordinates, time, radius vector, and latitude were expressed in function of her true longitude. The integrations were effected in series, and then by reversion of the series, the longitude was expressed in function of the time, and then in the same manner the other two coordinates. But Sir John Lubbock and M. Pontécoulant have made the mean longitude of the moon, that is, the time, the independent variable, and have expressed the moon's coordinates in terms of sines and cosines of angles increasing proportionally to the time, and this method has been adopted by M. Poisson Mem. Inst. Roman 13. 1835, p. 212. M. Damasceau, like Laplace and Clairaut, had deduced the successive coefficients of the lunar inequalities by numerical equations. But M. Plana expresses explicitly each coefficient in general terms of the letters expressing the constants of the problem, arranging them according to the order of the quantities, and substituting numbers at the end of the operation only. By attending to this arrangement, Lubbock and Pontécoulant have verified or corrected a large portion of the terms contained in the investigations of Damasceau and Plana. Sir John Lubbock has calculated the polar coordinates of the moon directly. M. Poisson, on the other hand, has obtained the variable elliptical elements. M. Pontécoulant conceives that the method of variation, or arbitrary, 374 constants may most conveniently be reserved for secular inequalities and inequalities of long periods. Lubbock and Pontécoulant have made the mode of treating the lunar theory and the planetary theory agree with each other, instead of following two different paths in the calculation of the two problems, which had previously been done. Prof. Hansen, also, in his Fundamenta Nova Investigationis Orbiti Vari Quam Luna Perlustrat Gothi, 1838, gives a general method, including the lunar theory and the planetary theory as two special cases. To this is annexed a solution of the problem of four bodies. I am here speaking of the lunar and planetary theories as mechanical problems only. Connected with this subject, I will not omit to notice a very general and beautiful method of solving problems respecting the motion of systems asterisk of mutually attracting bodies, given by Sir W. R. Hamilton in the Philosophical Transactions for 1834-5, on a general method in dynamics. His method consists in investigating the principal function of the coordinates of the bodies, this function being 1, by the differentiation of which the coordinates of the bodies of the system may be found. Moreover, an approximate value of this function being obtained, the same formulae supply a means of successive approximation without limit. 9. Precession. Motion of rigid bodies. The series of investigations of which I have spoken, extensive and complex as it is, treats the moving bodies as points only, and takes no account of any peculiarity of their form or motion of their parts. The investigation of the motion of a body of any magnitude and form is another branch of analytical mechanics, which well deserves notice. Like the former branch, it mainly owed its cultivation to the problems suggested by the solar system. Newton, as we have seen, endeavored to calculate the effect of the attraction of the sun and moon in producing the precession of the equinoxes, but in doing this he made some mistakes. In 1747, D'Alembert solved this problem by the aid of his principle, and it was not difficult for him to show, as he did in his opuscules, in 1761, that the same method enabled him to determine the motion of a body of any figure acted upon by any forces. But as the reader will have observed in the course of this narrative, the great mathematicians of this period were always nearly abreast of each other in their advances. Euler, in the meantime, had published, in 1751, a solution of the 375 problem of the precession, and in 1752, a memoir which he entitled Discovery of a New Principle of Mechanics, and which contains a solution of the general problem of the alteration of rotary motion by forces. D'Alembert noticed with disapprobation the assumption of priority which this title implied, though allowing the merit of the memoir. Various improvements were made in these solutions, but the final form was given them by Euler, and they were applied to a great variety of problems in his theory of the motion of solid and rigid bodies, which was written about 1760 and published in 1765. The formulae in this work were much simplified by the use of a discovery of Segner, that every body has three axes which were called principal axes, about which alone, in general, it would permanently revolve. The equations which Euler and other writers had obtained were attacked as erroneous by Landon in the Philosophical Transactions for 1785. But I think it is impossible to consider this criticism otherwise than as an example of the inability of the English mathematicians of that period to take a steady hold of the analytical generalizations to which the great continental authors had been led. Perhaps one of the most remarkable calculations of the motion of a rigid body is that which Lagrange performed with regard to the moon's libration, and by which he showed that the nodes of the moon's equator and those of her orbit must always coincide. Vibrating strings. Other mechanical questions, unconnected with astronomy, were also pursued with great zeal and success. Among these was the problem of a vibrating string, stretched between two fixed points. There is not much complexity in the mechanical conceptions which belong to this case, but considerable difficulty in reducing them to analysis. Taylor, in his Method of Increments, published in 1716, had annexed to his work a solution of this problem, obtained on suppositions, limited indeed, but apparently conformable to the most common circumstances of practice. John Bernoulli, in 1728, had also treated the same problem. But it assumed an interest altogether new, when in 1747 D'Alembert published his views on the subject, in which he maintained that, instead of one kind of curve only, there were an infinite number of different curves, which answered the conditions of the question. The problem, thus put forward by one great mathematician, was, as usual, taken up by the others, whose names the reader is now so familiar with in such an association. In 376, 1748, Euler not only assented to the generalization of D'Alembert, but held that it was not necessary that the curves so introduced should be defined by any algebraical condition whatever. From this extreme indeterminateness D'Alembert dissented, while Daniel Bernoulli, trusting more to physical and less to analytical reasonings, maintained that both these generalizations were inapplicable in fact, and that the solution was really restricted, as had at first been supposed, to the form of the trochoid, and to other forms derivable from that. He introduced, in such problems, the law of coexistent vibrations, which is of eminent use in enabling us to conceive the results of complex mechanical conditions and the real import of many analytical expressions. In the meantime, the wonderful analytical genius of Lagrange had applied itself to this problem. He had formed the Academy of Turin, in conjunction with his friends Saluses and Signa, and the first memoir in their Transactions was one by him on this subject. In this and in subsequent writings he has established, to the satisfaction of the mathematical world, that the functions introduced in such cases are not necessarily continuous, but are arbitrary to the same degree that the motion is so practically, though capable of expression by a series of circular functions. This controversy, concerning the degree of lawlessness with which the conditions of the solution may be assumed, is of consequence, not only with respect to vibrating strings, but also with respect to many problems, belonging to a branch of mechanics which we now have to mention, the doctrine of fluids. 11. Equilibrium of fluids. Figure of the earth. Tides. The application of the general doctrines of mechanics to fluids was a natural and inevitable step, when the principles of the science had been generalized. It was easily seen that a fluid is, for this purpose, nothing more than a body of which the parts are movable amongst each other with entire facility, and that the mathematician must trace the consequences of this condition upon his equations. This accordingly was done by the founders of mechanics, both for the cases of the equilibrium and of motion. Newton's attempt to solve the problem of the figure of the earth, supposing it fluid, is the first example of such an investigation. And this solution rested upon principles which we have already explained, applied with the skill and sagacity which distinguished all that Newton did. We have already seen how the generality of the principle, that fluids press equally in all directions, was established. In applying it to calculation, Newton took for his fundamental principle the equal 377 weight of columns of the fluid reaching to the center. Huygens took, as his basis, the asterisk perpendicularity of the resulting force at each point to the surface of the fluid. Bauger conceived that both principles were necessary, and Clairaut showed that the equilibrium of all canals is requisite. He also was the first mathematician who deduced from this principle the equations of partial differentials by which these laws are expressed, a step which, as Lagrange says, changed the face of hydrostatics and made it a new science. Euler simplified the mode of obtaining the equations of equilibrium for any forces whatever, and put them in the form which is now generally adopted in our treatises. The explanation of the tides, in the way in which Newton attempted it in the third book of the Principia, is another example of a hydrostatical investigation, for he considered only the form that the ocean would have if it were at rest. The memoirs of Maclaurin, Daniel Bernoulli, and Euler on the question of the tides, which shared among them the prize of the Academy of Sciences in 1740, went upon the same views. The Treatise of the Figure of the Earth, by Clairaut, in 1743, extended Newton's solution of the same problem by supposing a solid nucleus covered with a fluid of different density. No peculiar novelty has been introduced into this subject, except a method employed by Laplace for determining the attractions of spheroids of small eccentricity, which is, as Professor Airy has said, a calculus the most singular in its nature and the most powerful in its effects, of any which has yet appeared. Capillary action there is only one other problem of the statics of fluids on which it is necessary to say a word, the doctrine of capillary attraction. Daniel Bernoulli, in 1738, states that he passes over the subject because he could not reduce the facts to general laws. But Clairaut was more successful, and Laplace and Poisson have since given great analytical completeness to his theory. At present, our business is not so much with the sufficiency of the theory to explain phenomena, as with the mechanical problem of which this is an example, which is one of a very remarkable and important character. Namely, to determine the effect of attractions which are exercised by all the particles of bodies, on the hypothesis that the 378 attraction of each particle, though sensible when it acts upon another particle at an extremely small distance from it, becomes insensible and vanishes the moment this distance assumes a perceptible magnitude. It may easily be imagined that the analysis by which results are obtained under conditions so general and so peculiar is curious and abstract. The problem has been resolved in some very extensive cases. Motion of fluids, the only branch of mathematical mechanics which remains to be considered, is that which is, we may venture to say, hitherto incomparably the most incomplete of all, hydrodynamics. It may easily be imagined that the mere hypothesis of absolute relative mobility in the parts, combined with the laws of motion and nothing more, are conditions too vague and general to lead to definite conclusions. Yet such are the conditions of the problems which relate to the motion of fluids. Accordingly, the mode of solving them has been to introduce certain other hypotheses, often acknowledged to be false, and almost always in some measure arbitrary, which may assist in determining and obtaining the solution. The velocity of a fluid issuing from an orifice in a vessel, and the resistance which a solid body suffers in moving in a fluid, have been the two main problems on which mathematicians have employed themselves. We have already spoken of the manner in which Newton attacked both these and endeavored to connect them. The subject became a branch of analytical mechanics by the labors of de Bernoulli, whose Hydrodynamica was published in 1738. This work rests upon the Huyghenian principle of which we have already spoken in the history of the center of oscillation, namely, the equality of the actual descent of the particles and the potential ascent, or, in other words, the conservation of vis viva. This was the first analytical treatise, and the analysis is declared by Lagrange to be as elegant in its steps as it is simple in its results. Maclaurin also treated the subject, but is accused of reasoning in such a way as to show that he had determined upon his result beforehand. And the method of John Bernoulli, who likewise wrote upon it, has been strongly objected to by D'Alembert. D'Alembert himself applied the principle which bears his name to this subject, publishing a treatise on the equilibrium and motion of fluids in 1744 and on the resistance of fluids in 1753. His Réflexions sur la cause générale des vents, printed in 1747, are also a celebrated work, belonging to this part of mathematics. Euler, in this as in other cases, was one of those who most contributed to give analytical elegance to the subject. In addition to the questions which 379 have been mentioned, he and Lagrange treated the problems of the small vibrations of fluids, both inelastic and elastic, a subject which leads, like the question of vibrating strings, to some subtle and abstruse considerations concerning the significations of the integrals of partial differential equations. Laplace also took up the subject of waves propagated along the surface of water, and deduced a very celebrated theory of the tides, in which he considered the ocean to be not in equilibrium, as preceding writers had supposed, but agitated by a constant series of undulations, produced by the solar and lunar forces. The difficulty of such an investigation may be judged of from this, that Laplace, in order to carry it on, is obliged to assume a mechanical proposition, unproved and only conjectured to be true. Namely, that, in a system of bodies acted upon by forces which are periodical, the state of the system is periodical like the forces. Even with this assumption, various other arbitrary processes are requisite, and it appears still very doubtful whether Laplace's theory is either a better mechanical solution of the problem or a nearer approximation to the laws of the phenomena than that obtained by de Bernoulli following the views of Newton. In most cases, the solutions of problems of hydrodynamics are not satisfactorily confirmed by the results of observation. Poisson and Cauchy have prosecuted the subject of waves and have deduced very curious conclusions by a very recondite and profound analysis. The assumptions of the mathematician here do not represent the conditions of nature. The rules of theory, therefore, are not a good standard to which we may refer the aberrations of particular cases, and the laws which we obtain from experiment are very imperfectly illustrated by a priori calculation. The case of this department of knowledge, hydrodynamics, is very peculiar. We have reached the highest point of the science, the laws of extreme simplicity and generality from which the phenomena flow. We cannot doubt that the ultimate principles which we have obtained are the true ones and those which really apply to the facts, and yet we are far from being able to apply the principles to explain or find out the facts. In order to do this, we want, in addition to what we have, true and useful principles, intermediate between the highest and the lowest, between the extreme and almost barren generality of the laws of motion, and the endless varieties and inextricable complexity of fluid motions in special cases. 380. The reason of this peculiarity in the science of hydrodynamics appears to be that its general principles were not discovered with reference to the science itself, but by extension from the sister science of the mechanics of solids. They were not obtained by ascending gradually from particulars to truths more and more general respecting the motions of fluids, but were caught at once by a perception that the parts of fluids are included in that range of generality which we are entitled to give to the supreme laws of motions of solids. Thus, solid dynamics and fluid dynamics resemble two edifices which have their highest apartment in common, and though we can explore every part of the former building, we have not yet succeeded in traversing the staircase of the latter, either from the top or from the bottom. If we had lived in a world in which there were no solid bodies, we should probably not have yet discovered the laws of motion. If we had lived in a world in which there were no fluids, we should have no idea how insufficient a complete possession of the general laws of motion may be to give us a true knowledge of particular results. 14. Various general mechanical principles, the generalized laws of motion, the points to which I have endeavored to conduct my history, include in them all other laws by which the motions of bodies can be regulated, and among such, several laws which had been discovered before the highest point of generalization was reached, and which thus served as stepping stones to the ultimate principles. Such were, as we have seen, the principles of the conservation of vis viva, the principle of the conservation of the motion of the center of gravity, and the like. These principles may, of course, be deduced from our elementary laws, and were finally established by mathematicians on that footing. There are other principles which may be similarly demonstrated. Among the rest, I may mention the principle of the conservation of areas, which extends to any number of bodies, a law analogous to that which Kepler had observed, and Newton demonstrated, respecting the areas described by each planet round the Sun. I may mention also the principle of the immobility of the plane of maximum areas, a plane which is not disturbed by any mutual action of the parts of any system. The former of these principles was published about the same time by Euler, de Bernoulli, and Darcy, under different forms, in 1746 and 1747, the latter by Laplace. To these may be added a law, very celebrated in its time, and the occasion of an angry controversy, the principle of least action. 381, Maupertuis conceived that he could establish a priori, by theological arguments, that all mechanical changes must take place in the world so as to occasion the least possible quantity of action. In asserting this, it was proposed to measure the action by the product of velocity and space. And this measure being adopted, the mathematicians, though they did not generally assent to Maupertuis' reasonings, found that his principle expressed a remarkable and useful truth, which might be established on known mechanical grounds. 15. Analytical generality. Connection of statics and dynamics. Before I quit this subject, it is important to remark the peculiar character which the science of mechanics has now assumed, in consequence of the extreme analytical generality which has been given it. Symbols and operations upon symbols include the whole of the reasoner's task. And though the relations of space are the leading subjects in the science, the great analytical treatises upon it do not contain a single diagram. The Mécanique analytique of Lagrange, of which the first edition appeared in 1788, is by far the most consummate example of this analytical generality. The plan of this work, says the author, is entirely new. I have proposed to myself to reduce the whole theory of this science, and the art of resolving the problems which it includes, to general formulae, of which the simple development gives all the equations necessary for the solution of the problem. The reader will find no figures in the work. The methods which I deliver do not require either constructions or geometrical or mechanical reasonings, but only algebraical operations, subject to a regular and uniform rule of proceeding. Thus this writer makes mechanics a branch of analysis, instead of making, as had previously been done, analysis an implement of mechanics. The transcendent generalizing genius of Lagrange, and his matchless analytical skill and elegance, have made this undertaking as successful as it is striking. Note 63/6. Lagrange himself terms mechanics an analytical geometry of 4 dimensions. Besides the 3 coordinates which determine the place of a body in space, the time enters as a 4th coordinate. The mathematical reader is aware that the language of mathematical symbols is, in its nature, more general than the language of words, and that in this way truths, translated into symbols, often suggest their own generalizations. Something of this kind has happened in mechanics. The same formula expresses the general condition of statics and that of dynamics. The tendency to generalization which is thus introduced by analysis makes mathematicians unwilling to 382 acknowledge a plurality of mechanical principles. And in the most recent analytical treatises on the subject, all the doctrines are deduced from the single law of inertia. Indeed, if we identify forces with the velocities which produce them, and allow the composition of forces to be applicable to force so understood, it is easy to see that we can reduce the laws of motion to the principles of statics. And this conjunction, though it may not be considered as philosophically just, is verbally correct. If we thus multiply or extend the meanings of the term force, we make our elementary principles simpler and fewer than before. And those persons, therefore, who are willing to assent to such a use of words, can thus obtain an additional generalization of dynamical principles. And this, as I have stated, has been adopted in several recent treatises. I shall not further discuss here how far this is a real advance in science. Having thus rapidly gone through the history of force and attraction in the abstract, we return to the attempt to interpret the phenomena of the universe by the aid of these abstractions thus established. But before we do so, we may make one remark on the history of this part of science. In consequence of the vast career into which the doctrine of motion has been drawn by the splendid problems proposed to it by astronomy, the origin and starting point of mechanics, namely machines, had almost been lost out of sight. Machines had become the smallest part of mechanics, as land measuring had become the smallest part of geometry. Yet the application of mathematics to the doctrine of machines has led, at all periods of the science, and especially in our own time, to curious and valuable results. Some of these will be noticed in the additions to this volume. 383, Book 7. The Mechanical Sciences, Continued. History of Physical Astronomy. Descend from heaven, Urania, by that name if rightly thou art called, whose voice divine following, above the Olympian hill I soar, above the flight of Pegasean wing. The meaning, not the name, I call, for thou nor of the Muses 9, nor on the top of old Olympus dwell'st, but heavenly born before the hills appeared or fountain flowed, thou with eternal wisdom didst converse. Wisdom, thy sister. Paradise Lost, B. Roman 7. 385, Chapter 1. Prelude to the Inductive Epoch of Newton. We have now to contemplate the last and most splendid period of the progress of astronomy, the grand completion of the history of the most ancient and prosperous province of human knowledge, the steps which elevated this science to an unrivaled eminence above other sciences. The first great example of a wide and complex assemblage of phenomena indubitably traced to their single simple cause, in short, the first example of the formation of a perfect inductive science. In this, as in other considerable advances in real science, the complete disclosure of the new truths by the principal discoverer was preceded by movements and glimpses, by trials, seekings, and guesses on the part of others, by indications, in short, that men's minds were already carried by their intellectual impulses in the direction in which the truth lay, and were beginning to detect its nature. In a case so important and interesting as this, it is more peculiarly proper to give some view of this prelude to the epoch of the full discovery. Francis Bacon, that astronomy should become physical astronomy, that the motions of the heavenly bodies should be traced to their causes, as well as reduced to rule, was felt by all persons of active and philosophical minds as a pressing and irresistible need, at the time of which we speak. We have already seen how much this feeling had to do in impelling Kepler to the train of laborious research by which he made his discoveries. Perhaps it may be interesting to point out how strongly this persuasion of the necessity of giving a physical character to astronomy had taken possession of the mind of Bacon, who, looking at the progress of knowledge with a more comprehensive spirit, and from a higher point of view than Kepler, could have none of his astronomical prejudices, since on that subject he was of a different school, and of far inferior knowledge. In his Description of the Intellectual Globe, Bacon says that while astronomy had, up to that time, had it for her business to inquire into the rules of the heavenly motions, and philosophy into their causes, they had both so far worked without due appreciation of their respective tasks, philosophy neglecting facts, and astronomy claiming assent to her 386 mathematical hypotheses, which ought to be considered as mere steps of calculation. Since, therefore, he continues, each science has hitherto been a slight and ill-constructed thing, we must assuredly take a firmer stand. Our ground being that these two subjects, which on account of the narrowness of men's views and the traditions of professors have been so long dissevered, are, in fact, one and the same thing and compose one body of science. It must be allowed that, however erroneous might be the points of Bacon's positive astronomical creed, these general views of the nature and position of the science are most sound and philosophical. Kepler, in his attempts to suggest a right physical view of the starry heavens and their relation to the earth, Bacon failed, along with all the writers of his time. It has already been stated that the main cause of this failure was the want of a knowledge of the true theory of motion, the non-existence of the science of dynamics. At the time of Bacon and Kepler, it was only just beginning to be possible to reduce the heavenly motions to the laws of earthly motion, because the latter were only just then divulged. Accordingly, we have seen that the whole of Kepler's physical speculations proceed upon an ignorance of the first law of motion, and assume it to be the main problem of the physical astronomer to assign the cause which keeps up the motions of the planets. Kepler's doctrine is that a certain force or virtue resides in the sun, by which all bodies within his influence are carried round him. He illustrates the nature of this virtue in various ways, comparing it to light and to the magnetic power which it resembles in the circumstances of operating at a distance, and also in exercising a feebler influence as the distance becomes greater. But it was obvious that these comparisons were very imperfect, for they do not explain how the sun produces in a body at a distance a motion athwart the line of emanation. And though Kepler introduced an assumed rotation of the sun on his axis as the cause of this effect, that such a cause could produce the result could not be established by any analogy of terrestrial motions. But another image to which he referred suggested a much more substantial and conceivable kind of mechanical action by which the celestial motions might be produced, namely, a current of fluid matter circulating round the sun and carrying the planet with it like a boat in a stream. In the table of contents of the work on the planet Mars, the purport of the chapter to which I have alluded is 387, stated as follows: a physical speculation in which it is demonstrated that the vehicle of that virtue which urges the planets circulates through the spaces of the universe after the manner of a river or whirlpool vortex, moving quicker than the planets. I think it will be found, by anyone who reads Kepler's phrases concerning the moving force, the magnetic nature, the immaterial virtue of the sun, that they convey no distinct conception, except so far as they are interpreted by the expressions just quoted. A vortex of fluid constantly whirling round the sun, kept in this whirling motion by the rotation of the sun himself, and carrying the planets round the sun by its revolution, as a whirlpool carries straws, could be readily understood. And though it appears to have been held by Kepler that this current and vortex was immaterial, he ascribes to it the power of overcoming the inertia of bodies, and of putting them and keeping them in motion, the only material properties with which he had anything to do. Kepler's physical reasonings, therefore, amount, in fact, to the doctrine of vortices round the central bodies, and are occasionally so stated by himself, though by asserting these vortices to be an immaterial species. And by the fickleness and variety of his phraseology on the subject, he leaves this theory in some confusion, a proceeding, indeed, which both his want of sound mechanical conceptions and his busy and inventive fancy might have led us to expect. Nor, we may venture to say, was it easy for anyone at Kepler's time to devise a more plausible theory than the theory of vortices might have been made. It was only with the formation and progress of the science of mechanics that this theory became untenable. Descartes, but if Kepler might be excused, or indeed admired, for propounding the theory of vortices at his time, the case was different when the laws of motion had been fully developed, and when those who knew the state of mechanical science ought to have learned to consider the motions of the stars as a mechanical problem, subject to the same conditions as other mechanical problems, and capable of the same exactness of solution. And there was an especial inconsistency in the circumstance of the theory of vortices being put forwards by Descartes, who pretended, or was asserted by his admirers, to have been one of the discoverers of the true laws of motion. It certainly shows both great conceit and great shallowness, that he should have proclaimed with much pomp this crude invention of the anti-mechanical period, at the time when the best mathematicians of Europe, as Borelli in Italy, Hooke and Wallis in England, Huygens in Holland, 388, were patiently laboring to bring the mechanical problem of the universe into its most distinct form, in order that it might be solved at last and forever. I do not mean to assert that Descartes borrowed his doctrines from Kepler or from any of his predecessors, for the theory was sufficiently obvious, and especially if we suppose the inventor to seek his suggestions rather in the casual examples offered to the sense than in the exact laws of motion. Nor would it be reasonable to rob this philosopher of that credit, of the plausible deduction of a vast system from apparently simple principles, which, at the time, was so much admired, and which undoubtedly was the great cause of the many converts to his views. At the same time, we may venture to say that a system of doctrine thus deduced from assumed principles by a long chain of reasoning, and not verified and confirmed at every step by detailed and exact facts, has hardly a chance of containing any truth. Descartes said that he should think it little to show how the world is constructed, if he could not also show that it must of necessity have been so constructed. The more modest philosophy, which has survived the boastings of his school, is content to receive all its knowledge of facts from experience, and never dreams of interposing its peremptory must be when nature is ready to tell us what is. The a priori philosopher has, however, always a strong feeling in his favor among men. The deductive form of his speculations gives them something of the charm and the apparent certainty of pure mathematics, And while he avoids that laborious recurrence to experiments and measures and multiplied observations, which is irksome and distasteful to those who are impatient to grow wise at once, every fact of which the theory appears to give an explanation seems to be an unasked and almost an infallible witness in its favor. My business with Descartes here is only with his physical theory of vortices, which, great as was its glory at one time, is now utterly extinguished. It was propounded in his Principia Philosophiae in 1644. In order to arrive at this theory, he begins, as might be expected of him, from reasonings sufficiently general. He lays it down as a maxim in the first sentence of his book that a person who seeks for truth must, once in his life, doubt of all that he most believes. Conceiving himself thus to have stripped himself of all his belief on all subjects, in order to resume that part of it which merits to be retained, he begins with his celebrated assertion, "I think, therefore I am," which appears to him a certain and immovable principle, by means of 389, which he may proceed to something more. Accordingly, to this he soon adds the idea, and hence the certain existence, of God and his perfections. He then asserts it to be also manifest that a vacuum in any part of the universe is impossible. The whole must be filled with matter, and the matter must be divided into equal angular parts, this being the most simple, and therefore the most natural supposition. This matter being in motion, the parts are necessarily ground into a spherical form, and the corners thus rubbed off like filings or sawdust form a second and more subtle matter. There is, besides, a third kind of matter of parts more coarse and less fitted for motion. The first matter makes luminous bodies, as the sun, and the fixed stars. The second is the transparent substance of the skies. The third is the material of opic bodies, as the earth, planets, and comets. We may suppose, also, that the motions of these parts take the form of revolving circular currents or vortices. By this means, the first matter will be collected to the center of each vortex, while the second, or subtle matter, surrounds it, and by its centrifugal effort, constitutes light. The planets are carried round the sun by the motion of his vortex, each planet being at such a distance from the sun as to be in a part of the vortex suitable to its solidity and mobility. The motions are prevented from being exactly circular and regular by various causes. For instance, a vortex may be pressed into an oval shape by contiguous vortices. The satellites are, in like manner, carried round their primary planets by subordinate vortices, while the comets have sometimes the liberty of gliding out of one vortex into the one next contiguous, and thus traveling in a sinuous course from system to system through the universe. It is not necessary for us to speak here of the entire deficiency of this system in mechanical consistency, and in a correspondency to observation in details and measures. Its general reception and temporary sway, in some instances even among intelligent men and good mathematicians, are the most remarkable facts connected with it. These may be ascribed, in part, to the circumstance that philosophers were now ready and eager for a physical astronomy commensurate with the existing state of knowledge. They may have been owing also, in some measure, to the character and position of Descartes. He was a man of high claims in every department of speculation, and in pure mathematics, a genuine inventor of great eminence. A man of family and a soldier and inoffensive philosopher, attacked and persecuted, 390, for his opinions with great bigotry and fury by a Dutch divine, Vogt, the favorite and teacher of two distinguished princesses, and, it is said, the lover of one of them. This was Elizabeth, the daughter of the Elector Frederick, and consequently granddaughter of our James I. His other royal disciple, the celebrated Christiana of Sweden, showed her zeal for his instructions by appointing the hour of 5 in the morning for their interviews. This, in the climate of Sweden and in the winter, was too severe a trial for the constitution of the philosopher, born in the sunny valley of the Loire, and, after a short residence at Stockholm, he died of an inflammation of the chest in 1650. He always kept up an active correspondence with his friend Mersenne, who was called, by some of the Parisians, the resident of Descartes at Paris, and who informed him of all that was done in the world of science. It is said that he at first sent to Mersenne an account of a system of the universe which he had devised, which went on the assumption of a vacuum. Mersenne informed him that the vacuum was no longer the fashion at Paris, upon which he proceeded to remodel his system and to re-establish it on the principle of a plenum. Undoubtedly, he tried to avoid promulgating opinions which might bring him into trouble. He, on all occasions, endeavored to explain away the doctrine of the motion of the earth, so as to evade the scruples to which the decrees of the Pope had given rise. And, in stating the theory of vortices, he says, "There is no doubt that the world was created at first with all its perfection. Nevertheless, it is well to consider how it might have arisen from certain principles, although we know that it did not." Indeed, in the whole of his philosophy, he appears to deserve the character of being both rash and cowardly, pusillanimous simul et audex, far more than Aristotle, to whose physical speculations Bacon applies this description. Whatever the causes might be, his system was well received and rapidly adopted. Gassendi, indeed, says that he found nobody who had the courage to read the Principia through, but the system was soon embraced by the younger professors who were eager to dispute in its favor. It is said that the University of Paris was on the point of publishing an edict against these new doctrines, and was only prevented from doing so by a pasquinade which is worth mentioning. It was composed by the poet Boileau about 1684 and professed to be a request in favor of Aristotle, and an edict issued from Mount 391, Parnassus in consequence. It is obvious that, at this time, the cause of Cartesianism was looked upon as the cause of free inquiry and modern discovery, in opposition to that of bigotry, prejudice, and ignorance. Probably the poet was far from being a very severe or profound critic of the truth of such claims. This petition of the masters of arts, professors, and regents of the University of Paris humbly showeth that it is of public notoriety that the sublime and incomparable Aristotle was, without contest, the first founder of the four elements, fire, air, earth, and water, that he did, by special grace, accord unto them a simplicity which belongeth not to them of natural right, and so on. Nevertheless, since, a certain time past, two individuals named Reason and Experience have leagued themselves together to dispute his claim to the rank which of justice pertains to him, and have tried to erect themselves a throne on the ruins of his authority, and, in order the better to gain their ends, have excited certain factious spirits, who, under the names of Cartesians and Gassendists, have begun to shake off the yoke of their master, Aristotle, and, contemning his authority, with unexampled temerity, would dispute the right which he had acquired of making true pass for false and false for true. In fact, this production does not exhibit any of the peculiar tenets of Descartes, although, probably, the positive points of his doctrines obtained a footing in the University of Paris, under the cover of this assault on his adversaries. The Physics of Rohault, a zealous disciple of Descartes, was published at Paris about 1670, and was, for a time, the standard book for students of this subject, both in France and in England. I do not here speak of the later defenders of the Cartesian system, for in their hands it was much modified by the struggle which it had to maintain against the Newtonian system. We are concerned with Descartes and his school only as they form part of the picture of the intellectual condition of Europe just before the publication of Newton's discoveries. Beyond this, the Cartesian speculations are without value. When, indeed, Descartes' countrymen could no longer refuse their assent and admiration to the Newtonian theory, it came to be the fashion among them to say that Descartes had been the necessary precursor of Newton, and to adopt a favorite saying of Leibniz, that the Cartesian philosophy was the antechamber of truth. Yet this comparison is far from being happy. It appeared rather as if these suitors had mistaken the door. For those, 392, who first came into the presence of truth herself, were those who never entered this imagined antechamber, and those who were in the antechamber first were the last in penetrating further. In partly the same spirit, Playfair has noted it as a service which Newton perhaps owed to Descartes, that he had exhausted one of the most tempting forms of error. We shall see soon that this temptation had no attraction for those who looked at the problem in its true light, as the Italian and English philosophers already did. Voltaire has observed, far more truly, that Newton's edifice rested on no stone of Descartes' foundations. He illustrates this by relating that Newton only once read the work of Descartes, and in doing so, wrote the word error, repeatedly, on the first 7 or 8 pages, after which he read no more. This volume, Voltaire adds, was for some time in the possession of Newton's nephew, Gassendi. Even in his own country, the system of Descartes was by no means universally adopted. We have seen that though Gassendi was coupled with Descartes as one of the leaders of the new philosophy, he was far from admiring his work. Gassendi's own views of the causes of the motions of the heavenly bodies are not very clear, nor even very clearly referable to the laws of mechanics, although he was one of those who had most share in showing that those laws apply to astronomical motions. In a chapter headed Qui sit matrix siderum causa, he reviews several opinions, but the one which he seems to adopt is that which ascribes the motion of the celestial globes to certain fibers, of which the action is similar to that of the muscles of animals. It does not appear, therefore, that he had distinctly apprehended either the continuation of the movements of the planets by the first law of motion, or their deflection by the second law, the two main steps on the road to the discovery of the true forces by which they are made to describe their orbits. Leibniz and c. Nor does it appear that in Germany mathematicians had attained this point of view. Leibniz, as we have seen, did not assent to the opinions of Descartes, as containing the complete truth, and yet his own views of the physics of the universe do not seem to have any great advantage over these. In 1671, he published a new physical hypothesis, by which the causes of most phenomena are deduced from a certain single universal motion supposed in our globe, not to be despised either by the Tychonians or the Copernicans. He supposes 393 the particles of the earth to have separate motions, which produce collisions and thus propagate an agitation of the ether, radiating in all directions, and, by the rotation of the sun on its axis, concurring with its rectilinear action on the earth, arises the motion of the earth about the sun. The other motions of the solar system are, as we might expect, accounted for in a similar manner, but it appears difficult to invest such an hypothesis with any mechanical consistency. John Bernoulli maintained to the last the Cartesian hypothesis, though with several modifications of his own, and even pretended to apply mathematical calculation to his principles. This, however, belongs to a later period of our history, to the reception, not to the prelude, of the Newtonian theory. Borelli. In Italy, Holland, and England, mathematicians appear to have looked much more steadily at the problem of the celestial motions, by the light which the discovery of the real laws of motion threw upon it. In Borelli's theories of the Medicean planets, printed at Florence in 1666, we have already a conception of the nature of central action, in which true notions begin to appear. The attraction of a body upon another, which revolves about it, is spoken of and likened to magnetic action, not converting the attracting force into a transverse force, according to the erroneous views of Kepler, but taking it as a tendency of the bodies to meet. It is manifest, says he, that every planet and satellite revolves round some principal globe of the universe as a fountain of virtue, which so draws and holds them that they cannot by any means be separated from it, but are compelled to follow it wherever it goes, in constant and continuous revolutions. And, further on, he describes the nature of the action as a matter of conjecture indeed, but with remarkable correctness. We shall account for these motions by supposing, that which can hardly be denied, that the planets have a certain natural appetite for uniting themselves with the globe round which they revolve, and that they really tend, with all their efforts, to approach to such globe. The planets, for instance, to the Sun, the Medicean stars to Jupiter. It is certain also that circular motion gives a body a tendency to recede from the center of such revolution, as we find in a wheel or a stone whirled in a sling. Let us suppose, then, the planet to endeavor to approach the Sun. Since, in the meantime, it requires, by the circular motion, a force to recede from the same central body, it comes to pass that when 394 those two opposite forces are equal, each compensates the other, and the planet cannot go nearer to the Sun nor further from him than a certain determinate space, and thus appears balanced and floating about him. This is a very remarkable passage, but it will be observed, at the same time, that the author has no distinct conception of the manner in which the change of direction of the planet's motion is regulated from one instant to another. Still less do his views lead to any mode of calculating the distance from the central body at which the planet would be thus balanced, or the space through which it might approach to the center and recede from it. There is a great interval from Borelli's guesses, even to Huygens' theorems, and a much greater to the beginning of Newton's discoveries. England. It is peculiarly interesting to us to trace the gradual approach towards these discoveries, which took place in the minds of English mathematicians, and this we can do with tolerable distinctness. Gilbert, in his work, De Magnete, printed in 1600, has only some vague notions that the magnetic virtue of the Earth in some way determines the direction of the Earth's axis, the rate of its diurnal rotation, and that of the revolution of the Moon about it. He died in 1603, and in his posthumous work, already mentioned, De Mundo Nostro Sublunari Philosophia Nova, 1651, we have already a more distinct statement of the attraction of one body by another. The force which emanates from the Moon reaches to the Earth, and in like manner, the magnetic virtue of the Earth pervades the region of the Moon. Both correspond and conspire by the joint action of both, according to a proportion and conformity of motions. But the Earth has more effect in consequence of its superior mass. The Earth attracts and repels the Moon, and the Moon, within certain limits, the Earth. Not so as to make the bodies come together, as magnetic bodies do, but so that they may go on in a continuous course. Though this phraseology is capable of representing a good deal of the truth, it does not appear to have been connected, in the author's mind, with any very definite notions of mechanical action in detail. We may probably say the same of Milton's language. What if the sun be center to the world, and other stars, by his attractive virtue and their own incited, dance about him various rounds? Par lost B Romanate, 395. Boyle, about the same period, seems to have inclined to the Cartesian hypothesis. Thus, in order to show the advantage of the natural theology which contemplates organic contrivances, over that which refers to astronomy, he remarks, "It may be said that in bodies inanimate, the contrivance is very rarely so exquisite, but that the various motions and occurrences of their parts may, without much improbability, be suspected capable, after many essays, to cast one another into several of those circumvolutions called by Epicurus sigma upsilon sigma, tau rho omicron phi letter 1f70 sigma, and by Descartes vortices, which being once made, may continue a long time after the manner explained by the latter." Neither Milton nor Boyle, however, can be supposed to have had an exact knowledge of the laws of mechanics, and therefore they do not fully represent the views of their mathematical contemporaries. But there arose about this time a group of philosophers who began to knock at the door where truth was to be found, although it was left for Newton to force it open. These were the founders of the Royal Society, Wilkins, Wallis, Seth Ward, Wren, Hooke, and others. The time of the beginning of the speculations and association of these men corresponds to the time of the civil wars between the king and Parliament in England, and it does not appear a fanciful account of their scientific zeal and activity to say that while they shared the common mental ferment of the times, they sought in the calm and peaceful pursuit of knowledge a contrast to the vexatious and angry struggles which at that time disturbed the repose of society. It was well if these dissensions produced any good to science to balance the obvious evils which flowed from them. Gascoigne, the inventor of the micrometer, a friend of Horrocks, was killed in the Battle of Marston Moor. Milburn, another friend of Horrocks, who like him detected the errors of Landsberg's astronomical tables, left papers on this subject, which were lost by the coming of the Scotch army into England in 1639. In the Civil War which ensued, the anatomical collections of Harvey were plundered and destroyed. Most of these persons of whom I have lately had to speak were involved in the changes of fortune of the Commonwealth, some on one side and some on the other. Wilkins was made Warden of Wadham by the Committee of Parliament appointed for reforming the University of Oxford, and was, in 1659, made Master of Trinity College, Cambridge, by Richard Cromwell, but ejected thence the year following, upon the restoration of the 396 royal sway. Seth Ward, who was a Fellow of Sidney College, Cambridge, was deprived of his fellowship by the Parliamentary Committee, but at a later period, 1649, he took the engagement to be faithful to the Commonwealth and became Savilian Professor of Astronomy at Oxford. Wallis held a fellowship of Queen's College, Cambridge, but vacated it by marriage. He was afterwards much employed by the royal party in deciphering secret writings, in which art he had peculiar skill. Yet he was appointed by the Parliamentary Commissioners Savilian Professor of Geometry at Oxford, in which situation he was continued by Charles Roman II. After his restoration, Christopher Wren was somewhat later, and escaped these changes. He was chosen Fellow of All Souls in 1652 and succeeded Ward as Savilian Professor of Astronomy. These men, along with Boyle and several others, formed themselves into a club which they called the Philosophical or the Invisible College, and met from about the year 1645, sometimes in London and sometimes in Oxford, according to the changes of fortune and residence of the members. Hooke went to Christ Church, Oxford, in 1663, where he was patronized by Boyle, Ward, and Wallis, and when the Philosophical College resumed its meetings in London, after the Restoration as the Royal Society, Hooke was made curator of experiments. Halley was of the next generation and comes after Newton. He studied at Queen's College, Oxford, in 1673, but was at first a man of some fortune and not engaged in any official situation. His talents and zeal, however, made him an active and effective ally in the promotion of science. The connection of the persons of whom we have been speaking has a bearing on our subject, for it led, historically speaking, to the publication of Newton's discoveries in physical astronomy. Rightly to propose a problem is no inconsiderable step to its solution, and it was undoubtedly a great advance towards the true theory of the universe to consider the motion of the planets round the sun as a mechanical question, to be solved by a reference to the laws of motion and by the use of mathematics. So far the English philosophers appear to have gone before the time of Newton. Hooke, indeed, when the doctrine of gravitation was published, asserted that he had discovered it previously to Newton, and though this pretension could not be maintained, he certainly had perceived that the thing to be done was to determine the effect of a central force in producing curvilinear motion, which effect, as we have already seen, he illustrated by experiment as early as 1666. Hooke had also spoken more clearly on this subject, 397, in an attempt to prove the motion of the Earth from observations, published in 1674. In this, he distinctly states that the planets would move in straight lines if they were not deflected by central forces, and that the central attractive power increases in approaching the center in certain degrees, dependent on the distance. Now what these degrees are, he adds, I have not yet experimentally verified, but he ventures to promise to anyone who succeeds in this undertaking a discovery of the cause of the heavenly motions. He asserted, in conversation to Halley and Wren, that he had solved this problem, but his solution was never produced. The proposition that the attractive force of the sun varies inversely as the square of the distance from the center had already been divined, if not fully established. If the orbits of the planets were circles, this proportion of the forces might be deduced in the same manner as the propositions concerning circular motion, which Huygens published in 1673, yet it does not appear that Huygens made this application of his principles. Newton, however, had already made this step some years before this time. Accordingly, he says in a letter to Halley, on Hooke's claim to this discovery, when Hyginus put out his Horologium Oscillatorium, a copy being presented to me, in my letter of thanks I gave those rules in the end thereof a particular commendation for their usefulness in computing the forces of the moon from the earth, and the earth from the sun. He says, moreover, I am almost confident by circumstances that Sir Christopher Wren knew the duplicate proportion when I gave him a visit, and then Mr. Hooke, by his book Cometa, will prove the last of us three that knew it. Hooke's Cometa was published in 1678. These inferences were all connected with Kepler's law that the times are in the sesquiplicate ratio of the major axes of the orbits. But Halley had also been led to the duplicate proportion by another train of reasoning, namely, by considering the force of the sun as an emanation, which must become more feeble in proportion to the increased spherical surface over which it is diffused, and therefore in the inverse proportion of the square of the distances. In this view of the matter, however, the difficulty was to determine what would be the motion of a body acted on by such a force, when the orbit is not circular but oblong. The investigation of this case was a problem which, we can 398 easily conceive, must have appeared of very formidable complexity while it was unsolved, and the first of its kind. Accordingly, Halley, as his biographer says, finding himself unable to make it out in any geometrical way, first applied to Mr. Hooke and Sir Christopher Wren, and meeting with no assistance from either of them, he went to Cambridge in August 1684, to Mr. Newton, who supplied him fully with what he had so ardently sought. Note 24/7. Bullialdus, in 1645, had asserted that the force by which the sun, prehendit at Harpagat, takes hold of and grapples the planets must be as the inverse square of the distance. A paper of Halley's in the Philosophical Transactions for January 1686, professedly inserted as a preparation for Newton's work, contains some arguments against the Cartesian hypothesis of gravity, which seem to imply that Cartesian opinions had some footing among English philosophers. And we are told by Whiston, Newton's successor in his professorship at Cambridge, that Cartesianism formed a part of the studies of that place. Indeed, Roholt's physics was used as a classbook at that university long after the time of which we are speaking, but the peculiar Cartesian doctrines which it contained were soon superseded by others. With regard, then, to this part of the discovery, that the force of the sun follows the inverse duplicate proportion of the distances, we see that several other persons were on the verge of it at the same time with Newton, though he alone possessed that combination of distinctness of thought and power of mathematical invention, which enabled him to force his way across the barrier. But another, and so far as we know, an earlier train of thought, led by a different path to the same result, and it was the convergence of these two lines of reasoning that brought the conclusion to men's minds with irresistible force. I speak now of the identification of the force which retains the moon in her orbit with the force of gravity by which bodies fall at the Earth's surface. In this comparison, Newton had, so far as I am aware, no forerunner. We are now, therefore, arrived at the point at which the history of Newton's great discovery properly begins. 399. Chapter 2. The inductive epoch of Newton's discovery of the universal gravitation of matter, according to the law of the inverse square of the distance. In order that we may the more clearly consider the bearing of this, the greatest scientific discovery ever made, we shall resolve it into the partial propositions of which it consists. Of these, we may enumerate 5. The doctrine of universal gravitation asserts: 1. That the force by which the different planets are attracted to the sun is in the inverse proportion of the squares of their distances. 2. That the force by which the same planet is attracted to the sun, in different parts of its orbit, is also in the inverse proportion of the squares of the distances. 3. That the Earth also exerts such a force on the moon, and that this force is identical with the force of gravity. 4. That bodies thus act on other bodies, besides those which revolve round them. Thus, that the sun exerts such a force on the moon and satellites, and that the planets exert such forces on one another. 5. That this force, thus exerted by the general masses of the sun, earth, and planets, arises from the attraction of each particle of these masses, which attraction follows the above law and belongs to all matter alike. The history of the establishment of these 5 truths will be given in order. One sun's force on different planets with regard to the first of the above 5 propositions, that the different planets are attracted to the sun by a force which is inversely as the square of the distance. Newton had so far been anticipated that several persons had discovered it to be true or nearly true. That is, they had discovered that if the orbits of the planets were circles, the proportions of the central force to the inverse square of the distance would follow from Kepler's third law of the sesquiplicate proportion of the periodic times. As we have seen, Huygens' theorems would have proved this if they had been so applied. Wren knew it. Hooke not only knew it, but claimed a prior knowledge to Newton, and Halley had satisfied himself that it was at 400, least nearly true, before he visited Newton. Hooke was reported to Newton at Cambridge as having applied to the Royal Society to do him justice with regard to his claims, but when Halley wrote and informed Newton, in a letter dated June 29, 1686, that Hooke's conduct had been represented in worse colors than it ought, Newton inserted in his book a notice of these his predecessors, in order, as he said, to compose the dispute. This notice appears in a scholium to the 4th proposition of the Principia, which states the general law of revolutions in circles. The case of the 6th corollary, Newton there says, obtains in the celestial bodies, as has been separately inferred by our countrymen, Wren, Hooke, and Halley. He soon after names Huygens, who, in his excellent treatise De Horologio Oscillatorio, compares the force of gravity with the centrifugal forces of revolving bodies. The two steps requisite for this discovery were to propose the motions of the planets as simply a mechanical problem, and to apply mathematical reasoning so as to solve this problem, with reference to Kepler's third law considered as a fact. The former step was a consequence of the mechanical discoveries of Galileo and his school, the result of the firm and clear place which these gradually obtained in men's mind, and of the utter abolition of all the notions of solid spheres by Kepler. The mathematical step required no small mathematical powers, as appears when we consider that this was the first example of such a problem, and that the method of limits under all its forms was at this time in its infancy, or rather, at its birth. Accordingly, even this step, though much the easiest in the path of deduction, no one before Newton completely executed. To force in different points of an orbit the inference of the law of the force from Kepler's two laws concerning the elliptical motion was a problem quite different from the preceding, and much more difficult. But the dispute with respect to priority in the two propositions was intermingled. Borelli, in 1666, had, as we have seen, endeavored to reconcile the general form of the orbit with the notion of a central attractive force, by taking centrifugal force into the account. And Hooke, in 1679, had asserted that the result of the law of the inverse square in the force of the earth would be an ellipse, or a curve like an ellipse. But it does not appear that this was anything more than 401, a conjecture. Halley says that Hooke, in 1683, told him he had demonstrated all the laws of the celestial motions by the reciprocally duplicate proportion of the force of gravity. But that, being offered 40 shillings by Sir Christopher Wren to produce such a demonstration, his answer was that he had it, but would conceal it for some time, that others, trying and failing, might know how to value it when he should make it public. Halley, however, truly observes that after the publication of the demonstration in the Principia, this reason no longer held, and adds, "I have plainly told him that unless he produce another differing demonstration, and let the world judge of it, neither I nor anyone else can believe it." Newton allows that Hooke's assertions in 1679 gave occasion to his investigation on this point of the theory. His demonstration is contained in the second and third sections of the Principia. He first treats of the general law of central forces in any curve, and then, on account, as he states, of the application to the motion of the heavenly bodies, he treats of the case of force varying inversely as the square of the distance, in a more diffuse manner. In this, as in the former portion of his discovery, the two steps were the proposing the heavenly motions as a mechanical problem and the solving this problem. Borelli and Hooke had certainly made the former step with considerable distinctness, but the mathematical solution required no common inventive power. Newton seems to have been much ruffled by Hooke's speaking slightly of the value of this second step, and is moved in return to deny Hooke's pretensions with some asperity and to assert his own. He says in a letter to Halley, "Borelli did something in it and wrote modestly. He, Hooke, has done nothing, and yet written in such a way as if he knew, and had sufficiently hinted all but what remained to be determined by the drudgery of calculations and observations, excusing himself from that labor by reason of his other business, whereas he should rather have excused himself by reason of his inability, for it is very plain, by his words, he knew not how to go about it. Now is not this very fine? Mathematicians that find out, settle, and do all the business must content themselves with being nothing but dry calculators and drudges, and another that does nothing but pretend and grasp at all things must carry away all the inventions, as well of those that were to follow him as of those that 402 went before." This was written, however, under the influence of some degree of mistake, and in a subsequent letter Newton says, "Now I understand he was in some respects misrepresented to me. I wish I had spared the postscript to my last," in which is the passage just quoted. We see, by the melting away of rival claims, the undivided honor which belongs to Newton as the real discoverer of the proposition now under notice. We may add that in the sequel of the third section of the Principia, he has traced its consequences and solved various problems flowing from it with his usual fertility and beauty of mathematical resource, and has there shown the necessary connection of Kepler's third law with his first and second. 3 moons' gravity to the Earth, though others had considered cosmical forces as governed by the general laws of motion. It does not appear that they had identified such forces with the force of terrestrial gravity. This step in Newton's discoveries has generally been the most spoken of by superficial thinkers, and a false kind of interest has been attached to it, from the story of its being suggested by the fall of an apple. The popular mind is caught by the character of an eventful narrative which the anecdote gives to this occurrence, and by the antithesis which makes a profound theory appear the result of a trivial accident. How inappropriate is such a view of the matter we shall soon see. The narrative of the progress of Newton's thoughts is given by Pemberton, who had it from Newton himself, in his preface to his view of Newton's philosophy, and by Voltaire, who had it from Mrs. Conduit, Newton's niece. The first thoughts, we are told, which gave rise to his Principia, he had when he retired from Cambridge in 1666, on account of the plague. He was then 24 years of age. As he sat alone in a garden, he fell into a speculation on the power of gravity, that as this power is not found sensibly diminished at the remotest distance from the center of the earth to which we can rise, neither at the tops of the loftiest buildings, nor even on the summits of the highest mountains, it appeared to him reasonable to conclude that this power must extend much further than was usually thought. Why not as high as the moon? Said he to himself, and if so, her motion must be influenced by it. Perhaps she is retained in her orbit thereby. The thought of cosmical gravitation was thus distinctly brought into being, and Newton's superiority here was that he conceived the 403 celestial motions as distinctly as the motions which took place close to him, considered them as of the same kind, and applied the same rules to each without hesitation or obscurity. But so far, this thought was merely a guess. Its occurrence showed the activity of the thinker, but to give it any value, it required much more than a why not, a perhaps. Accordingly, Newton's why not was immediately succeeded by his if so, what then? His reasoning was that if gravity reached to the moon, it is probably of the same kind as the central force of the sun and follows the same rule with respect to the distance. What is this rule? We have already seen that, by calculating from Kepler's laws and supposing the orbits to be circles, the rule of the force appears to be the inverse duplicate proportion of the distance. And this, which had been current as a conjecture among the previous generation of mathematicians, Newton had already proved by indisputable reasonings, and was thus prepared to proceed in his train of inquiry. If then, he went on, pursuing his train of thought, the Earth's gravity extend to the moon, diminishing according to the inverse square of the distance, will it, at the moon's orbit, be of the proper magnitude for retaining her in her path? Here again came in calculation, and a calculation of extreme interest, for how important and how critical was the decision which depended on the resulting numbers. According to Newton's calculations, made at this time, the moon by her motion in her orbit was deflected from the tangent every minute through a space of 13 feet. But by noticing the space through which bodies would fall in 1 minute at the Earth's surface, and supposing this to be diminished in the ratio of the inverse square, it appeared that gravity would, at the moon's orbit, draw a body through more than 15 feet. The difference seems small, the approximation encouraging, the theory plausible. A man in love with his own fancies would readily have discovered or invented some probable cause of this difference. But Newton acquiesced in it as a disproof of his conjecture, and laid aside at that time any further thoughts of this matter, thus resigning a favorite hypothesis, with a candor and openness to conviction not inferior to Kepler, though his notion had been taken up on far stronger and sounder grounds than Kepler dealt in, and without even, so far as we know, Kepler's regrets and struggles. Nor was this levity or indifference. The idea, though thus laid aside, was not finally condemned and abandoned. When Hooke, in 1679, contradicted Newton on the subject of the curve described by a falling body, and asserted it to be an ellipse, Newton, 404, was led to investigate the subject, and was then again conducted, by another road, to the same law of the inverse square of the distance. This naturally turned his thoughts to his former speculations. Was there really no way of explaining the discrepancy which this law gave, when he attempted to reduce the moon's motion to the action of gravity? A scientific operation then recently completed gave the explanation at once. He had been mistaken in the magnitude of the Earth, and consequently in the distance of the moon, which is determined by measurements of which the Earth's radius is the base. He had taken the common estimate, current among geographers and seamen, that 60 English miles are contained in 1 degree of latitude. But Picard, in 1670, had measured the length of a certain portion of the meridian in France, with far greater accuracy than had yet been attained, and this measure enabled Newton to repeat his calculations with these amended data. We may imagine the strong curiosity which he must have felt as to the result of these calculations. His former conjecture was now found to agree with the phenomena to a remarkable degree of precision. This conclusion, thus coming after long doubts and delays, and falling in with the other results of mechanical calculation for the solar system, gave a stamp from that moment to his opinions, and through him to those of the whole philosophical world. Dr. Robison, Mechanical Philosophy, p. 288, says that Newton, having become a member of the Royal Society, there learned the accurate measurement of the earth by Picard, differing very much from the estimation by which he had made his calculations in 1666. And M. Biot, in his Life of Newton, published in the Biographie Universelle, says, according to conjecture, about the month of June, 1682, Newton being in London at a meeting of the Royal Society, mention was made of the new measure of a degree of the earth's surface, recently executed in France by Picard, and great praise was given to the care which had been employed in making this measure exact. I had adopted this conjecture as a fact in my first edition, but it has been pointed out by Prof. Rigaud, Historical S., on the first publication of the Principia, 1838, that Picard's measurement was probably well known to the Fellows of the Royal Society as early as 1675, there being an account of the results of it given in the Philosophical Transactions for that year. Newton appears to have discovered the method of determining that a body might describe an ellipse when acted upon by a force residing in the focus, and varying 405, inversely as the square of the distance, in 1679, upon occasion of his correspondence with Hooke. In 1684, at Halle's request, he returned to the subject, and in February 1685 there was inserted in the Register of the Royal Society a paper of Newton's, Issae Newtoni Propositions de Motu, which contained some of the principal propositions of the first 2 books of the Principia. This paper, however, does not contain the proposition Lunam graviter in terram, nor any of the other propositions of the 3rd book. The Principia was printed in 1686 and 7, apparently at the expense of Halley. On the 6th of April, 1687, the 3rd book was presented to the Royal Society. It does not appear, I think, that before Newton, philosophers in general had supposed that terrestrial gravity was the very force by which the moon's motions are produced. Men had, as we have seen, taken up the conception of such forces and had probably called them gravity. But this was done only to explain, by analogy, what kind of forces they were, just as at other times they compared them with magnetism. And it did not imply that terrestrial gravity was a force which acted in the celestial spaces. After Newton had discovered that this was so, the application of the term gravity did undoubtedly convey such a suggestion. But we should err if we inferred from this coincidence of expression that the notion was commonly entertained before him. Thus Huygens appears to use language which may be mistaken, when he says that Borelli was of opinion that the primary planets were urged by gravity towards the sun and the satellites towards the primaries. The notion of terrestrial gravity, as being actually a cosmical force, is foreign to all Borelli's speculations. But Horrocks, as early as 1635, appears to have entertained the true view on this subject, although vitiated by Keplerian errors concerning the connection between the rotation of the central body and its effect on the body which revolves about it. Thus he says that the emanation of the earth carries a projected stone along with the motion of the earth, just in the same way as it carries the moon in her orbit, and that this force is greater on the stone than on the moon, because the distance is less. Note 31/7. I have found no instance in which the word is so used by him. Note 32/7. Astronomia Kepleriana Defensa et Promota, cap. 2. See further on this subject in the additions to this volume. The proposition in which Newton has stated the discovery of which we are now speaking is the fourth of his third book, that the moon gravitates to the Earth, and by the force of gravity is perpetually, 406, deflected from a rectilinear motion and retained in her orbit. The proof consists in the numerical calculation, of which he only gives the elements and points out the method. But we may observe that no small degree of knowledge of the way in which astronomers had obtained these elements and judgment in selecting among them were necessary. Thus, the mean distance of the moon had been made as little as 56.5 semi-diameters of the Earth by Tycho and as much as 62.5 by Kircher. Newton gives good reasons for adopting 61. The term gravity and the expression to gravitate, which, as we have just seen, Newton uses of the moon, were to receive a still wider application in consequence of his discoveries. But in order to make this extension clearer, we consider it as a separate step. For mutual attraction of all the celestial bodies, if the preceding parts of the discovery of gravitation were comparatively easy to conjecture and difficult to prove, this was much more the case with the part of which we have now to speak, the attraction of other bodies, besides the central ones, upon the planets and satellites. If the mathematical calculation of the unmixed effect of a central force required transcendent talents, how much must the difficulty be increased when other influences prevented those first results from being accurately verified, while the deviations from accuracy were far more complex than the original action? If it had not been that these deviations, though surprisingly numerous and complicated in their nature, were very small in their quantity, it would have been impossible for the intellect of man to deal with the subject. As it was, the struggle with its difficulties is even now a matter of wonder. The conjecture that there is some mutual action of the planets had been put forth by Hooke in his attempt to prove the motion of the Earth, 1674. It followed, he said, from his doctrine that not only the sun and moon act upon the course and motion of the Earth, but that Mercury, Venus, Mars, Jupiter, and Saturn have also, by their attractive power, a considerable influence upon the motion of the Earth, and the Earth in like manner powerfully affects the motions of those bodies. And Borelli, in attempting to form theories of the satellites of Jupiter, had seen, though dimly and confusedly, the probability that the sun would disturb the motions of these bodies. Thus he says, cap. 14. How can we believe that the Medicean globes are not, like other planets, impelled with a greater velocity when they approach the sun, and thus they are acted upon by two moving forces, one of 407 which produces their proper revolution about Jupiter, the other regulates their motion round the sun. And in another place, cap. 20, he attempts to show an effect of this principle upon the inclination of the orbit, though, as might be expected, without any real result. The case which most obviously suggests the notion that the sun exerts a power to disturb the motions of secondary planets about primary ones might seem to be our own moon, for the great inequalities which had hitherto been discovered had all, except the first, or elliptical anomaly, a reference to the position of the sun. Nevertheless, I do not know that anyone had attempted thus to explain the curiously irregular course of the Earth's attendant. To calculate, from the disturbing agency, the amount of the irregularities was a problem which could not, at any former period, have been dreamt of as likely to be at any time within the verge of human power. Newton both made the step of inferring that there were such forces, and, to a very great extent, calculated the effects of them. The inference is made on mechanical principles, in the sixth theorem of the third book of the Principia, that the moon is attracted by the sun, as the Earth is, that the satellites of Jupiter and Saturn are attracted as the primaries are, in the same manner and with the same forces. If this were not so, it is shown that these attendant bodies could not accompany the principal ones in the regular manner in which they do. All those bodies at equal distances from the sun would be equally attracted. But the complexity which must occur in tracing the results of this principle will easily be seen. The satellite and the primary, though nearly at the same distance, and in the same direction from the sun, are not exactly so. Moreover, the difference of the distances and of the directions is perpetually changing, and if the motion of the satellite be elliptical, the cycle of change is long and intricate. On this account alone the effects of the sun's action will inevitably follow cycles as long and as perplexed as those of the positions. But on another account they will be still more complicated. For in the continued action of a force, the effect which takes place at first modifies and alters the effect afterwards. The result at any moment is the sum of the results in preceding instants. And since the terms, in this series of instantaneous effects, follow very complex rules, the sums of such series will be, it might be expected, utterly incapable of being reduced to any manageable degree of simplicity. It certainly does not appear that anyone but Newton could make 408 any impression on this problem or course of problems. No one for 60 years after the publication of the Principia, and with Newton's methods, no one up to the present day, had added anything of any value to his deductions. We know that he calculated all the principal lunar inequalities. In many of the cases, he has given us his processes, in others, only his results. But who has presented, in his beautiful geometry, or deduced from his simple principles, any of the inequalities which he left untouched? The ponderous instrument of synthesis, so effective in his hands, has never since been grasped by one who could use it for such purposes, and we gaze at it with admiring curiosity, as on some gigantic implement of war, which stands idle among the memorials of ancient days, and makes us wonder what manner of man he was who could wield as a weapon what we can hardly lift as a burden. It is not necessary to point out in detail the sagacity and skill which mark this part of the Principia. The mode in which the author obtains the effect of a disturbing force in producing a motion of the apse of an elliptical orbit, the 9th section of the first book, has always been admired for its ingenuity and elegance. The general statement of the nature of the principal inequalities produced by the sun in the motion of a satellite, given in the 66th proposition, is, even yet, one of the best explanations of such action. And the calculations of the quantity of the effects in the third book. For instance, the variation of the moon, the motion of the nodes and its inequalities, the change of inclination of the orbitar, full of beautiful and efficacious artifices. But Newton's inventive faculty was exercised to an extent greater than these published investigations show. In several cases, he has suppressed the demonstration of his method, and given us the result only, either from haste or from mere weariness, which might well overtake one who, while he was struggling with facts and numbers, with difficulties of conception and practice, was aiming also at that geometrical elegance of exposition, which he considered as alone fit for the public eye. Thus, in stating the effect of the eccentricity of the moon's orbit upon the motion of the apogee, he says, "The computations, as too intricate and embarrassed with approximations, I do not choose to introduce. The computations of the theoretical motion of the moon being thus difficult, and its irregularities numerous and complex, we may ask, 409, whether Newton's reasoning was sufficient to establish this part of his theory, namely, that her actual motions arise from her gravitation to the sun. And to this we may reply that it was sufficient for that purpose, since it showed that, from Newton's hypothesis, inequalities must result, following the laws which the moon's inequalities were known to follow, since the amount of the inequalities given by the theory agreed nearly with the rules which astronomers had collected from observation, and since, by the very intricacy of the calculation, it was rendered probable that the first results might be somewhat inaccurate, and thus might give rise to the still remaining differences between the calculations and the facts. A progression of the apogee, a regression of the nodes, and besides the elliptical or first inequality, an inequality following the law of the evection or second inequality discovered by Ptolemy. Another, following the law of the variation discovered by Tycho, were pointed out in the first edition of the Principia as the consequences of the theory. Moreover, the quantities of these inequalities were calculated and compared with observation with the utmost confidence, and the agreement in most instances was striking. The variation agreed with Halley's recent observations within a minute of a degree. The mean motion of the nodes in a year agreed within less than 1/100th of the whole. The equation of the motion of the nodes also agreed well. The inclination of the plane of the orbit to the ecliptic, and its changes, according to the different situations of the nodes, likewise agreed. The evection has been already noticed as encumbered with peculiar difficulties. Here the accordance was less close. The difference of the daily progress of the apogee in syzygy and its daily regress in quadratures is, Newton says, 4 1/4 minutes by the tables, 6 2/3 by our calculation. He boldly adds, "I suspect this difference to be due to the fault of the tables." In the second edition, 1711, he added the calculation of several other inequalities as the annual equation, also discovered by Tycho, and he compared them with more recent observations made by Flamsteed at Greenwich. But even in what has already been stated, it must be allowed that there is a wonderful accordance of theory with phenomena, both being very complex in the rules which they educe. The same theory which gave these inequalities in the motion of the moon produced by the disturbing force of the sun, gave also 410 corresponding inequalities in the motions of the satellites of other planets, arising from the same cause, and likewise pointed out the necessary existence of irregularities in the motions of the planets arising from their mutual attraction. Newton gave propositions by which the irregularities of the motion of Jupiter's moons might be deduced from those of our own, and it was shown that the motions of their nodes would be slow by theory, as Flamsteed had found it to be by observation. But Newton did not attempt to calculate the effect of the mutual action of the planets, though he observes that in the case of Jupiter and Saturn, this effect is too considerable to be neglected. And he notices in the second edition that it follows from the theory of gravity that the aphelia of Mercury, Venus, the Earth, and Mars slightly progress. In one celebrated instance, indeed, the deviation of the theory of the Principia from observation was wider and more difficult to explain. And as this deviation for a time resisted the analysis of Euler and Clairaut, as it had resisted the synthesis of Newton, it at one period staggered the faith of mathematicians in the exactness of the law of the inverse square of the distance. I speak of the motion of the moon's apogee, a problem which has already been referred to, and in which Newton's method, and all the methods which could be devised for some time afterwards, gave only half the observed motion, a circumstance which arose, as was discovered by Clairaut in 1750, from the insufficiency of the method of approximation. Newton does not attempt to conceal this discrepancy. After calculating what the motion of apse would be, upon the assumption of a disturbing force of the same amount as that which the sun exerts on the moon, he simply says, "The apse of the moon moves about twice as fast." Note 42/7, B. I Prop 44, second edit. There is reason to believe, however, that Newton had, in his unpublished calculations, rectified this discrepancy. The difficulty of doing what Newton did in this branch of the subject, and the powers it must have required, may be judged of from what has already been stated, that no one, with his methods, has yet been able to add anything to his labors. Few have undertaken to illustrate what he has written, and no great number have understood it throughout. The extreme complication of the forces, and of the conditions under which they act, makes the subject by far the most thorny walk of mathematics. It is necessary to resolve the action 411 into many elements, such as can be separated, to invent artifices for dealing with each of these, and then to recompound the laws thus obtained into one common conception. The moon's motion cannot be conceived without comprehending a scheme more complex than the Ptolemaic epicycles and eccentrics in their worst form. And the component parts of the system are not, in this instance, mere geometrical ideas, requiring only a distinct apprehension of relations of space in order to hold them securely. They are the foundations of mechanical notions, and require to be grasped so that we can apply to them sound mechanical reasonings. Newton's successors, in the next generation, abandoned the hope of imitating him in this intense mental effort. They gave the subject over to the operation of algebraical reasoning, in which symbols think for us, without our dwelling constantly upon their meaning, and obtain for us the consequences which result from the relations of space and the laws of force, however complicated be the conditions under which they are combined. Even Newton's countrymen, though they were long before they applied themselves to the method thus opposed to his, did not produce anything which showed that they had mastered or could retrace the Newtonian investigations. Thus the problem of three bodies, treated geometrically, belongs exclusively to Newton, and the proofs of the mutual action of the sun, planets, and satellites, which depend upon such reasoning, could not be discovered by anyone but him. Note 43/7, see the history of the problem of three bodies ante in Book 6, Chapter Roman 6, Sect 7. But we have not yet done with his achievements on this subject. For some of the most remarkable and beautiful of the reasonings which he connected with this problem belong to the next step of his generalization. 5. Mutual attraction of all particles of matter, that all the parts of the universe are drawn and held together by love, or harmony, or some affection to which, among other names, that of attraction may have been given, is an assertion which may very possibly have been made at various times by speculators writing at random and taking their chance of meaning and truth. The authors of such casual dogmas have generally nothing accurate or substantial, either in their conception of the general proposition or in their reference to examples of it, and therefore their doctrines are no concern of ours at present. But among those who were really the first to think of the mutual, 412, attraction of matter, we cannot help noticing Francis Bacon. For his notions were so far from being chargeable with the looseness and indistinctness to which we have alluded, that he proposed an experiment which was to decide whether the facts were so or not, whether the gravity of bodies to the earth arose from an attraction of the parts of matter towards each other, or was a tendency towards the center of the earth. And this experiment is, even to this day, one of the best which can be devised in order to exhibit the universal gravitation of matter. It consists in the comparison of the rate of going of a clock in a deep mine and on a high place. Huygens, in his book De Causa Gravitatis, published in 1690, showed that the earth would have an oblate form, in consequence of the action of the centrifugal force, but his reasoning does not suppose gravity to arise from the mutual attraction of the parts of the earth. The apparent influence of the moon upon the tides had long been remarked, but no one had made any progress in truly explaining the mechanism of this influence, and all the analogies to which reference had been made, on this and similar subjects, as magnetic and other attractions, were rather delusive than illustrative, since they represented the attraction as something peculiar in particular bodies, depending upon the nature of each body. That all such forces, cosmical and terrestrial, were the same single force, and that this was nothing more than the insensible attraction which subsists between one stone and another, was a conception equally bold and grand, and would have been an incomprehensible thought if the views which we have already explained had not prepared the mind for it. But the preceding steps having disclosed, between all the bodies of the universe, forces of the same kind as those which produce the weight of bodies at the earth, and therefore such as exist in every particle of terrestrial matter, it became an obvious question whether such forces did not also belong to all particles of planetary matter, and whether this was not, in fact, the whole account of the forces of the solar system. But supposing this conjecture to be thus suggested, how formidable, on first appearance at least, was the undertaking of verifying it? For if this be so, every finite mass of matter exerts forces which are the result of the infinitely numerous forces of its particles, these forces acting in different directions. It does not appear, at first sight, that the law by which the force is related to the distance will be the same for the particles as it is for the masses, and, in reality, it 413 is not so, except in special cases. And again, in the instance of any effect produced by the force of a body, how are we to know whether the force resides in the whole mass as a unit or in the separate particles? We may reason, as Newton does, that the rule which proves gravity to belong universally to the planets proves it also to belong to their parts. But the mind will not be satisfied with this extension of the rule, except we can find decisive instances and calculate the effects of both suppositions under the appropriate conditions. Accordingly, Newton had to solve a new series of problems suggested by this inquiry, and this he did. These solutions are no less remarkable for the mathematical power which they exhibit than the other parts of the Principia. The propositions in which it is shown that the law of the inverse square for the particles gives the same law for spherical masses have that kind of beauty which might well have justified their being published for their mathematical elegance alone, even if they had not applied to any real case. Great ingenuity is also employed in other instances, as in the case of spheroids of small eccentricity. And when the amount of the mechanical action of masses of various forms has thus been assigned, the sagacity shown in tracing the results of such action in the solar system is truly admirable. Not only the general nature of the effect being pointed out, but its quantity calculated. I speak in particular of the reasonings concerning the figure of the Earth, the tides, the precession of the equinoxes, the regression of the nodes of a ring such as Saturn's, and of some effects which at that time had not been ascertained even as facts of observation. For instance, the difference of gravity in different latitudes and the nutation of the Earth's axis. It is true that in most of these cases, Newton's process could be considered only as a rude approximation. In one, the precession, he committed an error, and in all, his means of calculation were insufficient. Indeed, these are much more difficult investigations than the problem of three bodies, in which 3 points act on each other by explicit laws. Up to this day, the resources of modern analysis have been employed upon some of them with very partial success, and the facts in all of them required to be accurately ascertained and measured, a process which is not completed even now. Nevertheless, the form and nature of the conclusions which Newton did obtain were such as to inspire a strong confidence in the competency of his theory to explain 414 all such phenomena as have been spoken of. We shall afterwards have to speak of the labors undertaken in order to examine the phenomena more exactly, to which the theory gave occasion. Thus, then, the theory of the universal mutual gravitation of all the particles of matter, according to the law of the inverse square of the distances, was conceived, its consequences calculated, and its results shown to agree with phenomena. It was found that this theory took up all the facts of astronomy as far as they had hitherto been ascertained. While it pointed out an interminable vista of new facts, too minute or too complex for observation alone to disentangle, but capable of being detected when theory had pointed out their laws, and of being used as criteria or confirmations of the truth of the doctrine. For the same reasoning which explained the evection, variation, and annual equation of the moon, showed that there must be many other inequalities besides these, since these resulted from approximate methods of calculation in which small quantities were neglected. And it was known that, in fact, the inequalities hitherto detected by astronomers did not give the place of the moon with satisfactory accuracy, so that there was room, among these hitherto untractable irregularities, for the additional results of the theory. To work out this comparison was the employment of the succeeding century, but Newton began it. Thus, at the end of the proposition in which he asserts that all the lunar motions and their irregularities follow from the principles here stated, he makes the observation which we have just made, and gives, as examples, the different motions of the apogee and nodes, the difference of the change of the eccentricity, and the difference of the moon's variation, according to the different distances of the sun. But this inequality, he says, in astronomical calculations, is usually referred to the prostapheresis of the moon and confounded with it. Reflections on the discovery such, then, is the great Newtonian induction of universal gravitation, and such its history. It is indisputably and incomparably the greatest scientific discovery ever made, whether we look at the advance which it involved, the extent of the truth disclosed, or the fundamental and satisfactory nature of this truth. As to the first point, we may observe that any one of the 5 steps into which we have separated the doctrine would of itself have been considered as an important advance, would have conferred distinction on the persons who made it, and the time to which it belonged. All 415, the 5 steps made at once, formed not a leap, but a flight, not an improvement merely, but a metamorphosis, not an epoch, but a termination. Astronomy passed at once from its boyhood to mature manhood. Again, with regard to the extent of the truth, we obtain as wide a generalization as our physical knowledge admits, when we learn that every particle of matter, in all times, places, and circumstances, attracts every other particle in the universe by one common law of action. And by saying that the truth was of a fundamental and satisfactory nature, I mean that it assigned, not a rule merely, but a cause, for the heavenly motions, and that kind of cause which most eminently and peculiarly we distinctly and thoroughly conceive, namely, mechanical force. Kepler's laws were merely formal rules, governing the celestial motions according to the relations of space, time, and number. Newton's was an asterisk causal law, referring these motions to mechanical reasons. It is no doubt conceivable that future discoveries may both extend and further explain Newton's doctrines, may make gravitation a case of some wider law, and may disclose something of the mode in which it operates. Questions with which Newton himself struggled. But in the meantime, few persons will dispute that both in generality and profundity, both in width and depth, Newton's theory is altogether without a rival or neighbor. Note 47/7. The value and nature of this step have long been generally acknowledged wherever science is cultivated. Yet it would appear that there is, in one part of Europe, a school of philosophers who contest the merit of this part of Newton's discoveries. Kepler, says a celebrated German metaphysician *, discovered the laws of free motion, a discovery of immortal glory. It has since been the fashion to say that Newton first found out the proof of these rules. It has seldom happened that the glory of the first discoverer has been more unjustly transferred to another person. It may appear strange that anyone in the present day should hold such language, but if we examine the reasons which this author gives, they will be found, I think, to amount to this: that his mind is in the condition in which Kepler's was, and that the whole range of mechanical ideas and modes of conception which made the transition from Kepler and Newton possible are extraneous to the domain of his philosophy. Even this author, however, if I understand him rightly, recognizes Newton as the author of the doctrine of perturbations. I have given a further account of these views in a memoir on Hegel's criticism of Newton's Principia. Cambridge Transactions, 1849. Hegel Encyclopedia, section 270. The requisite conditions of such a discovery in the mind of its author were, in this as in other cases, the idea and its comparison with facts, the conception of the law, and the molding this conception in such a form as to correspond with known realities. The idea of mechanical, 416, force as the cause of the celestial motions, had, as we have seen, been for some time growing up in men's minds, had gone on becoming more distinct and more general, and had, in some persons, approached the form in which it was entertained by Newton. Still, in the mere conception of universal gravitation, Newton must have gone far beyond his predecessors and contemporaries, both in generality and distinctness, and in the inventiveness and sagacity with which he traced the consequences of this conception. He was, as we have shown, without a rival and almost without a second. As to the facts which he had to include in his law, they had been accumulating from the very birth of astronomy. But those which he had more peculiarly to take hold of were the facts of the planetary motions as given by Kepler, and those of the moon's motions as given by Tycho Brahe and Jeremy Horrocks. We find here occasion to make a remark which is important in its bearing on the nature of progressive science. What Newton thus used and referred to as facts were the laws which his predecessors had established. What Kepler and Horrocks had put forth as theories were now established truths fit to be used in the construction of other theories. It is in this manner that one theory is built upon another, that we rise from particulars to generals, and from one generalization to another, that we have, in short, successive steps of induction. As Newton's laws assumed Kepler's laws assumed as facts the results of the planetary theory of Ptolemy, and thus the theories of each generation in the scientific world are, when thoroughly verified and established, the facts of the next generation. Newton's theory is the circle of generalization which includes all the others, the highest point of the inductive ascent, the catastrophe of the philosophically drama to which Plato had prologized, the point to which men's minds had been journeying for 2,000 years. Character of Newton. It is not easy to anatomize the constitution and the operations of the mind which make such an advance in knowledge. Yet we may observe that there must exist in it, in an eminent degree, the elements which compose the mathematical talent. It must possess distinctness of intuition, tenacity and facility in tracing logical connection, fertility of invention, and a strong tendency to generalization. It is easy to discover indications of these characteristics in Newton. The distinctness of his intuitions of space, and we may add of force also, was seen in the amusements of his youth, in his constructing clocks and mills, carts and dials, as well as the facility with which he, 417, mastered geometry. This fondness for handicraft employments, and for making models and machines, appears to be a common prelude of excellence in physical science, probably on this very account, that it arises from the distinctness of intuitive power with which the child conceives the shapes and the working of such material combinations. Newton's inventive power appears in the number and variety of the mathematical artifices and combinations which he devised, and of which his books are full. If we conceive the operation of the inventive faculty in the only way in which it appears possible to conceive it, that, while some hidden source supplies a rapid stream of possible suggestions, the mind is on the watch to seize and detain any one of these which will suit the case in hand, allowing the rest to pass by and be forgotten, we shall see what extraordinary fertility of mind is implied by so many successful efforts. What an innumerable host of thoughts must have been produced to supply so many that deserved to be selected. And since the selection is performed by tracing the consequences of each suggestion, so as to compare them with the requisite conditions, we see also what rapidity and certainty in drawing conclusions the mind must possess as a talent, and what watchfulness and patience as a habit. The hidden fountain of our unbidden thoughts is for us a mystery, and we have, in our consciousness, no standard by which we can measure our own talents. But our acts and habits are something of which we are conscious. And we can understand, therefore, how it was that Newton could not admit that there was any difference between himself and other men, except in his possession of such habits as we have mentioned, perseverance and vigilance. When he was asked how he made his discoveries, he answered, by always thinking about them. And at another time he declared that if he had done anything, it was due to nothing but industry and patient thought. I keep the subject of my inquiry constantly before me, and wait till the first dawning opens gradually, by little and little, into a full and clear light. No better account can be given of the nature of the mental effort which gives to the philosopher the full benefit of his powers. But the natural powers of men's minds are not on that account the less different. There are many who might wait through ages of darkness without being visited by any dawn. The habit to which Newton thus, in some sense, owed his 418 discoveries, this constant attention to the rising thought and development of its results in every direction, necessarily engaged and absorbed his spirit, and made him inattentive and almost insensible to external impressions and common impulses. The stories which are told of his extreme absence of mind probably refer to the 2 years during which he was composing his Principia, and thus following out a train of reasoning the most fertile, the most complex, and the most important, which any philosopher had ever had to deal with. The magnificent and striking questions, which, during this period, he must have had daily rising before him, the perpetual succession of difficult problems of which the solution was necessary to his great object, may well have entirely occupied and possessed him. He existed only to calculate and to think. Often, lost in meditation, he knew not what he did, and his mind appeared to have quite forgotten its connection with the body. His servant reported that on rising in a morning, he frequently sat a large portion of the day, half-dressed, on the side of his bed, and that his meals waited on the table for hours before he came to take them. Even with his transcendent powers, to do what he did was almost irreconcilable with the common conditions of human life, and required the utmost devotion of thought, energy of effort, and steadiness of will, the strongest character, as well as the highest endowments which belong to man. Newton has been so universally considered as the greatest example of a natural philosopher that his moral qualities, as well as his intellect, have been referred to as models of the philosophical character. And those who love to think that great talents are naturally associated with virtue have always dwelt with pleasure upon the views given of Newton by his contemporaries, for they have uniformly represented him as candid and humble, mild and good. We may take as an example of the impressions prevalent about him in his own time the expressions of Thomson in the poem on his death. 419, say ye who best can tell, ye happy few, who saw him in the softest lights of life, all unwithheld, indulging to his friends the vast unborrowed treasures of his mind, O speak the wondrous man. How mild, how calm, how greatly humble, how divinely good, how firm established on eternal truth. Fervent in doing well, with every nerve still pressing on, forgetful of the past, and panting for perfection, far above those little cares and visionary joys that so perplex the fond, impassioned heart of ever-cheated, ever-trusting man. Note 50/7. In the same strain we find the general voice of the time. For instance, one of Logan's views of Cambridge is dedicated Issaco Newtono, Mathematico, Physico, Chimico consummatissimo, nec minus suavitate morum et candor animi, spectably. In opposition to the general current of such testimony, we have the complaints of Flamsteed, who ascribes to Newton angry language and harsh conduct in the matter of the publication of the Greenwich Observations, and of Whiston. Yet even Flamsteed speaks well of his general disposition. Whiston was himself so weak and prejudiced that his testimony is worth very little. In the first edition of the Principia, published in 1687, Newton showed that the nature of all the then known inequalities of the moon, and in some cases their quantities, might be deduced from the principles which he laid down, but the determination of the amount and law of most of the inequalities was deferred to a more favorable opportunity, when he might be furnished with better astronomical observations. Such observations as he needed for this purpose had been made by Flamsteed, and for these he applied, representing how much value their use would add to the observations. If, he says in 1694, you publish them without such a theory to recommend them, they will only be thrown into the heap of the observations of former astronomers, till somebody shall arise that by perfecting the theory of the moon shall discover your observations to be exacter than the rest. But when that shall be, God knows. I fear, not in your lifetime, if I should die before it is done. For I find this theory so very intricate, and the theory of gravity so necessary to it, that I am satisfied it will never be perfected, but by somebody who understands the theory of gravity as well, or better than I do. He obtained from Flamsteed the lunar observations for which he applied, and by using these he framed the theory of the moon, which is given as his in David Gregory's Astronomiae Elementa. He also obtained from Flamsteed the diameters of the planets as observed at various times, and the greatest elongation of Jupiter's satellites, both of which, Flamsteed says, he made use of in his Principia. Note 51/7. In the preface to a treatise on dynamics, Part 1, published in 1836, I have endeavored to show that Newton's modes of determining several of the lunar inequalities admitted of an accuracy not very inferior to the modern analytical methods. Newton, in his letters to Flamsteed in 1694 and 5, acknowledges this service. 420. Note 52/7. The quarrel on the subject of the publication of Flamsteed's observations took place at a later period. Flamsteed wished to have his observations printed complete and entire. Halley, who, under the authority of Newton and others, had the management of the printing, made many alterations and omissions, which Flamsteed considered as deforming and spoiling the work. The advantages of publishing a complete series of observations, now generally understood, were not then known to astronomers in general, though well known to Flamsteed, and earnestly insisted upon in his remonstrances. The result was that Flamsteed published his observations at his own expense, and finally obtained permission to destroy the copies printed by Halley, which he did. In 1726, after Flamsteed's death, his widow applied to the Vice-Chancellor of Oxford, requesting that the volume printed by Halley might be removed out of the Bodleian Library, where it exists, as being nothing more than an erroneous abridgment of Mr. Flamsteed's works, and unfit to see the light. Chapter 3. Sequel to the epoch of Newton reception of the Newtonian theory. Sect 1 General remarks. The doctrine of universal gravitation, like other great steps in science, required a certain time to make its way into men's minds, and had to be confirmed, illustrated, and completed by the labors of succeeding philosophers. As the discovery itself was great beyond former example, the features of the natural sequel to the discovery were also on a gigantic scale, and many vast and laborious trains of research, each of which might, in itself, be considered as forming a wide science, and several of which have occupied many profound and zealous inquirers from that time to our own day, come before us as parts only of the verification of Newton's theory. Almost everything that has been done, and is doing, in astronomy, falls inevitably under this description, and it is only when the astronomer travels to the very limits of his vast field of labor that he falls in with phenomena which do not acknowledge the jurisdiction of the Newtonian legislation. We must give some account of the events of this part of the history of astronomy, but our narrative must necessarily be extremely brief and imperfect, for the subject is most large and copious, and our limits are fixed and narrow. We have here to do with the history of discoveries, only so far as it illustrates their philosophy. And though the 421 astronomical discoveries of the last century are by no means poor, even in interest of this kind, the generalizations which they involve are far less important for our object, in consequence of being included in a previous generalization. Newton shines out so brightly that all who follow seem faint and dim. It is not precisely the case which the poet describes as in a theater the eyes of men, after some well-graced actor leaves the stage, are idly bent on him that enters next, thinking his prattle to be tedious. But our eyes are at least less intently bent on the astronomers who succeeded, and we attend to their communications with less curiosity, because we know the end, if not the course of their story. We know that their speeches have all closed with Newton's sublime declaration, asserted in some new form. Still, however, the account of the verification and extension of any great discovery is a highly important part of its history. In this instance, it is most important, both from the weight and dignity of the theory concerned, and the ingenuity and extent of the methods employed. And of course, so long as the Newtonian theory still required verification, the question of the truth or falsehood of such a grand system of doctrines could not but excite the most intense curiosity. In what I have said, I am very far from wishing to depreciate the value of the achievements of modern astronomers, but it is essential to my purpose to mark the subordination of narrower to wider truths the different character and import of the labors of those who come before and after the promulgation of a master truth. With this warning, I now proceed to my narrative. Sect 2. Reception of the Newtonian theory in England. There appears to be a popular persuasion that great discoveries are usually received with a prejudiced and contentious opposition, and the authors of them neglected or persecuted. The reverse of this was certainly the case in England with regard to the discoveries of Newton. As we have already seen, even before they were published, they were proclaimed by Halley to be something of transcendent value, and from the moment of their appearance, they rapidly made their way from one class of thinkers to another, nearly as fast as the nature of men's intellectual capacity allows. Halley, Wren, and all the leading 422 members of the Royal Society appear to have embraced the system immediately and zealously. Men whose pursuits had lain rather in literature than in science, and who had not the knowledge and habits of mind which the strict study of the system required, adopted, on the credit of their mathematical friends, the highest estimation of the Principia and a strong regard for its author, as Evelyn, Locke, and Pepys. Only 5 years after the publication, the principles of the work were referred to from the pulpit, as so incontestably proved that they might be made the basis of a theological argument. This was done by Dr. Bentley, when he preached the Boyle's lectures in London in 1692. Newton himself, from the time when his work appeared, is never mentioned except in terms of profound admiration, as, for instance, when he is called by Dr. Bentley, in his sermon, that very excellent and divine theorist, Mr. Isaac Newton. It appears to have been soon suggested that the government ought to provide in some way for a person who was so great an honor to the nation. Some delay took place with regard to this, but in 1695, his friend Mr. Montague, afterwards Earl of Halifax, at that time Chancellor of the Exchequer, made him Warden of the Mint. And in 1699, he succeeded to the higher office of Master of the Mint, a situation worth £1,200 or £1,500 a year, which he filled to the end of his life. In 1703, he became President of the Royal Society, and was annually re-elected to this office during the remaining 25 years of his life. In 1705, he was knighted in the Master's Lodge at Trinity College by Queen Anne, then on a visit to the University of Cambridge. After the accession of George I, Newton's conversation was frequently sought by the princess, afterwards Queen Caroline, who had a taste for speculative studies, and was often heard to declare in public that she thought herself fortunate in living at a time which enabled her to enjoy the society of so great a genius. His fame and the respect paid him went on increasing to the end of his life, and when, in 1727, full of years and glory, his earthly career was ended, his death was mourned as a national calamity, with the forms usually confined to royalty. His body lay in state in the Jerusalem chamber. His pall was borne by the first nobles of the land, and his earthly remains were deposited in the center of Westminster Abbey, in the midst of the memorials of the greatest and wisest men whom England has produced. It cannot be superfluous to say a word or two on the reception of 423, his philosophy in the universities of England. These are often represented as places where bigotry and ignorance resist, as long as it is possible to resist, the invasion of new truths. We cannot doubt that such opinions have prevailed extensively, when we find an intelligent and generally temperate writer, like the late Professor Playfair of Edinburgh, so far possessed by them as to be incapable of seeing or interpreting in any other way any facts respecting Oxford and Cambridge. Yet, notwithstanding these opinions, it will be found that, in the English universities, new views, whether in science or in other subjects, have been introduced as soon as they were clearly established, that they have been diffused from the few to the many more rapidly there than elsewhere occurs, and that from these points the light of newly discovered truths has most usually spread over the land. In most instances, undoubtedly, there has been something of a struggle, on such occasions, between the old and the new opinions. Few men's minds can at once shake off a familiar and consistent system of doctrines and adopt a novel and strange set of principles as soon as presented, but all can see that one change produces many, and that change, in itself, is a source of inconvenience and danger. In the case of the admission of the Newtonian opinions into Cambridge and Oxford, however, there are no traces even of a struggle. Cartesianism had never struck its roots deep in this country. That is, the peculiar hypotheses of Descartes. The Cartesian books, such, for instance, as that of Rohault, were indeed in use, and with good reason, for they contained by far the best treatises on most of the physical sciences, such as mechanics, hydrostatics, optics, and formal astronomy, which could then be found. But I do not conceive that the vortices were ever dwelt upon as a matter of importance in our academic teaching. At any rate, if they were brought among us, they were soon dissipated. Newton's college and his university exulted in his fame and did their utmost to honor and aid him. He was exempted by the king from the obligation of taking orders, under which the fellows of Trinity College in general are. By his college, he was relieved from all offices which might interfere, however slightly, with his studious employments, though he resided within the walls of the society 35 years, almost without the interruption of a month. By the university, he was elected their representative in Parliament in 1688, 424, and again in 1701. And though he was rejected in the dissolution of 1705, those who opposed him acknowledged him to be the glory of the university and nation, but considered the question as a political one, and Newton as sent to tempt them from their duty, by the great and just veneration they had for him. Instruments and other memorials, valued because they belonged to him, are still preserved in his college, along with the tradition of the chambers which he occupied. Note 54/7. His name is nowhere found on the college books, as appointed to any of the offices which usually pass down the list of resident fellows in rotation. This might be owing in part, however, to his being Lucasian professor. The constancy of his residence in college appears from the Exit and Redit book of that time, which is still preserved. The most active and powerful minds at Cambridge became at once disciples and followers of Newton. Samuel Clarke, afterwards his friend, defended in the public schools a thesis taken from his philosophy as early as 1694, and in 1697 published an edition of Rohault's Physics, with notes in which Newton is frequently referred to with expressions of profound respect, though the leading doctrines of the Principia are not introduced till a later edition, in 1703. In 1699, Bentley, whom we have already mentioned as a Newtonian, became master of Trinity College. And in the same year, Whiston, another of Newton's disciples, was appointed his deputy as professor of mathematics. Whiston delivered the Newtonian doctrines, both from the professor's chair and in works written for the use of the university. Yet it is remarkable that a taunt respecting the late introduction of the Newtonian system into the Cambridge course of education has been founded on some peevish expressions which he uses in his memoirs, written at a period when, having incurred expulsion from his professorship and the university, he was naturally querulous and jaundiced in his views. In 1709-10, Dr. Lafton, who was tutor in Clare Hall, procured himself to be appointed moderator of the university disputations, in order to promote the diffusion of the new mathematical doctrines. By this time, the first edition of the Principia was become rare and fetched a great price. Bentley urged Newton to publish a new one, and Coates, by far the first, at that time, of the mathematicians of Cambridge, undertook to superintend the printing, and the edition was accordingly published in 1713. I perceive that my accomplished German translator, Littrow, has incautiously copied the insinuations of some modern writers to the effect that Clarke's reference to Newton, in his edition of Roholt's Physics, was a mode of introducing Newtonian doctrines covertly, when it was not allowed him to introduce such novelties, 425, openly. I am quite sure that anyone who looks into this matter will see that this supposition of any unwillingness at Cambridge to receive Newton's doctrine is quite absurd, and can prove nothing but the intense prejudices of those who maintain such an opinion. Newton received and held his professorship amid the unexampled admiration of all contemporary members of the university. Whiston, who is sometimes brought as an evidence against Cambridge on this point, says, "I with immense pains set myself with the utmost zeal to the study of Sir Isaac Newton's wonderful discoveries in his Philosophiae Naturalis Principia Mathematica, one or two of which lectures I had heard him read in the public schools, though I understood them not at the time. As to Roholt's Physics, it really did contain the best mechanical philosophy of the time, the doctrines which were held by Descartes in common with Galileo, and with all the sound mathematicians who succeeded them. Nor does it look like any great antipathy to novelty in the University of Cambridge, that this book, which was quite as novel in its doctrines as Newton's Principia, and which had only been published at Paris in 1671, had obtained a firm hold on the university in less than 20 years. Nor is there any attempt made in Clarke's notes to conceal the novelty of Newton's discoveries, but on the contrary, admiration is claimed for them as new. The promptitude with which the mathematicians of the University of Cambridge adopted the best parts of the mechanical philosophy of Descartes, and the greater philosophy of Newton, in the 17th century, has been paralleled in our own times, in the promptitude with which they have adopted and followed into their consequences the mathematical theory of heat of Fourier and Laplace, and the undulatory theory of light of Young and Fresnel. In Newton's College, we possess, besides the memorials of him mentioned above, which include 2 locks of his silver-white hair, a paper in his own handwriting, describing the preparatory reading which was necessary in order that our college students might be able to read the Principia. I have printed this paper in the preface to my edition of the first 3 sections of the Principia in the original Latin, 1846. Bentley, who had expressed his admiration for Newton in his Boyle's lectures in 1692, was made master of the college in 1699, as I have stated, and partly, no doubt, in consequence of the Newtonian sermons which he had preached. In his administration of the college he zealously stimulated and assisted the exertions of Coates, Whiston, and other disciples of Newton. Smith, Bentley's successor as master of 426, the college, erected a statue of Newton in the college chapel, a noble work of Roubiliac, with the inscription Qui genus humanum ingenio superavit. At Oxford, David Gregory and Halley, both zealous and distinguished disciples of Newton, obtained the Savilian professorships of astronomy and geometry in 1691 and 1703. David Gregory's Astronomiae Physicae et Geometricae Elementa issued from the Oxford Press in 1702. The author, in the first sentence of the preface, states his object to be to explain the mechanics of the universe, Physica Coelestis, which Isaac Newton, the Prince of Geometers, has carried to a point of elevation which all look up to with admiration. And this design is executed by a full exposition of the Newtonian doctrines and their results. Cale, a pupil of Gregory, followed his tutor to Oxford and taught the Newtonian philosophy there in 1700, being then deputy Sedleian professor. He illustrated his lectures by experiments and published an introduction to the Principia which is not out of use even yet. In Scotland, the Newtonian philosophy was accepted with great alacrity, as appears by the instances of David Gregory and Cale. David Gregory was professor at Edinburgh before he removed to Oxford and was succeeded there by his brother James. The latter had, as early as 1690, printed a thesis, containing in 22 propositions, a compend of Newton's Principia. Probably these were intended as the C's for academical disputations, as Lafton at Cambridge introduced the Newtonian philosophy into these exercises. The formula at Cambridge, in use till very recently in these disputations, was rect statuit Newtonus de modo luni, or the like. Note 56/7. See Hutton's Math, Dict, Art, James Gregory. If it fell in with my plan to notice derivative works, I might speak of Maclaurin's admirable account of Sir Isaac Newton's discoveries, published in 1748. This is still one of the best books on the subject. The late professor regards historical essay on the first publication of Sir Isaac Newton's Principia, Oxf. 1838, contains a careful and candid view of the circumstances of that event. The general diffusion of these opinions in England took place, not only by means of books, but through the labors of various experimental lecturers, like de Séguliers, who removed from Oxford to London in 1713, when he informs us that he found the Newtonian philosophy generally received among persons of all ranks and professions, and even among the ladies by the help of experiments. 427. We might easily trace in our literature indications of the gradual progress of the Newtonian doctrines. For instance, in the earlier editions of Pope's Dunciad, this couplet occurred in the description of the effects of the reign of dullness. Philosophy, that reached the heavens before, shrinks to her hidden cause and is no more. And this, says his editor, Warburton, was intended as a censure on the Newtonian philosophy. For the poet had been misled by the prejudices of foreigners, as if that philosophy had recurred to the occult qualities of Aristotle. This was the idea he received of it from a man educated much abroad, who had read everything, but everything superficially. When I hinted to him how he had been imposed upon, he changed the lines with great pleasure into a compliment, as they now stand on that divine genius, and a satire on that very folly by which he himself had been misled. In 1743, it was printed, Philosophy, that leaned on heaven before, shrinks to her second cause, and is no more. The Newtonians repelled the charge of dealing in occult causes, and, referring gravity to the will of the deity as the first cause, assumed a superiority over those whose philosophy rested in second causes. To the cordial reception of the Newtonian theory by the English astronomers, there is only one conspicuous exception, which is, however, one of some note, being no other than Flamsteed, the astronomer royal, a most laborious and exact observer. Flamsteed at first listened with complacency to the promises of improvements in the lunar tables, which the new doctrines held forth, and was willing to assist Newton and to receive assistance from him. But after a time, he lost his respect for Newton's theory and ceased to take any interest in it. He then declared to one of his correspondents, "I have determined to lay these crotchets of Sir Isaac Newton's wholly aside." We need not, however, find any difficulty in this, if we recollect that Flamsteed, though a good observer, was no philosopher, never understood by a theory anything more than a formula which should predict results, and was incapable of comprehending the object of Newton's theory, which was to assign causes as well as rules, and to satisfy the conditions of mechanics as well as of geometry. 428. I do not see any reason to retract what was thus said, but it ought perhaps to be distinctly said that on these very accounts Flamsteed's rejection of Newton's rules did not imply a denial of the doctrine of gravitation. In the letter above quoted, Flamsteed says that he has been employed upon the moon, and that the heavens reject that equation of Sir I. Newton which Gregory and Newton called his sixth. I had then compared but 72 of my observations with the tables, now I have examined above 100 more. I find them all firm in the same, and the seventh too. And thereupon he comes to the determination above stated. At an earlier period, Flamsteed, as I have said, had received Newton's suggestions with great deference, and had regulated his own observations and theories with reference to them. The calculation of the lunar inequalities upon the theory of gravitation was found by Newton and his successors to be a more difficult and laborious task than he had anticipated, and was not performed without several trials and errors. One of the equations was at first published in Gregory's Astronomiae Elementa with a wrong sign. And when Newton had done all, Flamsteed found that the rules were far from coming up to the degree of accuracy which had been claimed for them, that they could give the moon's place true to 2 or 3 minutes. It was not till considerably later that this amount of exactness was attained. The late Mr. Bailey, to whom astronomy and astronomical literature are so deeply indebted, in his supplement to the account of Flamsteed, has examined with great care and great candor the assertion that Flamsteed did not understand Newton's theory. He remarks, very justly, that what Newton himself at first presented as his theory might more properly be called rules for computing lunar tables than a physical theory in the modern acceptation of the term. He shows, too, that Flamsteed had read the Principia with attention. Nor do I doubt that many considerable mathematicians gave the same imperfect assent to Newton's doctrine which Flamsteed did. But when we find that others, as Halley, David Gregory, and Coates, at once not only saw in the doctrine a source of true formulae, but also a magnificent physical discovery, we are obliged, I think, to make Flamsteed, in this respect, an exception to the first class of astronomers of his own time. Mr. Bailey's suggestion that the annual equations for the corrections of the lunar apogee and node were collected from Flamsteed's tables, 429, and observations independently of their suggestion by Newton as the results of theory sup. p. 692, note, and p. 698, appears to me not to be adequately supported by the evidence given. Sect. 3. Reception of the Newtonian theory abroad. The reception of the Newtonian theory on the continent was much more tardy and unwilling than in its native island. Even those whose mathematical attainments most fitted them to appreciate its proofs were prevented by some peculiarity of view from adopting it as a system, as Leibniz, Bernoulli, Huygens, who all clung to one modification or other of the system of vortices. In France, the Cartesian system had obtained a wide and popular reception, having been recommended by Fontenelle with the graces of his style. And its empire was so firm and well established in that country that it resisted for a long time the pressure of Newtonian arguments. Indeed, the Newtonian opinions had scarcely any disciples in France till Voltaire asserted their claims, on his return from England in 1728. Until then, as he himself says, there were not 20 Newtonians out of England. The hold which the philosophy of Descartes had upon the minds of his countrymen is, perhaps, not surprising. He really had the merit, a great one in the history of science, of having completely overturned the Aristotelian system and introduced the philosophy of matter and motion. In all branches of mixed mathematics, as we have already said, his followers were the best guides who had yet appeared. His hypothesis of vortices, as an explanation of the celestial motions, had an apparent advantage over the Newtonian doctrine in this respect, that it referred effects to the most intelligible or at least most familiar kinds of mechanical causation, namely, pressure and impulse. And above all, the system was acceptable to most minds in consequence of being, as was pretended, deduced from a few simple principles by necessary consequences, and of being also directly connected with metaphysical and theological speculations. We may add that it was modified by its mathematical adherents in such a way as to remove most of the objections to it. A vortex revolving about a center could be constructed, or at least it was supposed that it could be constructed, so as to produce a tendency of bodies to the center. In all cases, therefore, where a central force acted, a vortex was supposed. But in reasoning to the results of this hypothesis, it was 430 easy to leave out of sight all other effects of the vortex, and to consider only the central force. And when this was done, the Cartesian mathematician could apply to his problems a mechanical principle of some degree of consistency. This reflection will, in some degree, account for what at first seems so strange, the fact that the language of the French mathematicians is Cartesian, for almost half a century after the publication of the Principia of Newton. There was, however, a controversy between the two opinions going on all this time, and every day showed the insurmountable difficulties under which the Cartesians labored. Newton, in the Principia, had inserted a series of propositions, the object of which was to prove that the machinery of vortices could not be accommodated to one part of the celestial phenomena without contradicting another part. A more obvious difficulty was the case of gravity of the Earth. If this force arose, as Descartes asserted, from the rotation of the Earth's vortex about its axis, it ought to tend directly to the axis and not to the center. The assertors of vortices often tried their skill in remedying this vice in the hypothesis, but never with much success. Huygens supposed the ethereal matter of the vortices to revolve about the center in all directions. Perrault made the strata of the vortex increase in velocity of rotation as they recede from the center. Sorin maintained that the circumambient resistance which comprises the vortex will produce a pressure passing through the center. The elliptic form of the orbits of the planets was another difficulty. Descartes had supposed the vortices themselves to be oval, but others, as John Bernoulli, contrived ways of having elliptical motion in a circular vortex. The mathematical prize questions proposed by the French Academy naturally brought the two sets of opinions into conflict. The Cartesian memoir of John Bernoulli, to which we have just referred, was the one which gained the prize in 1730. It not unfrequently happened that the Academy, as if desirous to show its impartiality, divided the prize between the Cartesians and Newtonians. Thus, in 1734, the question being the cause of the inclination of the orbits of the planets, the prize was shared between John Bernoulli, whose memoir was founded on the system of vortices, and his son Daniel, who was a Newtonian. The last act of homage of this kind to the Cartesian system was performed in 1740, when the prize on the question of the tides was distributed between Daniel Bernoulli, Euler, Maclaurin, and Cavalieri, the last of whom had tried to patch up and amend the Cartesian hypothesis on this subject. 431. Thus, the Newtonian system was not adopted in France till the Cartesian generation had died off. Fontenelle, who was secretary to the Academy of Sciences and who lived till 1756, died a Cartesian. There were exceptions. For instance, Delisle, an astronomer who was selected by Peter the Great of Russia to found the Academy of St. Petersburg, who visited England in 1724 and to whom Newton then gave his picture and Halley his tables. But in general, during the interval, that country and this had a national difference of creed on physical subjects. Voltaire, who visited England in 1727, notices this difference in his lively manner. A Frenchman who arrives in London finds a great alteration in philosophy, as in other things. He left the world full, he finds it empty. At Paris you see the universe composed of vortices of subtle matter. In London we see nothing of the kind. With you it is the pressure of the moon which causes the tides of the sea. In England it is the sea which gravitates towards the moon. So that when you think the moon ought to give us high water, these gentlemen believe that you ought to have low water, which unfortunately we cannot test by experience, for in order to do that, we should have examined the moon and the tides at the moment of the creation. You will observe also that the sun, which in France has nothing to do with the business, here comes in for a quarter of it. Among you Cartesians, all is done by an impulsion which one does not well understand. With the Newtonians, it is done by an attraction of which we know the cause no better. At Paris you fancy the earth shaped like a melon. At London it is flattened on the two sides. It was Voltaire himself, as we have said, who was mainly instrumental in giving the Newtonian doctrines currency in France. He was at first refused permission to print his Elements of the Newtonian Philosophy by the Chancellor, D'Aguesseau, who was a Cartesian. But after the appearance of this work in 1738, and of other writings by him on the same subject, the Cartesian edifice, already without real support or consistency, crumbled to pieces and disappeared. The first memoir in the Transactions of the French Academy, in which the doctrine of central force is applied to the solar system, is one by the Chevalier de Louville in 1720, on the construction and theory of tables of the sun. In this, however, the mode of explaining the motions of the planets by means of an original impulse and an attractive force is attributed to Kepler, not to Newton. The first memoir which refers to the universal gravitation of matter is by Maupertuis in 432, 1736. But Newton was not unknown or despised in France till this time. In 1699 he was admitted one of the very small number of foreign associates of the French Academy of Sciences. Even Fontenelle, who, as we have said, never adopted his opinions, spoke of him in a worthy manner, in the log which he composed on the occasion of his death. At a much earlier period, too, Fontenelle did homage to his fame. The following passage refers, I presume, to Newton. In the History of the Academy for 1708, which is written by the secretary, he says, in referring to the difficulty which the comets occasion in the Cartesian hypothesis, we might relieve ourselves at once from all the embarrassment which arises from the directions of these motions, by suppressing, as has been done by one of the greatest geniuses of the age, all this immense fluid matter, which we commonly suppose between the planets, and conceiving them suspended in a perfect void. Comets, as the above passage implies, were a kind of artillery which the Cartesian plenum could not resist. When it appeared that the paths of such wanderers traversed the vortices in all directions, it was impossible to maintain that these imaginary currents governed the movements of bodies immersed in them, and the mechanism ceased to have any real efficacy. Both these phenomena of comets, and many others, became objects of a stronger and more general interest, in consequence of the controversy between the rival parties, and thus the prevalence of the Cartesian system did not seriously impede the progress of sound knowledge. In some cases, no doubt, it made men unwilling to receive the truth, as in the instance of the deviation of the comets from the zodiacal motion. And again, when Roemer discovered that light was not instantaneously propagated, but it encouraged observation and calculation, and thus forwarded the verification and extension of the Newtonian system, of which process we must now consider some of the incidents. 433. Chapter 4. Sequel to the Epoch of Newton, continued verification and completion of the Newtonian theory. Sect 1. Division of the subject. The verification of the law of universal gravitation as the governing principle of all cosmical phenomena led, as we have already stated, to a number of different lines of research, all long and difficult. Of these we may treat successively: the motions of the moon, of the sun, of the planets, of the satellites, of comets. We may also consider separately the secular inequalities, which at first sight appear to follow a different law from the other changes. We may then speak of the results of the principle as they affect this earth, in its figure, in the amount of gravity at different places, and in the phenomena of the tides. Each of these subjects has lent its aid to confirm the general law, but in each the confirmation has had its peculiar difficulties and has its separate history. Our sketch of this history must be very rapid, for our aim is only to show what is the kind and course of the confirmation which such a theory demands and receives. For the same reason, we pass over many events of this period which are highly important in the history of astronomy. They have lost much of their interest for us, and even for common readers, because they are of a class with which we are already familiar, truths included in more general truths to which our eyes now most readily turn. Thus, the discovery of new satellites and planets is but a repetition of what was done by Galileo. The determination of their nodes and apses, the reduction of their motions to the law of the ellipse, is but a fresh exemplification of the discoveries of Kepler. Otherwise, the formation of tables of the satellites of Jupiter and Saturn, the discovery of the eccentricities of the orbits, and of the motions of the nodes and apses by Cassini, Halley, and others, would rank with the great achievements in astronomy. Newton's peculiar advance in the tables of the celestial motions is the introduction of perturbations. To these motions, so affected, we now proceed. 434. Sect 2. Application of the Newtonian theory to the moon. The motions of the moon may be first spoken of as the most obvious and the most important of the applications of the Newtonian theory. The verification of such a theory consists, as we have seen in previous cases, in the construction of tables derived from the theory and the comparison of these with observation. The advancement of astronomy would alone have been a sufficient motive for this labor, but there were other reasons which urged it on with a stronger impulse. A perfect lunar theory, if the theory could be perfected, promised to supply a method of finding the longitude of any place on the Earth's surface, and thus the verification of a theory, which professed to be complete in its foundations, was identified with an object of immediate practical use to navigators and geographers, and of vast acknowledged value. A good method for the near discovery of the longitude had been estimated by nations and princes at large sums of money. The Dutch were willing to tempt Galileo to this task by the offer of a chain of gold. Philip III of Spain had promised a reward for this object still earlier. The Parliament of England, in 1714, proposed a recompense of 20,000 sterling. The Regent Duke of Orleans, 2 years afterwards, offered 100,000 francs for the same purpose. These prizes, added to the love of truth and of fame, kept this object constantly before the eyes of mathematicians during the first half of the last century. If the tables could be so constructed as to represent the moon's real place in the heavens with extreme precision, as it would be seen from a standard observatory, the observation of her apparent place, as seen from any other point of the Earth's surface, would enable the observer to find his longitude from the standard point. The motions of the moon had hitherto so ill agreed with the best tables that this method failed altogether. Newton had discovered the ground of this want of agreement. He had shown that the same force which produces the evection, variation, and annual equation must produce also a long series of other inequalities, of various magnitudes and cycles, which perpetually drag the moon before or behind the place where she would be sought by an astronomer who knew only of those principal and notorious inequalities. But to calculate and apply the new inequalities was no slight undertaking. 435. In the first edition of the Principia in 1687, Newton had not given any calculations of new inequalities affecting the longitude of the moon. But in David Gregory's Elements of Physical and Geometrical Astronomy, published in 1702, is inserted Newton's lunar theory as applied by him to practice, in which the great discoverer has given the results of his calculations of 8 of the lunar equations, their quantities, epochs, and periods. These calculations were for a long period the basis of new tables of the moon, which were published by various persons, as by Delisle in 1715 or 1716, Grammaticai at Ingolstadt in 1726, Wright in 1732, Angelo Capelli at Venice in 1733, Dunthorne at Cambridge in 1739. Flamsteed had given tables of the moon upon Horrocks's theory in 1681 and wished to improve them. And though, as we have seen, he would not, or could not, accept Newton's doctrines in their whole extent, Newton communicated his theory to the observer in the shape in which he could understand it and use it. And Flamsteed employed these directions in constructing new lunar tables, which he called his theory. These tables were not published till long after his death, by Le Monnier at Paris in 1746. They are said, by Lalande, not to differ much from Halley's. Halley's tables of the moon were printed in 1719 or 1720, but not published till after his death in 1749. They had been founded on Flamsteed's observations and his own. And when, in 1720, Halley succeeded Flamsteed in the post of Astronomer Royal at Greenwich, and conceived that he had the means of much improving what he had done before, he began by printing what he had already executed. Note 69/7. Mr. Bailey says that Mayer's Nouvelles Tables de la Lune in * 1753, published upwards of 50 years after Gregory's astronomy, may be considered as the first lunar tables formed solely on Newton's principles. Though Wright in 1732 published new and correct tables of the lunar motions according to the Newtonian theory, Newton's rules were in them only partially adopted. In 1735, Leadbitter published his Uranoscopia, in which those rules were more fully followed. But these Newtonian tables did not supersede Flamsteed's Horrocksian tables till both were supplanted by those of Mayer. Sup. p. 702. But Halley had long proposed a method, different from that of Newton, but marked by great ingenuity, for amending the lunar tables. He proposed to do this by the use of a cycle, which we have mentioned as one of the earliest discoveries in astronomy, the period of 223 lunations, or 18 years and 11 days, the Chaldean 436, Saros. This period was anciently used for predicting the eclipses of the sun and moon. For those eclipses which happened during this period are repeated again in the same order, and with nearly the same circumstances, after the expiration of one such period and the commencement of a second. The reason of this is that at the end of such a cycle, the moon is in nearly the same position with respect to the sun, her nodes, and her apogee as she was at first, and is only a few degrees distant from the same part of the heavens. But on the strength of this consideration, Halley conjectured that all the irregularities of the moon's motion, however complex they may be, would recur after such an interval. And that, therefore, if the requisite corrections were determined by observation for one such period, we might by means of them give accuracy to the tables for all succeeding periods. This idea occurred to him before he was acquainted with Newton's views. After the lunar theory of the Principia had appeared, he could not help seeing that the idea was confirmed. For the inequalities of the moon's motion, which arise from the attraction of the sun, will depend on her positions with regard to the sun, the apogee, and the node. And therefore, however numerous, will recur when these positions recur. Halley announced, in 1691, his intention of following this idea into practice, in a paper in which he corrected the text of 3 passages in Pliny, in which this period is mentioned, and from which it is sometimes called the Plinian period. In 1710, in the preface to a new edition to Street's Caroline Tables, he stated that he had already confirmed it to a considerable extent. And even after Newton's theory had been applied, he still resolved to use his cycle as a means of obtaining further accuracy. On succeeding to the observatory at Greenwich in 1720, he was further delayed by finding that the instruments had belonged to Flamsteed and were removed by his executors. And this, he says, was the more grievous to me on account of my advanced age, being then in my 64th year, which put me past all hopes of ever living to see a complete period of 18 years' observation. But thanks to God, he has been pleased hitherto, in 1731, to afford me sufficient health and strength to execute my office, in all its parts, with my own hands and eyes, without any assistance or interruption, during one whole period of the moon's 437 apogee, which period is performed in somewhat less than 9 years. He found the agreement very remarkable, and conceived hopes of attaining the great object, of finding the longitude with the requisite degree of exactness. Nor did he give up his labors on this subject till he had completed his Plinian period in 1739. The accuracy with which Halley conceived himself able to predict the moon's place was within 2 minutes of space, or 1/15th of the breadth of the moon herself. The accuracy required for obtaining the national reward was considerably greater. Lemonnier pursued the idea of Halley, but before Halley's method had been completed, it was superseded by the more direct prosecution of Newton's views. We have already remarked, in the history of analytical mechanics, that in the lunar theory, considered as one of the cases of the problem of 3 bodies, no advance was made beyond what Newton had done, till mathematicians threw aside the Newtonian artifices and applied the newly developed generalizations of the analytical method. The first great apparent deficiency in the agreement of the law of universal gravitation with astronomical observation was removed by Clairaut's improved approximation to the theoretical motion of the moon's apogee in 1750. Yet not till it had caused so much disquietude that Clairaut himself had suggested a modification of the law of attraction. And it was only in tracing the consequences of this suggestion that he found the Newtonian law of the inverse square to be that which, when rightly developed, agreed with the facts. Euler solved the problem by the aid of his analysis in 1745 and published tables of the moon in 1746. His tables were not very accurate at first, but he, D'Alembert, and Clairaut continued to labor at this object, and the 2 latter published tables of the moon in 1754. Finally, Tobias Mayer, an astronomer of Göttingen, having compared Euler's tables with observations, corrected them so successfully that in 1753 he published tables of the moon, which really did possess the accuracy which Halley only flattered himself that he had attained. Mayer's success in his first tables encouraged him to make them still more perfect. He applied himself to the mechanical theory of the moon's orbit, corrected all the coefficients of the series by a great number of observations, and in 1755 sent his new tables to London as worthy to claim the prize offered for the discovery of longitude. He died soon after, 438, in 1762, at the early age of 39, worn out by his incessant labors, and his widow sent to London a copy of his tables with additional corrections. These tables were committed to Bradley, then Astronomer Royal, in order to be compared with observation. Bradley labored at this task with unremitting zeal and industry, having himself long entertained hopes that the lunar method of finding the longitude might be brought into general use. He and his assistant, Gale Morris, introduced corrections into Mayer's tables of 1755. In his report of 1756, he says that he did not find any difference so great as a minute and a quarter, and in 1760 he adds that this deviation had been further diminished by his corrections. It is not foreign to our purpose to observe the great labor which this verification required. Not less than 1220 observations and long calculations founded upon each were employed. The accuracy which Mayer's tables possessed was considered to entitle them to a part of the parliamentary reward. They were printed in 1770, and his widow received 3,000 L from the English nation. At the same time, Euler, whose tables had been the origin and foundation of Mayer's, also had a recompense of the same amount. This public national acknowledgement of the practical accuracy of these tables is, it will be observed, also a solemn recognition of the truth of the Newtonian theory, as far as truth can be judged of by men acting under the highest official responsibility, and aided by the most complete command of the resources of the skill and talents of others. The finding the longitude is thus the seal of the moon's gravitation to the sun and earth, and with this occurrence, therefore, our main concern with the history of the lunar theory ends. Various improvements have been since introduced into this research, but on these we, with so many other subjects before us, must forbear to enter. Sect 3. Application of the Newtonian theory to the planets, satellites, and Earth. The theories of the planets and satellites, as affected by the law of universal gravitation, and therefore by perturbations, were naturally subjects of interest. After the promulgation of that law, some of the effects of the mutual attraction of the planets had, indeed, already attracted notice. The inequality produced by the mutual attraction of Jupiter and Saturn cannot be overlooked by a good observer. In the 439 preface to the second edition of the Principia, Coates remarks that the perturbation of Jupiter and Saturn is not unknown to astronomers. In Halley's tables, it was noticed that there are very great deviations from regularity in these two planets, and these deviations are ascribed to the perturbing force of the planets on each other. But the correction of these by a suitable equation is left to succeeding astronomers. The motion of the planes and apsides of the planetary orbits was one of the first results of their mutual perturbation which was observed. In 1706, Lahayer and Maraldi compared Jupiter with the Rudolphine tables and those of Bullialdus. It appeared that his aphelion had advanced and that his nodes had regressed. In 1728, J. Cassini found that Saturn's aphelion had in like manner traveled forwards. In 1720, when Liouville refused to allow in his solar tables the motion of the aphelion of the Earth, Fontenelle observed that this was a misplaced scrupulousness, since the aphelion of Mercury certainly advances. Yet this reluctance to admit change and irregularity was not yet overcome. When astronomers had found an approximate and apparent constancy and regularity, they were willing to believe it absolute and exact. In the satellites of Jupiter, for instance, they were unwilling to admit even the eccentricity of the orbits, and still more, the variation of the nodes, inclinations, and apsides. But all the fixedness of these was successively disproved. Fontenelle, in 1732, on the occasion of Maraldi's discovery of the change of inclination of the fourth satellite, expresses a suspicion that all the elements might prove liable to change. We see, says he, the constancy of the inclination already shaken in the three first satellites and the eccentricity in the fourth. The immobility of the nodes holds out so far, but there are strong indications that it will share the same fate. The motions of the nodes and apsides of the satellites are a necessary part of the Newtonian theory, and even the Cartesian astronomers now required only data in order to introduce these changes into their tables. The complete reformation of the tables of the sun, planets, and satellites, which followed as a natural consequence from the revolution which Newton had introduced, was rendered possible by the labors of the great constellation of mathematicians of whom we have spoken in the last book, Clairaut, Euler, D'Alembert, and their successors. And 440, it was carried into effect in the course of the last century. Thus Lalande applied Clairaut's theory to Mars, as did Mayer, and the inequalities in this case, says Bailey in 1785, may amount to 2 minutes and therefore must not be neglected. Lalande determined the inequalities of Venus, as did Father Walmesley, an English mathematician, these were found to reach only to 30 seconds. The planetary tables which were in highest repute up to the end of the last century were those of Lalande. In these, the perturbations of Jupiter and Saturn were introduced, their magnitude being such that they cannot be dispensed with, but the tables of Mercury, Venus, and Mars had no perturbations. Hence, these latter tables might be considered as accurate enough to enable the observer to find the object, but not to test the theory of perturbations. But when the calculation of the mutual disturbances of the planets was applied, it was always found that it enabled mathematicians to bring the theoretical places to coincide more exactly with those observed. In improving, as much as possible, this coincidence, it is necessary to determine the mass of each planet. For upon that, according to the law of universal gravitation, its disturbing power depends. Thus, in 1813, Lindenau published tables of Mercury, and concluded from them that a considerable increase of the supposed mass of Venus was necessary to reconcile theory with observation. He had published tables of Venus in 1810 and of Mars in 1811. And, in proving Bouvard's tables of Jupiter and Saturn, values were obtained of the masses of those planets. The form in which the question of the truth of the doctrine of universal gravitation now offers itself to the minds of astronomers is this: that it is taken for granted that it will account for the motions of the heavenly bodies, and the question is, with what supposed masses it will give the best account. The continually increasing accuracy of the table shows the truth of the fundamental assumption. Note 85/7. Among the most important corrections of the supposed masses of the planets, we may notice that of Jupiter by Professor Airy. This determination of Jupiter's mass was founded not on the effect as seen in perturbations, but on a much more direct datum, the time of revolution of his fourth satellite. It appeared, from this calculation, that Jupiter's mass required to be increased by about 1/80th. This result agrees with that which has been derived by German astronomers from the perturbations which the attractions of Jupiter produce in the 4 new planets, and has been generally adopted as an improvement of the elements of our system. The question of perturbation is exemplified in the satellites also. 441, thus the satellites of Jupiter are not only disturbed by the Sun, as the Moon is, but also by each other, as the planets are. This mutual action gives rise to some very curious relations among their motions, which, like most of the other leading inequalities, were forced upon the notice of astronomers by observation before they were obtained by mathematical calculation. In Bradley's remarks upon his own tables of Jupiter's satellites, published among Halley's tables, he observes that the places of the 3 interior satellites are affected by errors which recur in a cycle of 437 days, answering to the time in which they return to the same relative position with regard to each other and to the axis of Jupiter's shadow. Wargentin, who had noticed the same circumstance without knowledge of what Bradley had done, applied it, with all diligence, to the purpose of improving the tables of the satellites in 1746. But at a later period, Laplace established, by mathematical reasoning, the very curious theorem on which this cycle depends, which he calls the libration of Jupiter's satellites. And D'Alembert was then able to publish tables of Jupiter's satellites more accurate than those of Wargentin, which he did in 1789. The progress of physical astronomy from the time of Euler and Clairaut has consisted of a series of calculations and comparisons of the most abstruse and recondite kind. The formation of tables of the planets and satellites from the theory required the solution of problems much more complex than the original case of the problem of 3 bodies. The real motions of the planets and their orbits are rendered still further intricate by this, that all the lines and points to which we can refer them are themselves in motion. The task of carrying order and law into this mass of apparent confusion has required a long series of men of transcendent intellectual powers, and a perseverance and delicacy of observation, such as we have not the smallest example of in any other subject. It is impossible here to give any detailed account of these labors, but we may mention one instance of the complex considerations which enter into them. The nodes of Jupiter's 4th satellite do not go backwards, as the Newtonian theory seems to require. They advance upon Jupiter's orbit. But then, it is to be recollected that the theory requires the nodes to retrograde upon the orbit of the perturbing body, which is here the third satellite. And Lalande showed that, by the necessary relations of space, the latter motion may be retrograde though the former is direct. 442. Attempts have been made, from the time of the solution of the problem of three bodies to the present, to give the greatest possible accuracy to the tables of the Sun, by considering the effect of the various perturbations to which the Earth is subject. Thus, in 1756, Euler calculated the effect of the attractions of the planets on the Earth, the prize question of the French Academy of Sciences, and Clairaut soon after. Lacaille, making use of these results, and of his own numerous observations, published tables of the Sun. In 1786, D'Alembert undertook to verify and improve these tables, by comparing them with 314 observations made by Maskelyne at Greenwich in 1775 and 1784, and in some of the intermediate years. He corrected most of the elements, but he could not remove the uncertainty which occurred respecting the amount of the inequality produced by the reaction of the Moon. He admitted also, in pursuance of Clairaut's theory, a second term of this inequality depending on the Moon's latitude, but irresolutely, and half disposed to reject it on the authority of the observations. Succeeding researches of mathematicians have shown that this term is not admissible as a result of mechanical principles. D'Alembert's tables, thus improved, were exact to 7 or 8 seconds, which was thought, and truly, a very close coincidence for the time. But astronomers were far from resting content with this. In 1806, the French Board of Longitude published D'Alembert's improved solar tables. And in the Connaissance des Temps for 1816, Burckhardt gave the results of a comparison of D'Alembert's tables with a great number of Maskelyne's observations, far greater than the number on which they were founded. It appeared that the epoch, the perigee, and the eccentricity required sensible alterations, and that the mass of Venus ought to be reduced about 1/9, and that of the Moon to be sensibly diminished. In 1827, Professor Airy compared D'Alembert's tables with 2,000 Greenwich observations, made with the new transit instrument at Cambridge, and deduced from this comparison the correction of the elements. These in general agreed closely with Burckhardt's, excepting that a diminution of Mars appeared necessary. Some discordances, however, led Professor Airy to suspect the existence of an inequality which had escaped the sagacity of Laplace and Burckhardt. And a few weeks after this suspicion had been expressed, the same mathematician announced to the Royal Society that he had 443 detected, in the planetary theory, such an inequality, hitherto unnoticed, arising from the mutual attraction of Venus and the Earth. Its whole effect on the Earth's longitude would be to increase or diminish it by nearly 3 seconds of space, and its period is about 240 years. This term, he adds, accounts completely for the difference of the secular motions given by the comparison of the epochs of 1783 and 1821, and by that of the epochs of 1801 and 1821. Many excellent tables of the motions of the Sun, Moon, and planets were published in the latter part of the last century, but the Bureau des Longitudes, which was established in France in 1795, endeavored to give new or improved tables of most of these motions. Thus were produced D'Alembert's tables of the Sun, Berg's tables of the Moon, Bouvard's tables of Jupiter, Saturn, and Uranus. The agreement between these and observation is, in general, truly marvelous. We may notice here a difference in the mode of referring to observation when a theory is first established, and when it is afterwards to be confirmed and corrected. It was remarked as a merit in the method of Hipparchus, and an evidence of the mathematical coherence of his theory, that in order to determine the place of the Sun's apogee and the eccentricity of his orbit, he required to know nothing besides the lengths of winter and spring. But if the fewness of the requisite data is a beauty in the first fixation of a theory, the multitude of observations to which it applies is its excellence when it is established. And in correcting tables, mathematicians take far more data than would be requisite to determine the elements. For the theory ought to account for all the facts, and since it will not do this with mathematical rigor, for observation is not perfect, the elements are determined, not so as to satisfy any selected observations, but so as to make the whole mass of error as small as possible. And thus, in the adaptation of theory to observation, even in its most advanced state, there is room for sagacity and skill, prudence and judgment. In this manner, by selecting the best mean elements of the motions of the heavenly bodies, the observed motions deviate from this mean in the way the theory points out and constantly return to it. To this general rule of the constant return to a mean, there are, however, some apparent exceptions, of which we shall now speak. 444. Sect 4. Application of the Newtonian theory to secular inequalities. Secular inequalities in the motions of the heavenly bodies occur in consequence of changes in the elements of the solar system, which go on progressively from age to age. The example of such changes, which was first studied by astronomers, was the acceleration of the moon's mean motion, discovered by Halley. The observed fact was that the moon now moves in a very small degree quicker than she did in the earlier ages of the world. When this was ascertained, the various hypotheses which appeared likely to account for the fact were reduced to calculation. The resistance of the medium in which the heavenly bodies move was the most obvious of these hypotheses. Another, which was for some time dwelt upon by Laplace, was the successive transmission of gravity. That is, the hypothesis that the gravity of the Earth takes a certain finite time to reach the moon. But none of these suppositions gave satisfactory conclusions, and the strength of Euler, D'Alembert, Lagrange, and Laplace was for a time foiled by this difficulty. At length, in 1787, Laplace announced to the Academy that he had discovered the true cause of this acceleration, and that it arose from the action of the Sun upon the Moon, combined with the secular variation of the eccentricity of the Earth's orbit. It was found that the effects of this combination would exactly account for the changes which had hitherto so perplexed mathematicians. A very remarkable result of this investigation was that this secular inequality of the motion of the moon is periodical, but it requires millions of years to re-establish itself, so that after an almost inconceivable time, the acceleration will become a retardation. Laplace, some time after, in 1797, announced other discoveries relative to the secular motions of the apogee and the nodes of the moon's orbit. Laplace collected these researches in his Theory of the Moon, which he published in the third volume of the Mécanique Céleste in 1802. A similar case occurred with regard to an acceleration of Jupiter's mean motion and a retardation of Saturn's, which had been observed by Cassini, Maraldi, and Horrocks. After several imperfect attempts by other mathematicians, Laplace, in 1787, found that there resulted from the mutual attraction of these two planets a great inequality, of which the period is 929 years and a half, and which has accelerated Jupiter and retarded Saturn ever since the restoration of astronomy. 445. Thus the secular inequalities of the celestial motions, like all the others, confirm the law of universal gravitation. They are called secular, because ages are requisite to unfold their existence, and because they are not obviously periodical. They might, in some measure, be considered as extensions of the Newtonian theory, for though Newton's law accounts for such facts, he did not, so far as we know, foresee such a result of it. But on the other hand, they are exactly of the same nature as those which he did foresee and calculate. And when we call them secular in opposition to periodical, it is not that there is any real difference, for they, too, have their cycle. But it is that we have assumed our mean motion without allowing for these long inequalities. And thus, as Laplace observes on this very occasion, the lot of this great discovery of gravitation is no less than this, that every apparent exception becomes a proof, every difficulty a new occasion of a triumph. And such, as he truly adds, is the character of a true theory, of a real representation of nature. It is impossible for us here to enumerate even the principal objects which have thus filled the triumphal march of the Newtonian theory from its outset up to the present time. But among these secular changes, we may mention the diminution of the obliquity of the ecliptic, which has been going on from the earliest times to the present. This change has been explained by theory and shown to have, like all the other changes of the system, a limit after which the diminution will be converted into an increase. We may mention here some subjects of a kind somewhat different from those just spoken of. The true theoretical quantity of the precession of the equinoxes, which had been erroneously calculated by Newton, was shown by D'Alembert to agree with observation. The constant coincidence of the nodes of the moon's equator with those of her orbit was proved to result from mechanical principles by Lagrange. The curious circumstance that the time of the moon's rotation on her axis is equal to the time of her revolution about the Earth was shown to be consistent with the results of the laws of motion by Laplace. Laplace also, as we have seen, explained certain remarkable relations which constantly connect the longitudes of the three first satellites of Jupiter. Bailly and Lagrange analyzed and explained the curious librations of the nodes and inclinations of their orbits, and Laplace traced the effect of Jupiter's oblate figure on their motions. 446, which masks the other causes of inequality by determining the direction of the motions of the perigove and node of each satellite. Sect 5. Application of the Newtonian theory to the new planets. We are now so accustomed to consider the Newtonian theory as true that we can hardly imagine to ourselves the possibility that those planets which were not discovered when the theory was founded should contradict its doctrines. We can scarcely conceive it possible that Uranus or Ceres should have been found to violate Kepler's laws, or to move without suffering perturbations from Jupiter and Saturn. Yet if we can suppose men to have had any doubt of the exact and universal truth of the doctrine of universal gravitation, at the period of these discoveries, they must have scrutinized the motions of these new bodies with an interest far more lively than that with which we now look for the predicted return of a comet. The solid establishment of the Newtonian theory is thus shown by the manner in which we take it for granted not only in our reasonings, but in our feelings. But though this is so, a short notice of the process by which the new planets were brought within the domain of the theory may properly find a place here. William Herschel, a man of great energy and ingenuity, who had made material improvements in reflecting telescopes, observing at Bath on the 13th of March, 1781, discovered in the constellation Gemini a star larger and less luminous than the fixed stars. On the application of a more powerful telescope, it was seen magnified, and 2 days afterwards he perceived that it had changed its place. The attention of the astronomical world was directed to this new object, and the best astronomers in every part of Europe employed themselves in following it along the sky. The admission of an eighth planet into the long-established list was a notion so foreign to men's thoughts at that time that other suppositions were first tried. The orbit of the new body was at first calculated as if it had been a comet running in a parabolic path. But in a few days the star deviated from the course thus assigned it. And it was in vain that, in order to represent the observations, the perihelion distance of the parabola was increased from 14 to 18 times the Earth's distance from the Sun. Sarin, of the Academy of Sciences of Paris, is said to have been the first person who perceived that the 447 places were better represented by a circle than by a parabola. And Lexell, a celebrated mathematician of Petersburg, found that a motion in a circular orbit, with a radius double of that of Saturn, would satisfy all the observations. This made its period about 82 years. Lalande soon discovered that the circular motion was subject to a sensible inequality. The orbit was, in fact, an ellipse, like those of the other planets. To determine the equation of the center of a body, which revolves so slowly, would, according to the ancient methods, have required many years. But Laplace contrived methods by which the elliptical elements were determined from 4 observations, within little more than a year from its first discovery by Herschel. These calculations were soon followed by tables of the new planet, published by Nowit. In order to obtain additional accuracy, it now became necessary to take account of the perturbations. The French Academy of Sciences proposed, in 1789, the construction of new tables of this planet as its prize question. It is a curious illustration of the constantly accumulating evidence of the theory, that the calculation of the perturbations of the planet enabled astronomers to discover that it had been observed as a star in 3 different positions in former times, namely, by Flamsteed in 1690, by Mayer in 1756, and by Lemonnier in 1769. D'Alembert, aided by this discovery, and by the theory of Laplace, calculated tables of the planet, which, being compared with observation for 3 years, never deviated from it more than 7 seconds. The Academy awarded its prize to these tables. they were adopted by the astronomers of Europe, and the planet of Herschel now conforms to the laws of attraction, along with those ancient members of the known system from which the theory was inferred. The history of the discovery of the other new planets, Ceres, Pallas, Juno, and Vesta, is nearly similar to that just related, except that their planetary character was more readily believed. The first of these was discovered on the first day of this century by Piazzi, the astronomer at Palermo, but he had only begun to suspect its nature and had not completed his third observation when his labors were suspended by a dangerous illness. And on his recovery, the star was invisible, being lost in the rays of the sun. He declared it to be a planet with an elliptical orbit, but the path which it followed on emerging from the neighborhood of the sun was not that which Piazzi had traced out for it. Its extreme smallness made it difficult to rediscover, and the whole of the year 1801 was 448 employed in searching the sky for it in vain. At last, after many trials, von Zach and Albers again found it, the one on the last day of 1801, the other on the first day of 1802. Gauss and Burckhardt immediately used the new observations in determining the elements of the orbit, and the former invented a new method for the purpose. Ceres now moves in a path of which the course and inequalities are known, and can no more escape the scrutiny of astronomers. The second year of the 19th century also produced its planet. This was discovered by Dr. Albers, a physician of Bremen, while he was searching for Ceres among the stars of the constellation Virgo. He found a star which had a perceptible motion even in the space of 2 hours. It was soon announced as a new planet and received from its discoverer the name of Pallas. As in the case of Ceres, Burckhardt and Gauss employed themselves in calculating its orbit, but some peculiar difficulties here occurred. Its eccentricity is greater than that of any of the old planets, and the inclination of its orbit to the ecliptic is not less than 35 degrees. These circumstances both made its perturbations large and rendered them difficult to calculate. Burckhardt employed the known processes of analysis, but they were found insufficient, and the Imperial Institute, as the French Academy was termed during the reign of Napoleon, proposed the perturbations of Pallas as a prize question. To these discoveries succeeded others of the same kind. The German astronomers agreed to examine the whole of the zone in which Ceres and Pallas move, in the hope of finding other planets, fragments, as Albers conceived they might possibly be, of one original mass. In the course of this research, Mr. Harding of Lilienthal, on the 1st of September, 1804, found a new star, which he soon was led to consider as a planet. Gauss and Burckhardt also calculated the elements of this orbit, and the planet was named Juno. After this discovery, Albers sought the sky for additional fragments of his planet with extraordinary perseverance. He conceived that one of two opposite constellations, the Virgin or the Whale, was the place where its separation must have taken place, and where, therefore, all the orbits of all the portions must pass. He resolved to survey, 3 times a year, all the small stars in these two regions. This undertaking, so curious in its nature, was successful. The 29th of March, 1807, he discovered Vesta, which was soon found to be a planet. And to show the manner in which Albers pursued his labors, we may state that he afterwards published a notification that he had examined the 449 same parts of the heavens with such regularity, that he was certain no new planet had passed that way between 1808 and 1816. Gauss and Burckhardt computed the orbit of Vesta, and when Gauss compared one of his orbits with 22 observations of M. Bouvard, he found the errors below 17 seconds of space in right ascension and still less in declination. The elements of all these orbits have been successively improved, and this has been done entirely by the German mathematicians. These perturbations are calculated, and the places for some time before and after opposition are now given in the Berlin ephemeris. I have lately observed, says Professor Airy, and compared with the Berlin ephemeris the right ascensions of Juno and Vesta, and I find that they are rather more accurate than those of Venus. So complete is the confirmation of the theory by these new bodies, so exact are the methods of tracing the theory to its consequences. We may observe that all these new discovered bodies have received names taken from the ancient mythology. In the case of the first of these, astronomers were originally divided. The discoverer himself named it the Georgium Sidus, in honor of his patron, George III. Lalande and others called it Herschel. Nothing can be more just than this mode of perpetuating the fame of the author of a discovery, but it was felt to be ungraceful to violate the homogeneity of the ancient system of names. Astronomers tried to find for the hitherto neglected denizen of the skies an appropriate place among the deities to whose assembly he was at last admitted, and Uranus, the father of Saturn, was fixed upon as best suiting the order of the course. The mythological nomenclature of planets appeared from this time to be generally agreed to. Piazzi termed his series Ferdinandia. The first term, which contains a happy allusion to Sicily, the country of the discovery in modern and of the goddess in ancient times, has been accepted. The attempt to pay a compliment to royalty out of the products of science, in this as in most other cases, has been set aside. Pallas, Juno, and Vesta were named, without any peculiar propriety of selection, according to the choice of their discoverers. Sect 6 Application of the Newtonian theory to comets. A few words must be said upon another class of bodies, which at first seemed as lawless as the clouds and winds, and which astronomy, 450, has reduced to a regularity as complete as that of the sun, upon comets. No part of the Newtonian discoveries excited a more intense interest than this. These anomalous visitants were anciently gazed at with wonder and alarm, and might still, as in former times, be accused of perplexing nations, though with very different fears and questionings. The conjecture that they, too, obeyed the law of universal gravitation was to be verified by showing that they described a curve such as that force would produce. Hevelius, who was a most diligent observer of these objects, had, without reference to gravitation, satisfied himself that they moved in parabolas. To determine the elements of the parabola from observations, even Newton called probum longe difficilimum. Newton determined the orbit of the comet of 1680 by certain graphical methods. His methods supposed the orbit to be a parabola and satisfactorily represented the motion in the visible part of the comet's path. But this method did not apply to the possible return of the wandering star. Halley has the glory of having first detected a periodical comet in the case of that which has since borne his name. But this great discovery was not made without labor. In 1705, Halley explained how the parabolic orbit of a planet may be determined from 3 observations, and joining example to precept, himself calculated the positions and orbits of 24 comets. He found, as the reward of this industry, that the comets of 1607 and of 1531 had the same orbit as that of 1682. And here the intervals are also nearly the same, namely, about 75 years. Are the 3 comets then identical? In looking back into the history of such appearances, he found comets recorded in 1456, in 1380, and in 1305. The intervals are still the same, 75 or 76 years. It was impossible now to doubt that they were the periods of a revolving body, that the comet was a planet, its orbit a long ellipse, not a parabola. Note 99/7. The importance of Halley's labors on comets has always been acknowledged. In speaking of Halley's Synopsis Astronomici Cometici, Delambre says, Roman 18. Cycle, p. 130, voilà bien, depuis Kepler, si quana fate de plus grande, de plus beau, de plus neuf en astronomie. Halley, in predicting the comet of 1758, says, if it returns, hoc primum ob homine Anglo iuventum, fuis non inficiabiter equa posteritas. But if this were so, the comet must reappear in 1758 or 1759. Halley predicted that it would do so, and the fulfillment of this prediction was naturally looked forwards to as an additional stamp of the truths of the theory of gravitation. 451. But in all this, the comet had been supposed to be affected only by the attraction of the sun. The planets must disturb its motion as they disturb each other. How would this disturbance affect the time and circumstances of its reappearance? Halley had proposed, but not attempted to solve, this question. The effect of perturbations upon a comet defeats all known methods of approximation and requires immense labor. Clairaut, says Bailey, undertook this. With courage enough to dare the adventure, he had talent enough to obtain a memorable victory. The difficulties, the labors, grew upon him as he advanced, but he fought his way through them, assisted by Lalande and by a female calculator, Madame Lepot. He predicted that the comet would reach its perihelion April 13, 1759, but claimed the license of a month for the inevitable inaccuracy of a calculation, which, in addition to all other sources of error, was made in haste, that it might appear as a prediction. The comet justified his calculations and his caution together, for it arrived at its perihelion on the 13th of March. Two other comets of much shorter period have been detected of late years: Encke's, which revolves round the Sun in 3 years and 1/3, and Biela's, which describes an ellipse, not extremely eccentric, in 6 years and 3/4. These bodies, apparently thin and vaporous masses like other comets, have, since their orbits were calculated, punctually conformed to the law of gravitation. If it were still doubtful whether the more conspicuous comets do so, these bodies would tend to prove the fact, by showing it to be true in an intermediate case. A third comet of short period was discovered by Faye at the Observatory of Paris, Nav. 22, 1843. It is included between the orbits of Mars and Saturn, and its period is 7 years and 3/10. This is commonly called Faye's comet, as the two mentioned in the text are called Encke's and Biela's. In the former edition, I had expressed my assent to the rule proposed by M. Arago, that the latter ought to be called Gambart's comet, in honor of the astronomer who first proved it to revolve round the Sun. But astronomers in general have used the former name, considering that the discovery and observation of the object are more distinct and conspicuous merits than a calculation founded upon the observations of others. And in reality, 452, Biela had great merit in the discovery of his comet's periodicity, having set about his search of it from an anticipation of its return founded upon former observations. Also, a comet was discovered by De Vico at Rome on Aug. 22, 1844, which was found to describe an elliptical orbit having its aphelion near the orbit of Jupiter, which is consequently one of those of short period. And on Feb. 26, 1846, M. Brorson of Kiel discovered a telescopic comet whose orbit is found to be elliptical. We may add to the history of comets that of Lexell's, which in 1770 appeared to be revolving in a period of about 5 years, and whose motion was predicted accordingly. The prediction was disappointed, but the failure was sufficiently explained by the comet's having passed close to Jupiter, by which occurrence its orbit was utterly deranged. It results from the theory of universal gravitation that comets are collections of extremely attenuated matter. Lexell's is supposed to have passed twice, in 1767 and 1779, through the system of Jupiter's satellites, without disturbing their motions, though suffering itself so great a disturbance as to have its orbit entirely altered. The same result is still more decidedly proved by the last appearance of Biela's comet. It appeared double, but the two bodies did not perceptibly affect each other's motions, as I am informed by Professor Chally of Cambridge, who observed both of them from Jan. 23 to Mar 25, 1846. This proves the quantity of matter in each body to have been exceedingly small. Thus, no verification of the Newtonian theory, which was possible in the motions of the stars, has yet been wanting. The return of Halley's comet again in 1835, and the extreme exactitude with which it conformed to its predicted course, is a testimony of truth, which must appear striking even to the most incurious respecting such matters. Note 101/7. M. de Humboldt, Cosmos, p. 116, speaks of 9 returns of Halley's comet, the comet observed in China in 1378 being identified with this. But whether we take 1378 or 1380 for the appearance in that century, if we begin with that, we have only 7 appearances, namely, in 1378 or 1380, in 1456, in 1531, in 1607, in 1682, in 1759, and in 1835. Sect 7. Application of the Newtonian theory to the figure of the Earth. The heavens had thus been consulted respecting the Newtonian doctrine, and the answer given, over and over again, in 1,453 different forms, had been that it was true, nor had the most persevering cross-examination been able to establish anything of contradiction or prevarication. The same question was also to be put to the earth and the ocean, and we must briefly notice the result. According to the Newtonian principles, the form of the Earth must be a globe somewhat flattened at the poles. This conclusion, or at least the amount of the flattening, depends not only upon the existence and law of attraction, but upon its belonging to each particle of the mass separately, and thus the experimental confirmation of the form asserted from calculation would be a verification of the theory in its widest sense. The application of such a test was the more necessary to the interests of science, inasmuch as the French astronomers had collected from their measures, and had connected with their Cartesian system, the opinion that the Earth was not oblate but oblong. Dominic Cassini had measured 7 degrees of latitude from Amiens to Perpignan in 1701 and found them to decrease in going from south to north. The prolongation of this measure to Dunkirk confirmed the same result. But if the Newtonian doctrine was true, the contrary ought to be the case, and the degrees ought to increase in proceeding towards the pole. The only answer which the Newtonians could at this time make to the difficulty thus presented was that an arc so short as that thus measured was not to be depended upon for the determination of such a question, inasmuch as the inevitable errors of observation might exceed the differences which were the object of research. It would, undoubtedly, have become the English to have given a more complete answer, by executing measurements under circumstances not liable to this uncertainty. The glory of doing this, however, they for a long time abandoned to other nations. The French undertook the task with great spirit. In 1733, in one of the meetings of the French Academy, when this question was discussed, de la Condamine, an ardent and eager man, proposed to settle this question by sending members of the Academy to measure a degree of the meridian near the equator, in order to compare it with the French degrees, and offered himself for the expedition. Maupertuis, in like manner, urged the necessity of another expedition to measure a degree in the neighborhood of the pole. The government received the applications favorably, and these remarkable scientific missions were sent out at the national expense. 454. As soon as the result of these measurements was known, there was no longer any doubt as to the fact of the Earth's oblateness, and the question only turned upon its quantity. Even before the return of the academicians, the Cassinis and Lacaille had measured the French arc, and found errors which subverted the former result, making the Earth oblate to the amount of 1/168th of its diameter. The expeditions to Peru and to Lapland had to struggle with difficulties in the execution of their design, which make their narratives resemble some romantic history of irregular warfare, rather than the monotonous records of mere measurements. The equatorial degree employed the observers not less than 8 years. When they did return, and the results were compared, their discrepancy, as to quantity, was considerable. The comparison of the Peruvian and French arcs gave an ellipticity of nearly 1/314th. That of the Peruvian and Swedish arcs gave 1/213th for its value. Newton had deduced from his theory, by reasonings of singular ingenuity, an ellipticity of 1/230th. But this result had been obtained by supposing the Earth homogeneous. If the Earth be, as we should most readily conjecture it to be, more dense in its interior than at its exterior, its ellipticity will be less than that of a homogeneous spheroid revolving in the same time. It does not appear that Newton was aware of this, but Clairaut, in 1743, in his figure of the Earth, proved this and many other important results of the attraction of the particles. Especially, he established that, in proportion as the fraction expressing the ellipticity becomes smaller, that expressing the excess of the polar over the equatorial gravity becomes larger. And he thus connected the measures of the ellipticity obtained by means of degrees with those obtained by means of pendulums in different latitudes. The altered rate of a pendulum when carried towards the equator had been long ago observed by Richter and Halley, and had been quoted by Newton as confirmatory of his theory. Pendulums were swung by the academicians who measured the degrees and confirmed the general character of the results. But having reached this point of the verification of the Newtonian theory, any additional step becomes more difficult. Many excellent measures, both of degrees and of pendulums, have been made since those just mentioned. The results of the arcs is an ellipticity of 1/298th of the pendulums, an ellipticity of about 1/285th. This difference, 455, is considerable if compared with the quantities themselves, but does not throw a shadow of doubt on the truth of the theory. Indeed, the observations of each kind exhibit irregularities which we may easily account for by ascribing them to the unknown distribution of the denser portions of the Earth, but which preclude the extreme of accuracy and certainty in our result. But the near agreement of the determination, from degrees and from pendulums, is not the only coincidence by which the doctrine is confirmed. We can trace the effect of the Earth's oblateness in certain minute apparent motions of the stars, for the attraction of the sun and moon on the protuberant matter of the spheroid produces the precession of the equinoxes and a nutation of the Earth's axis. The precession had been known from the time of Hipparchus, and the existence of nutation was foreseen by Newton, but the quantity is so small that it required consummate skill and great labor in Bradley to detect it by astronomical observation. Being, however, so detected, its amount, as well as that of the precession, gives us the means of determining the amount of terrestrial ellipticity by which the effect is produced. But it is found, upon calculation, that we cannot obtain this determination without assuming some law of density in the homogeneous strata of which we suppose the Earth to consist. The density will certainly increase in proceeding towards the center. And there is a simple and probable law of this increase, which will give 1/300th for the ellipticity, from the amount of two lunar inequalities, one in latitude and one in longitude, which are produced by the Earth's oblateness. Nearly the same result follows from the quantity of nutation. Thus, everything tends to convince us that the ellipticity cannot deviate much from this fraction. I ought not to omit another class of phenomena in which the effects of the Earth's oblateness, acting according to the law of universal gravitation, have manifested themselves. I speak of the moon's motion, as affected by the Earth's ellipticity. In this case, as in most others, observation anticipated theory. Mason had inferred from lunar observations a certain inequality in longitude, depending upon the distance of the moon's node from the equinox. Doubts were entertained by astronomers whether this inequality really existed, but Laplace showed that such an inequality would arise from the oblate form of the Earth, and that its magnitude might serve to 456 determine the amount of the oblateness. Laplace showed, at the same time, that along with this inequality in longitude, there must be an inequality in latitude, and this assertion Berg confirmed by the discussion of observations. The two inequalities, as shown in the observations, agree in assigning to the Earth's form an ellipticity of 1/305th. Sect 8 confirmation of the Newtonian theory by experiments on attraction. The attraction of all the parts of the Earth to one another was thus proved by experiments in which the whole mass of the Earth is concerned. But attempts have also been made to measure the attraction of smaller portions, as mountains or artificial masses. This is an experiment of great difficulty, for the attraction of such masses must be compared with that of the Earth, of which it is a scarcely perceptible fraction. And, moreover, in the case of mountains, the effect of the mountain will be modified or disguised by unknown or unappreciable circumstances. In many of the measurements of degrees, indications of the attraction of mountains had been perceived, but at the suggestion of Maskelyne, the experiment was carefully made, in 1774, upon the mountain Schiehallion in Scotland, the mountain being mineralogically surveyed by Playfair. The result obtained was that the attraction of the mountain drew the plumb line about 6 seconds from the vertical, and it was deduced from this, by Hutton's calculations, that the density of the Earth was about 1 4/5 that of Schiehallion, or 4.5 times that of water. Cavendish, who had suggested many of the artifices in this calculation, himself made the experiment in the other form, by using leaden balls about 9 inches diameter. This observation was conducted with an extreme degree of ingenuity and delicacy, which could alone make it valuable, and the result agreed very nearly with that of the Schiehallion experiment, giving for the density of the Earth about 5 1/3 times that of water. Nearly the same result was obtained by Carlini in 1824 from observations of the pendulum made at a point of the Alps, the Hospice, on Mount Cenis, at a considerable elevation above the average surface of the Earth. 457. Sect 9 application of the Newtonian theory to the tides. We come, finally, to that result in which most remains to be done for the verification of the general law of attraction, the subject of the tides. Yet, even here, the verification is striking, as far as observations have been carried. Newton's theory explained, with singular felicity, all the prominent circumstances of the tides then known, the difference of spring and neap tides, the effect of the moon's and sun's declination and parallax, even the difference of morning and evening tides and the anomalous tides of particular places. About and after this time, attempts were made both by the Royal Society of England and by the French Academy to collect numerous observations, but these were not followed up with sufficient perseverance. Perhaps, indeed, the theory had not been at that time sufficiently developed, but the admirable prize essays of Euler, Bernoulli, and D'Alembert in 1740 removed, in a great measure, this deficiency. These dissertations supplied the means of bringing this subject to the same test to which all the other consequences of gravitation had been subjected, namely, the calculation of tables, and the continued and orderly comparison of these with observation. Laplace has attempted this verification in another way, by calculating the results of the theory, which he has done with an extraordinary command of analysis, and then by comparing these, in supposed critical cases, with the Brest observations. This method has confirmed the theory as far as it could do so, but such a process cannot supersede the necessity of applying the proper criterion of truth in such cases, the construction and verification of tables. Bernoulli's theory, on the other hand, has been used for the construction of tide tables, but these have not been properly compared with experiment, and when the comparison has been made, having been executed for purposes of gain rather than of science, it has not been published and cannot be quoted as a verification of the theory. Thus we have, as yet, no sufficient comparison of fact with theory, for Laplace's is far from a complete comparison. In this, as in other parts of physical astronomy, our theory ought not only to agree with observations selected and grouped in a particular manner, but with the whole course of observation and with every part of the phenomena. In this, as in other cases, the true theory should be verified by its giving us the best tables. But tide tables were never, I believe, 458 calculated upon Laplace's theory, and thus it was never fairly brought to the test. It is, perhaps, remarkable, considering all the experience which astronomy had furnished, that men should have expected to reach the completion of this branch of science by improving the mathematical theory, without, at the same time, ascertaining the laws of the facts. In all other departments of astronomy, as, for instance, in the cases of the moon and the planets, the leading features of the phenomena had been made out empirically, before the theory explained them. The course which analogy would have recommended for the cultivation of our knowledge of the tides would have been to ascertain, by an analysis of long series of observations, the effect of changes in the time of transit, parallax, and declination of the moon, and thus to obtain the laws of phenomena and then proceed to investigate the laws of causation. Though this was not the course followed by mathematical theorists, it was really pursued by those who practically calculated tide tables, and the application of knowledge to the useful purposes of life being thus separated from the promotion of the theory was naturally treated as a gainful property and preserved by secrecy. Art, in this instance, having cast off her legitimate subordination to science, or rather, being deprived of the guidance which it was the duty of science to afford, resumed her ancient practices of exclusiveness and mystery. Liverpool, London, and other places had their tide tables, constructed by undivulged methods, which methods in some instances at least were handed down from father to son for several generations as a family possession. And the publication of new tables, accompanied by a statement of the mode of calculation, was resented as an infringement of the rights of property. The mode in which these secret methods were invented was that which we have pointed out, the analysis of a considerable series of observations. Probably the best example of this was afforded by the Liverpool tide tables. These were deduced by a clergyman named Holden from observations made at that port by a harbour master of the name of Hutchinson, who was led, by a love of such pursuits, to observe the tides carefully for above 20 years, day and night. Holden's tables, founded on 4 years of these observations, were remarkably accurate. At length, men of science began to perceive that such calculations were part of their business, and that they were called upon, as the 459 guardians of the established theory of the universe, to compare it in the greatest possible detail with the facts. Mr. Lubbock was the first mathematician who undertook the extensive labors which such a conviction suggested. Finding that regular tide observations had been made at the London docks from 1795, he took 19 years of these, purposely selecting the length of a cycle of the motions of the lunar orbit, and caused them, in 1830, one to be analyzed by Mr. Dessieu, an expert calculator. He thus obtained tables for the effect of the moon's declination, parallax, and hour of transit on the tides, and was enabled to produce tide tables founded upon the data thus obtained. Some mistakes in these, as first published, mistakes unimportant as to the theoretical value of the work, served to show the jealousy of the practical tide table calculators by the acrimony with which the oversights were dwelt upon. But in a very few years, the tables thus produced by an open and scientific process were more exact than those which resulted from any of the secrets, and thus practice was brought into its proper subordination to theory. The theory with which Mr. Lubbock was led to compare his results was the equilibrium theory of Daniel Bernoulli, and it was found that this theory, with certain modifications of its elements, represented the facts to a remarkable degree of precision. Mr. Lubbock pointed out this agreement especially in the semi-mensual inequality of the times of high water. The like agreement was afterwards, in 1833, shown by Mr. Whewell to obtain still more accurately at Liverpool, both for the times and heights. For by this time, 19 years of Hutchinson's Liverpool observations had also been discussed by Mr. Lubbock. The other inequalities of the times and heights, depending upon the declination and parallax of the moon and sun, were variously compared with the equilibrium theory by Mr. Lubbock and Mr. Whewell, and the general result was that the facts agreed with the condition of equilibrium at a certain anterior time, but that this anterior time was different for different phenomena. In like manner, it appeared to follow from these researches that in order to explain the facts, the mass of the moon must be supposed different in the calculation at different places. A result in effect the same was obtained by M. Dossi, an active French hydrographer, for he found that observations at various stations could not be reconciled with the formulae of Laplace's mécanique, 460 Céleste, in which the ratio of the heights of spring tides and neap tides was computed on an assumed mass of the moon, without an alteration of level which was, in fact, equivalent to an alteration of the moon's mass. Thus, all things appeared to tend to show that the equilibrium theory would give the formulae for the inequalities of the tides, but that the magnitudes which enter into these formulae must be sought from observation. Whether this result is consistent with theory is a question not so much of physical astronomy as of hydrodynamics, and has not yet been solved. A theory of the tides, which should include in its conditions the phenomena of derivative tides and of their combinations, will probably require all the resources of the mathematical mechanician. As a contribution of empirical materials to the treatment of this hydrodynamical problem, it may be allowable to mention here Mr. Whewell's attempts to trace the progress of the tide into all the seas of the globe, by drawing on maps of the ocean what he calls codal lines. Lines marking the contemporaneous position of the various points of the great wave, which carries high water from shore to shore. This is necessarily a task of labor and difficulty, since it requires us to know the time of high water on the same day in every part of the world. But in proportion as it is completed, it supplies steps between our general view of the movements of the ocean and the phenomena of particular ports. Note 108/7, Essay towards a first approximation to a map of codal lines. Phil, Trans 1833-1836. Looking at this subject by the light which the example of the history of astronomy affords, we may venture to repeat that it will never have justice done it till it is treated as other parts of astronomy are treated. That is, till tables of all the phenomena which can be observed are calculated by means of the best knowledge which we at present possess, until these tables are constantly improved by a comparison of the predicted with the observed fact. A set of tide observations and tide ephemerides of this kind would soon give to this subject that precision which marks the other parts of astronomy, and would leave an assemblage of unexplained residual phenomena in which a careful research might find the materials of other truths as yet unsuspected. That there would be, in the tidal movements of the ocean, inequalities of the heights and times of high and low water. 461, corresponding to those which the equilibrium theory gives, could be considered only as a conjecture, till the comparison with observation was made. It was, however, a natural conjecture, since the waters of the ocean are at every moment tending to acquire the form assumed in the equilibrium theory, and it may be considered likely that the causes which prevent their assuming this form produce an effect nearly constant for each place. Whatever be thought of this reasoning, the conjecture is confirmed by observation with curious exactness. The laws of a great number of the tidal phenomena, namely, of the semi-mensual inequality of the heights, of the semi-mensual inequality of the times, of the diurnal inequality, of the effect of the moon's declination, of the effect of the moon's parallax are represented very closely by formulae derived from the equilibrium theory. The hydrodynamical mode of treating the subject has not added anything to the knowledge of the laws of the phenomena to which the other view had conducted us. We may add that Laplace's assumption that in the moving fluid the motions must have a periodicity corresponding to that of the forces is also a conjecture. And though this conjecture may, in some cases of the problem, be verified by substituting the resulting expressions in the equations of motion, this cannot be done in the actual case, where the revolving motion of the ocean is prevented by the intrusion of tracts of land running nearly from pole to pole. Yet in Mr. Airy's treatise on tides and waves, in the Encyclopaedia Metropolitana, much has been done to bring the hydrodynamical theory of oceanic tides into agreement with observation. In this admirable work, Mr. Airy has, by peculiar artifices, solved problems which come so near the actual cases that they may represent them. He has, in this way, deduced the laws of the semi-diurnal and the diurnal tide, and the other features of the tides which the equilibrium theory in some degree imitates. But he has also, taking into account the effect of friction, shown that the actual tide may be represented as the tide of an earlier epoch, that the relative mass of the moon and sun, as inferred from the tides, would depend upon the depth of the ocean art. 455, with many other results remarkably explaining the observed phenomena. He has also shown that the relation of the cotidal lines to the tide waves really propagated is, in complex cases, very obscure, because different waves of different magnitudes, traveling in different directions, may coexist, and the cotidal line is the compound result of all these. 462. With reference to the maps of cotidal lines, mentioned in the text, I may add that we are as yet destitute of observations, which should supply the means of drawing such lines on a large scale in the Pacific Ocean. Admiral Luck has, however, supplied us with some valuable materials, and remarks on this subject in his note sur les marées périodiques dans le grand océan boréal et dans la mer glaciale, and has drawn them, apparently on sufficient data, in the White Sea. Chapter 5. Discoveries added to the Newtonian theory. Sect 1. Tables of astronomical refraction. We have traveled over an immense field of astronomical and mathematical labor in the last few pages, and have yet, at the end of every step, still found ourselves under the jurisdiction of the Newtonian laws. We are reminded of the universal monarchies, where a man could not escape from the empire without quitting the world. We have now to notice some other discoveries, in which this reference to the law of universal gravitation is less immediate and obvious. I mean the astronomical discoveries respecting light. The general truths to which the establishment of the true laws of atmospheric refraction led astronomers were the law of deflection of the rays of light, which applies to all refractions, and the real structure and size of the atmosphere so far as it became known. The great discoveries of Roemer and Bradley, namely, the velocity of light, the aberration of light, and the nutation of the Earth's axis, gave a new distinctness to the conceptions of the propagation of light in the minds of philosophers, and confirmed the doctrines of Copernicus, Kepler, and Newton, respecting the motions which belong to the Earth. The true laws of atmospheric refraction were slowly discovered. Tycho attributed the apparent displacement of the heavenly bodies to the low and gross part of the atmosphere only, and hence made it cease at a point halfway to the zenith, but Kepler rightly extended it to the zenith itself. Dominic Cassini endeavored to discover the law of this correction by observation, and gave his result in the form 463, which, as we have said, sound science prescribes, a table to be habitually used for all observations. But great difficulties at this time embarrassed this investigation, for the parallaxes of the Sun and of the planets were unknown, and very diverse values had been assigned them by different astronomers. To remove some of these difficulties, Richter, in 1762, went to observe at the equator, and on his return, Cassini was able to confirm and amend his former estimations of parallax and refraction. But there were still difficulties. According to Lahire, though the phenomena of twilight give an altitude of 34,000 toises to the atmosphere, those of refraction make it only 2,000. John Cassini undertook to support and improve the calculations of his father Dominic, and took the true supposition that the light follows a curvilinear path through the air. The Royal Society of London had already ascertained experimentally the refractive power of air. Newton calculated a table of refractions, which was published under Halley's name in the Asterisk Philosophical Transactions for 1721, without any indication of the method by which it was constructed. But M. Biot has recently shown, by means of the published correspondence of Flamsteed, that Newton had solved the problem in a manner nearly corresponding to the most improved methods of modern analysis. Dominic Cassini and Picard proved, Lemonnier in 1738 confirmed more fully, the fact that the variations of the thermometer affect the refraction. Mayer, taking into account both these changes and the changes indicated by the barometer, formed a theory, which Lacaille, with immense labor, applied to the construction of a table of refractions from observation. But Bradley's table, published in 1763 by Maskelyne, was more commonly adopted in England, and his formula, originally obtained empirically, has been shown by Young to result from the most probable suppositions we can make respecting the atmosphere. Bessel's refraction tables are now considered the best of those which have appeared. Sect 2 Discovery of the velocity of light, Romer. The astronomical history of refraction is not marked by any great discoveries, and was, for the most part, a work of labor only. The progress of the other portions of our knowledge respecting light is 464 more striking. In 1676, a great number of observations of eclipses of Jupiter's satellites were accumulated and could be compared with Cassini's tables. Romer, a Danish astronomer whom Picard had brought to Paris, perceived that these eclipses happened constantly later than the calculated time at one season of the year, and earlier at another season, a difference for which astronomy could offer no account. The error was the same for all the satellites. If it had depended on a defect in the tables of Jupiter, it might have affected all, but the effect would have had a reference to the velocities of the satellites. The cause, then, was something extraneous to Jupiter. Romer had the happy thought of comparing the error with the Earth's distance from Jupiter, and it was found that the eclipses happened later in proportion as Jupiter was further off. Thus we see the eclipse later, as it is more remote, and thus light, the messenger which brings us intelligence of the occurrence, travels over its course in a measurable time. By this evidence, light appeared to take about 11 minutes in describing the diameter of the Earth's orbit. This discovery, like so many others, once made, appears easy and inevitable. Yet Dominic Cassini had entertained the idea for a moment and had rejected it, and Fontenelle had congratulated himself publicly on having narrowly escaped this seductive error. The objections to the admission of the truth arose principally from the inaccuracy of observation, and from the persuasion that the motions of the satellites were circular and uniform. Their irregularities disguised the fact in question. As these irregularities became clearly known, Romer's discovery was finally established, and the equation of light took its place in the tables. Sect 3 Discovery of aberration Bradley. Improvements in instruments and in the art of observing were requisite for making the next great step in tracing the effect of the laws of light. It appears clear, on consideration, that since light and the spectator on the Earth are both in motion, the apparent direction of an object will be determined by the composition of these motions. But yet the effect of this composition of motions was, as is usual in such cases, traced as a fact in observation, before it was clearly seen as a consequence of reasoning. This fact, the aberration of light, the greatest astronomical discovery of the 18th century, belongs to Bradley, 465, who was then professor of astronomy at Oxford and afterwards Astronomer Royal at Greenwich. Molyneux and Bradley, in 1725, began a series of observations for the purpose of ascertaining, by observations near the zenith, the existence of an annual parallax of the fixed stars, which Hooke had hoped to detect, and Flamsteed thought he had discovered. Bradley soon found that the star observed by him had a minute apparent motion different from that which the annual parallax would produce. He thought of a nutation of the Earth's axis as a mode of accounting for this, but found, by comparison of a star on the other side of the pole, that this explanation would not apply. Bradley and Molyneux then considered for a moment an annual alteration of figure in the Earth's atmosphere, such as might affect the refractions, but this hypothesis was soon rejected. In 1727, Bradley resumed his observations, with a new instrument, at Wanstead, and obtained empirical rules for the changes of declination of different stars. At last, accident turned his thoughts to the direction in which he was to find the cause of the variations which he had discovered. Being in a boat on the Thames, he observed that the vane on the top of the mast gave a different apparent direction to the wind, as the boat sailed one way or the other. Here was an image of his case. The boat represented the Earth moving in different directions at different seasons, and the wind represented the light of a star. He had now to trace the consequences of this idea. He found that it led to the empirical rules, which he had already discovered, and in 1729 he gave his discovery to the Royal Society. His paper is a very happy narrative of his labors and his thoughts. His theory was so sound that no astronomer ever contested it, and his observations were so accurate that the quantity which he assigned as the greatest amount of the change, 1/19 of a degree, has hardly been corrected by more recent astronomers. It must be noticed, however, that he considered the effects in declination only. The effects in right ascension required a different mode of observation and a consummate goodness in the machinery of clocks, which at that time was hardly attained. Sect 4. Discovery of nutation. When Bradley went to Greenwich as Astronomer Royal, he continued with perseverance observations of the same kind as those by which he had detected aberration. The result of these was another, 466, discovery, namely, that very nutation which he had formerly rejected. This may appear strange, but it is easily explained. The aberration is an annual change, and is detected by observing a star at different seasons of the year. The nutation is a change of which the cycle is 18 years, and which, therefore, though it does not much change the place of a star in 1 year, is discoverable in the alterations of several successive years. A very few years' observations showed Bradley the effect of this change, and long before the half-cycle of 9 years had elapsed, he had connected it in his mind with the true cause, the motion of the moon's nodes. Machen was then secretary to the Royal Society, and was employed in considering the theory of gravity and its consequences with regard to the celestial motions. To him, Bradley communicated his conjectures. From him, he soon received a table containing the results of his calculations, and the law was found to be the same in the table and in observation, though the quantities were somewhat different. It appeared by both that the Earth's pole, besides the motion which the precession of the equinoxes gives it, moves in 18 years through a small circle, or rather, as was afterwards found by Bradley, an ellipse, of which the axes are 19 and 14 seconds. For the rigorous establishment of the mechanical theory of that effect of the moon's attraction from which the phenomena of nutation flow, Bradley rightly and prudently invited the assistance of the great mathematicians of his time. D'Alembert, Thomas Simpson, Euler, and others answered this call, and the result was, as we have already said in the last chapter, Sect 7, that this investigation added another to the recondite and profound evidences of the doctrine of universal gravitation. It has been said that Bradley's discoveries assure him the most distinguished place among astronomers after Hipparchus and Kepler. If his discoveries had been made before Newton's, there could have been no hesitation as to placing him on a level with those great men. The existence of such suggestions as the Newtonian theory offered on all astronomical subjects may perhaps dim, in our eyes, the brilliance of Bradley's achievements. But this circumstance cannot place any other person above the author of such discoveries, and therefore we may consider D'Alembert's adjudication of precedence as well warranted and deserving to be permanent. 467. Sect 5 Discovery of the Laws of Double stars the two Herschels. No truth, then, can be more certainly established than that the law of gravitation prevails to the very boundaries of the solar system. But does it hold good further? Do the fixed stars also obey this universal sway? The idea, the question, is an obvious one, but where are we to find the means of submitting it to the test of observation? If the stars were each insulated from the rest, as our sun appears to be from them, we should have been quite unable to answer this inquiry. But among the stars, there are some which are called double stars, and which consist of two stars, so near to each other that the telescope alone can separate them. The elder Herschel diligently observed and measured the relative positions of the two stars in such pairs, and as has so often happened in astronomical history, pursuing one object he fell in with another. Supposing such pairs to be really unconnected, he wished to learn, from their phenomena, something respecting the annual parallax of the Earth's orbit. But in the course of 20 years' observations, he made the discovery, in 1803, that some of these couples were turning round each other with various angular velocities. These revolutions were for the most part so slow that he was obliged to leave their complete determination as an inheritance to the next generation. His son was not careless of the bequest, and after having added an enormous mass of observations to those of his father, he applied himself to determine the laws of these revolutions. A problem so obvious and so tempting was attacked also by others, as Savary and Encke, in 1830 and 1832, with the resources of analysis. But a problem in which the data are so minute and inevitably imperfect required the mathematician to employ much judgment, as well as skill in using and combining these data. And Sir John Herschel, by employing positions only of the line joining the pair of stars, which can be observed with comparative exactness, to the exclusion of their distances, which cannot be measured with much correctness, and by inventing a method which depended upon the whole body of observations, and not upon selected ones only, for the determination of the motion, has made his investigations by far the most satisfactory of those which have appeared. The result is that it has been rendered very probable that in several of the double stars the two stars describe ellipses about each other, and therefore that here also, at an 468 immeasurable distance from our system, the law of attraction according to the inverse square of the distance prevails. And according to the practice of astronomers, when a law has been established, tables have been calculated for the future motions, and we have ephemerides of the revolutions of suns round each other in a region so remote that the whole circle of our Earth's orbit, if placed there, would be imperceptible by our strongest telescopes. The permanent comparison of the observed with the predicted motions, continued for more than one revolution, is the severe and decisive test of the truth of the theory, and the result of this test astronomers are now awaiting. In calculating the orbits of revolving systems of double stars, there is a peculiar difficulty, arising from the plane of the orbit being in a position unknown, but probably oblique, to the visual ray. Hence it comes to pass that even if the orbit be an ellipse described about the focus by the laws of planetary motion, it will appear otherwise, and the true orbit will have to be deduced from the apparent one. With regard to a difficulty which has been mentioned, that the two stars, if they are governed by gravity, will not revolve the one about the other, but both about their common center of gravity, this circumstance adds little difficulty to the problem. Newton has shown, Princip. Lib. I Prop 61, in the problem of two bodies, the relation between the relative orbits and the orbit about the common center of gravity. How many of the apparently double stars have orbital motions? Sir John Herschel in 1833 gave, in his Astronomy Art. 606, a list of 9 stars, with periods extending from 43 years Eta Coronii to 1,200 years Gamma Leonis, which he presented as the chief results then obtained in this department. In his work on double stars, the fruit of his labors in both hemispheres, which the astronomical world are looking for with eager expectation, he will, I believe, have a few more to add to these. Is it well established that such double stars attract each other according to the law of the inverse square of the distance? The answer to this question must be determined by ascertaining whether the above cases are regulated by the laws of elliptical motion. This is a matter which it must require a long course of careful observation to determine in such a number of cases as to prove the universality of the rule. Perhaps the minds of astronomers are still in suspense upon the subject. When Sir John Herschel's work shall appear, it will probably, 469, be found that with regard to some of these stars, and Gamma Virginis in particular, the conformity of the observations with the laws of elliptical motion amounts to a degree of exactness which must give astronomers a strong conviction of the truth of the law. For since Sir W. Herschel's first measures in 1781, the arc described by one star about the other is above 305 degrees, and during this period the angular annual motion has been very various, passing through all gradations from about 20 minutes to 80 degrees. Yet in the whole of this change, the two curves constructed, the one from the observations, the other from the elliptical elements, for the purpose of comparison, having a total ordinate of 305 parts, do not, in any part of their course, deviate from each other so much as two such parts. The verification of Newton's discoveries was sufficient employment for the last century. The first step in the extension of them belongs to this century. We cannot at present foresee the magnitude of this task, but everyone must feel that the law of gravitation, before verified in all the particles of our own system, and now probably extended to the all but infinite distance of the fixed stars, presses upon our minds with a strong claim to be accepted as a universal law of the whole material creation. Thus, in this and the preceding chapter, I have given a brief sketch of the history of the verification and extension of Newton's great discovery. By the mass of labor and of skill which this head of our subject includes, we may judge of the magnitude of the advance in our knowledge which that discovery made. A wonderful amount of talent and industry have been requisite for this purpose, but with these, external means have cooperated. Wealth, authority, mechanical skill, the division of labor, the power of associations and of governments have been largely and worthily applied in bringing astronomy to its present high and flourishing condition. We must consider briefly what has thus been done. 470. Chapter 6. The Instruments and Aids of Astronomy during the Newtonian Period. Sect 1. Instruments. Some instruments or other were employed at all periods of astronomical observation, but it was only when observation had attained a considerable degree of delicacy that the exact construction of instruments became an object of serious care. Gradually, as the possibility and the value of increased exactness became manifest, it was seen that everything which could improve the astronomer's instruments was of high importance to him. And hence in some cases a vast increase of size and of expense was introduced, in other cases new combinations, or the result of improvements in other sciences, were brought into play. Extensive knowledge, intense thought, and great ingenuity were requisite in the astronomical instrument maker. Instead of ranking with artisans, he became a man of science, sharing the honor and dignity of the astronomer himself. One measure of angles. Tycho Brahe was the first astronomer who acted upon a due appreciation of the importance of good instruments. The collection of such at Uraniborg was by far the finest which had ever existed. He endeavored to give steadiness to the frame and accuracy to the divisions of his instruments. His mural quadrant was well adapted for this purpose. Its radius was 5 cubits. It is clear that as we enlarge the instrument, we are enabled to measure smaller arcs. On this principle, many large gnomons were erected. Cassini's celebrated one in the church of St. Petronius at Bologna was 83 feet French high. But this mode of obtaining accuracy was soon abandoned for better methods. 3 great improvements were introduced about the same time. The application of the micrometer to the telescope by Huygens, Malvasia, and Auzout, the application of the telescope to the astronomical quadrant, and the fixation of the center of its field by a cross of fine wires placed in the focus by Gascoigne and afterwards by Picard. We may judge how great was the improvement which these contrivances introduced into the art of 471, observing. By finding that Hevelius refused to adopt them, because they would make all the old observations of no value. He had spent a laborious and active life in the exercise of the old methods, and could not bear to think that all the treasures which he had accumulated had lost their worth by the discovery of a new mine of richer ore. Littrow, in his Die Wunder des Himmels ed. 2 pp. 684-685, says that Gascoigne invented and used the telescope with wires in the common focus of the lenses in 1640. He refers to Phil. Trans. XXX. 603. Picard reinvented this arrangement in 1667. I have already spoken of Gascoigne as the inventor of the micrometer. Romer, already mentioned, p. 464, brought into use the transit instrument and the employment of complete circles instead of the quadrants used till then, and by these means gave to practical astronomy a new form, of which the full value was not discovered till long afterwards. The apparent place of the object in the instrument being so precisely determined by the new methods, the exact division of the arc into degrees and their subdivisions became a matter of great consequence. A series of artists, principally English, have acquired distinguished places in the lists of scientific fame by their performances in this way. And from that period, particular instruments have possessed historical interest and individual reputation. Graham was one of the first of these artists. He executed a great mural arc for Halley at Greenwich. For Bradley, he constructed the sector which detected aberration. He also made the sector which the French academicians carried to Lapland, and probably the goodness of this instrument, compared with the imperfection of those which were sent to Peru, was one main cause of the great difference of duration in the two series of observations. Bird, somewhat later, about 1750, divided several quadrants for public observatories. His method of dividing was considered so perfect that the knowledge of it was purchased by the English government and published in 1767. Ramsden was equally celebrated. The error of one of his best quadrants, that at Padua, is said to be never greater than 2 seconds. But at a later period, Ramsden constructed mural circles only, holding this to be a kind of instrument far superior to the quadrant. He made one of 5 feet diameter, in 1788, for M. Piazzi at Palermo, and one of 8 feet for the Observatory of Dublin. Troughton, a worthy successor of the 472 artists we have mentioned, has invented a method of dividing the circle still superior to the former ones. Indeed, one which is theoretically perfect and practically capable of consummate accuracy. In this way, circles have been constructed for Greenwich, Armagh, Cambridge, and many other places. And probably this method, carefully applied, offers to the astronomer as much exactness as his other implements allow him to receive. But the slightest casualty happening to such an instrument, after it has been constructed, or any doubt whether the method of graduation has been rightly applied, makes it unfit for the jealous scrupulosity of modern astronomy. The English artists sought to attain accurate measurements by continued bisection and other aliquot subdivision of the limb of their circle. But Mayer proposed to obtain this end otherwise, by repeating the measure on different parts of the circumference till the error of the division becomes unimportant, instead of attempting to divide an instrument without error. This invention of the repeating circle was zealously adopted by the French, and the relative superiority of the rival methods is still a matter of difference of opinion. In the series of these great astronomical mechanists, we must also reckon George Reichenbach. He was born Aug. 24, 1772, at Durlach, became lieutenant of artillery in the Bavarian service in 1794. Salen-Enrath, commissioner of salt works in 1811, and in 1820, first commissioner of waterworks and roads. He became, with Fraunhofer, the ornament of the Mechanical and Optical Institute erected in 1805 at Benediktbüren by Utzschneider. And his astronomical instruments, meridian circles, transit instruments, equatorials, heliometers, make an epoch in observing astronomy. His contrivances in the salt works at Berchtesgaden and Reichenhall, in the arms manufactory at Amberg, and in the works for boring cannon at Vienna are enduring monuments of his rare mechanical talent. He died May 21, 1826 at Munich. 2. The improvements in the measures of space require corresponding improvements in the measure of time. The beginning of anything which we can call accuracy, in this subject, was the application of the pendulum to clocks, by Huygens, in 1656. That the successive oscillations of a pendulum occupy equal times had been noticed by Galileo. But in order to take advantage of this property, the pendulum must be connected with machinery by which its motion is kept from languishing, and by which the number of its swings is recorded. By inventing such machinery, Huygens at once obtained 473, a measure of time more accurate than the sun itself. Hence astronomers were soon led to obtain the right ascension of a star, not directly, by measuring a distance in the heavens, but indirectly, by observing the moment of its transit. This observation is now made with a degree of accuracy which might, at first sight, appear beyond the limits of human sense, being noted to a tenth of a second of time. But we may explain this by remarking that though the number of the second at which the transit happens is given by the clock, and is reckoned according to the course of time, the subdivision of the second of time into smaller fractions is performed by the eye, by seeing the space described by the heavenly body in a whole second, and hence estimating a smaller time according to the space which its description occupies. But in order to make clocks so accurate as to justify this degree of precision, their construction was improved by various persons in succession. Picard soon found that Huygens clocks were affected in their going by temperature, for heat caused expansion of the metallic pendulum. This cause of error was remedied by combining different metals, as iron and copper, which expand in a different degree, in such a way that their effects compensate each other. Graham afterwards used quicksilver for the same purpose. The escapement, too, which connects the force which impels the clock with the pendulum which regulates it, and other parts of the machinery, had the most refined mechanical skill and ingenuity of the best artists constantly bestowed upon them. The astronomer of the present day, constantly testing the going of such a clock by the motions of the fixed stars, has a scale of time as stable and as minutely exact as the scales on which he measures distance. The construction of good watches, that is, portable or marine clocks, was important on another account, namely, because they might be used in determining the longitude of places. Hence the improvement of this little machine became an object of national interest, and was included in the reward of 20,000 L, which we have already noticed as offered by the English Parliament for the discovery of the longitude. Harrison, originally a carpenter, turned his mind to this subject with success. After 30 years of labor, in which he was encouraged by many eminent persons, he produced, in 1758, a timekeeper, which was sent on a voyage to Jamaica for trial. After 161 days, the error, 474 of the watch, was only 1 minute 5 seconds, and the artist received from the nation 5,000 L. At a later period, at the age of 75 years, after a life devoted to this object, having still further satisfied the commissioners, he received, in 1765, 10,000 L. At the same time that Euler and the heirs of Mayer received each 3,000 L. for the lunar tables which they had constructed. The two methods of finding the longitude, by chronometers and by lunar observations, have solved the problem for all practical purposes. But the latter could not have been employed at sea without the aid of that invaluable instrument, the sextant, in which the distance of two objects is observed, by bringing one to coincide apparently with the reflected image of the other. This instrument was invented by Hadley in 1731. Though the problem of finding the longitude be, in fact, one of geography rather than astronomy, it is an application of astronomical science which has so materially affected the progress of our knowledge that it deserves the notice we have bestowed upon it. 3 telescopes we have spoken of the application of the telescope to astronomical measurements, but not of the improvement of the telescope itself. If we endeavor to augment the optical power of this instrument, we run, according to the path we take, into various inconveniences, distortion, confusion, want of light, or colored images. Distortion and confusion are produced if we increase the magnifying power, retaining the length and the aperture of the object glass. If we diminish the aperture, we suffer from loss of light. What remains then is to increase the focal length. This was done to an extraordinary extent in telescopes constructed in the beginning of the last century. Huygens, in his first attempts, made them 22 feet long. Afterwards, Campani, by order of Louis XIV, made them of 86, 100, and 136 feet. Huygens, by new exertions, made a telescope 210 feet long. Auzout and Hartsoeker are said to have gone much further, and to have succeeded in making an object glass of 600 feet focus. But even such telescopes as those of Campani are almost unmanageable. In that of Huygens, the object glass was placed on a pole, and the observer was placed at the focus with an eyeglass. The most serious objection to the increase of the aperture of object glasses was the coloration of the image produced, in consequence of the unequal refrangibility of differently colored rays. Newton, who discovered the principle of this defect in lenses, had maintained that 475, the evil was irremediable, and that a compound lens could no more refract without producing color than a single lens could. Euler and Klingenstierna doubted the exactness of Newton's proposition, and in 1755, Dalland disproved it by experiment. This discovery pointed out a method of making object glasses which should give no color, which should be achromatic. For this purpose, Dalland fabricated various kinds of glass, flint and crown glass, and Clairaut and D'Alembert calculated formulae. Dalland and his son succeeded in constructing telescopes of 3 feet long, with a triple object glass, which produced an effect as great as those of 45 feet on the ancient principles. At first, it was conceived that these discoveries opened the way to a vast extension of the astronomer's power of vision, but it was found that the most material improvement was the compendious size of the new instruments. For, in increasing the dimensions, the optician was stopped by the impossibility of obtaining lenses of flint glass of very large dimensions. And this branch of art remained long stationary, but after a time, its epoch of advance again arrived. In the present century, Fraunhofer, at Munich, with the help of Guinand and the pecuniary support of Utzschneider, succeeded in forming lenses of flint glass of a magnitude till then unheard of. Achromatic object glasses, of a foot in diameter and 20 feet focal length, are now no longer impossible, although in such attempts the artist cannot reckon on certain success. Joseph Fraunhofer was born March 6, 1787, at Straubing in Bavaria, the son of a poor glazier. He was in his earlier years employed in his father's trade, so that he was not able to attend school and remained ignorant of writing and arithmetic till his 14th year. At a later period, he was assisted by Utzschneider and tried rapidly to recover his lost ground. In the year 1806, he entered the establishment of Utzschneider as an optician. In this establishment, transferred from Benedict Bjorn to Munich in 1819, he soon came to be the greatest optician of Germany. His excellent telescopes and microscopes are known throughout Europe. His greatest telescope, that in the observatory at Dorpat, has an object glass of 9 inches diameter and a focal length of 13 feet. His written productions are to be found in the memoirs of the Bavarian Academy, in Gilbert's Annalen der Physik, and in Schumacher's Astronomische Nachrichten. He died the 7th of June, 1826. 476. Such telescopes might be expected to add something to our knowledge of the heavens if they had not been anticipated by reflectors of an equal or greater scale. James Gregory had invented, and Newton had more efficaciously introduced, reflecting telescopes. But these were not used with any peculiar effect till the elder Herschel made them his especial study. His skill and perseverance in grinding specula, and in contriving the best apparatus for their use, were rewarded by a number of curious and striking discoveries, among which, as we have already related, was the discovery of a new planet beyond Saturn. In 1789, Herschel surpassed all his former attempts by bringing into action a reflecting telescope of 40 feet length with a speculum of 4 feet in diameter. The first application of this magnificent instrument showed a new satellite, the 6th of Saturn. He and his son have, with reflectors of 20 feet, made a complete survey of the heavens, so far as they are visible in this country, and the latter is now in a distant region completing this survey by adding to it the other hemisphere. In speaking of the improvements of telescopes, we ought to notice that they have been pursued in the eyeglasses as well as in the object glasses. Instead of the single lens, Huygens substituted an eyepiece of 2 lenses, which, though introduced for another purpose, attain the object of destroying color. Ramsden's eyepiece is one fit to be used with a micrometer, and others of more complex construction have been used for various purposes. Sect 2 Observatories. Astronomy, which is thus benefited by the erection of large and stable instruments, requires also the establishment of permanent observatories, supplied with funds for their support and for that of the observers. Such observatories have existed at all periods of the history of the science, but from the commencement of the period which we are now reviewing, they multiplied to such an extent that we cannot even enumerate them. Yet we must undoubtedly look upon such establishments, and the labors of which they have been the scene, as important and essential parts of the history of the progress of astronomy. Some of the most distinguished of the observatories of modern times we may mention. The first of these were that of Tycho Brahe, 477, at Uraniborg, and that of the Landgrave of Hesse-Kassel, at Kassel, where Rothman and Biagius observed. But by far the most important observations, at least since those of Tycho, which were the basis of the discoveries of Kepler and Newton, have been made at Paris and Greenwich. The Observatory of Paris was built in 1667. It was there that the first Cassini made many of his discoveries. 3 of his descendants have since labored in the same place, and 2 others of his family, the Maraldis, besides many other eminent astronomers as Picard, La Hire, Lefebvre, Fauci, Legental, Chappe, Machen, Bouvard. Greenwich Observatory was built a few years later, 1675. And ever since its erection, the observations there made have been the foundation of the greatest improvements which astronomy, for the time, received. Flamsteed, Halley, Bradley, Bliss, Maskelyne, Pond have occupied the place in succession. On the retirement of the last-named astronomer in 1835, Professor Airy was removed thither from the Cambridge Observatory. In every state, and in almost every principality in Europe, observatories have been established. But these have often fallen speedily into inaction, or have contributed little to the progress of astronomy, because their observations have not been published. From the same causes, the numerous private observatories which exist throughout Europe have added little to our knowledge, except where the attention of the astronomer has been directed to some definite points. As, for instance, the magnificent labors of the Herschels, or the skillful observations made by Mr. Pond with the Westbury Circle, which first pointed out the error of graduation of the Greenwich quadrants. The observations, now regularly published, are those of Greenwich, begun by Maskelyne and continued quarterly by Mr. Pond; those of Königsberg, published by Bessel since 1814; of Vienna by Littrow since 1820; of Speyer by Schwerd since 1826; those of Cambridge, commenced by Airy in 1828; of Armagh by Robinson in 1829. Besides these, a number of useful observations have been published in journals and occasional forms, as, for instance, those of Zach, made by Seeberg near Gotha, since 1788, and others have been employed in forming catalogues, of which we shall speak shortly. I have left the statement of published observations in the text as it stood originally. I believe that at present, 1847, the 12 places contained in the following list publish their observations quite regularly, or nearly so: Greenwich, Oxford, Cambridge, Vienna, 478, Berlin, Dorpat, Munich, Geneva, Paris, Königsberg, Madras, the Cape of Good Hope. Littrow, in his translation, adds to the publications noticed in the text as containing astronomical observations: Zach's Monatlich Correspondence, Lindenau and Bonenberger's Zeitschrift für Astronomie, Bode's Astronomisches Jahrbuch, Schumacher's Astronomische Nachrichten. Nor has the establishment of observatories been confined to Europe. In 1786, M. de Beauchamp, at the expense of Louis XVI, erected an observatory at Baghdad, built to restore the Chaldean and Arabian observations, as the inscription stated. But probably, the restoration once effected, the main intention had been fulfilled, and little perseverance in observing was thought necessary. In 1828, the British government completed the building of an observatory at the Cape of Good Hope, which Lacaille had already made an astronomical station by his observations there at an earlier period, 1750, and an observatory formed in New South Wales by Sir T.M. Brisbane in 1822, and presented by him to the government, is also in activity. The East India Company has founded observatories at Madras, Bombay, and St. Helena, and observations made at the former of these places and at St. Helena have been published. The bearing of the work done at such observatories upon the past progress of astronomy has already been seen in the preceding narrative. Their bearing upon the present condition of the science will be the subject of a few remarks hereafter. Sect 3. Scientific societies. The influence of scientific societies, or academical bodies, has also been very powerful in the subject before us. In all branches of knowledge, the use of such associations of studious and inquiring men is great. The clearness and coherence of a speculator's ideas and their agreement with facts, the two main conditions of scientific truth, are severally but beneficially tested by collision with other minds. In astronomy, moreover, the vast extent of the subject makes requisite the division of labor and the support of sympathy. The Royal Societies of London and of Paris were founded nearly at the same time as the metropolitan observatories of the two countries. We have seen what constellations of philosophers and what activity of research existed at those periods. These philosophers appear in the lists, their discoveries, 479 in the publications, of the above-mentioned eminent societies. As the progress of physical science, and principally of astronomy, attracted more and more admiration, academies were created in other countries. That of Berlin was founded by Leibniz in 1710, that of St. Petersburg was established by Peter the Great in 1725, and both these have produced highly valuable memoirs. In more modern times, these associations have multiplied almost beyond the power of estimation. They have been formed according to divisions, both of locality and of subject, conformable to the present extent of science and the vast population of its cultivators. It would be useless to attempt to give a view either of their number or of the enormous mass of scientific literature which their transactions present. But we may notice, as especially connected with our present subject, the Astronomical Society of London, founded in 1820, which gave a strong impulse to the pursuit of the science in England. Sect 4. Patrons of astronomy. The advantages which letters and philosophy derive from the patronage of the great have sometimes been questioned. That love of knowledge, it has been thought, cannot be genuine which requires such stimulation, nor those speculations free and true which are thus forced into being. In the sciences of observation and calculation, however, in which disputed questions can be experimentally decided, and in which opinions are not disturbed by men's practical principles and interests, there is nothing necessarily operating to poison or neutralize the resources which wealth and power supply to the investigation of truth. Astronomy has, in all ages, flourished under the favor of the rich and powerful. In the period of which we speak, this was eminently the case. Louis XIV gave to the astronomy of France a distinction which, without him, it could not have attained. No step perhaps tended more to this than his bringing the celebrated Dominic Cassini to Paris. This Italian astronomer, for he was born at Permaldo in the county of Nice and was professor at Bologna, was already in possession of a brilliant reputation when the French ambassador, in the name of his sovereign, applied to Pope Clement IX and to the Senate of Bologna that he should be allowed to remove to Paris. The request was granted only so far as an absence of 6 years, but at the end of that time, the benefits and honors which 480 the king had conferred upon him fixed him in France. The impulse which his arrival, in 1669, and his residence gave to astronomy showed the wisdom of the measure. In the same spirit, the French government drew to Paris Romer from Denmark, Huygens from Holland, and gave a pension to Hevelius, and a large sum when his observatory at Danzig had been destroyed by fire in 1679. When the sovereigns of Prussia and Russia were exerting themselves to encourage the sciences in their countries, they followed the same course which had been so successful in France. Thus, as we have said, the Tsar Peter took Delisle to Petersburg in 1725. The celebrated Frederick the Great drew to Berlin, Voltaire and Maupertuis, Euler and Lagrange, and the Empress Catharine obtained in the same way Euler 2 of the Bernoullis and other mathematicians. In none of these instances, however, did it happen that the generous plant did still its stock renew, as we have seen was the case at Paris, with the Cassinis and their kinsmen the Maraldis. I may notice among instances of the patronage of astronomy the reward at present offered by the King of Denmark for the discovery of a comet. It is not necessary to mention here the more recent cases in which sovereigns or statesmen have attempted to patronize individual astronomers. Sect 5 Astronomical expeditions. Besides the pensions thus bestowed upon resident mathematicians and astronomers, the governments of Europe have wisely and usefully employed considerable sums upon expeditions and travels undertaken by men of science for some appropriate object. Thus Picard, in 1671, was sent to Uraniborg, the scene of Tycho's observations, to determine its latitude and its longitude. He found that the city of the skies had utterly disappeared from the earth, and even its foundations were retraced with difficulty. With the same object, that of accurately connecting the labors of the places which had been at different periods the metropolis of astronomy, Chazelles was sent, in 1693, to Alexandria. We have already mentioned Richer's astronomical expedition to Cayenne in 1672. Varin and Deshays were sent a few years later into the same regions for similar purposes. Halley's expedition to St. 481 Helena in 1677, with the view of observing the southern stars, was at his own expense. But at a later period, in 1698, he was appointed to the command of a small vessel by King William III, in order that he might make his magnetical observations in all parts of the world. Lacaille was maintained by the French government 4 years at the Cape of Good Hope, 1754, for the purpose of observing the stars of the southern hemisphere. The 2 transits of Venus in 1761 and 1769 occasioned expeditions to be sent to Kamchatka and Tobolsk by the Russians, to the Isle of France, and to Coromandel by the French, to the Isles of St. Helena and Otaheite by the English, to Lapland and to Drontheim by the Swedes and Danes. I shall not here refer to the measures of degrees executed by various nations, still less the innumerable surveys by land and sea, but I may just notice the successive English expeditions of Captains Basil Hall, Sabine, and Foster, for the purpose of determining the length of the second's pendulum in different latitudes, and the voyages of M. Biot and others, sent by the French government for the same purpose. Much has been done in this way, but not more than the progress of astronomy absolutely required, and only a small portion of that which the completion of the subject calls for. Sect 6 Present State of Astronomy. Astronomy, in its present condition, is not only much the most advanced of the sciences, but is also in far more favorable circumstances than any other science for making any future advance, as soon as this is possible. The general methods and conditions by which such an advantage is to be obtained for the various sciences, we shall endeavor hereafter to throw some light upon. But in the meantime, we may notice here some of the circumstances in which this peculiar felicity of the present state of astronomy may be traced. The science is cultivated by a number of votaries, with an assiduity and labor, and with an expenditure of private and public resources to which no other subject approaches. And the mode of its cultivation in all public and most private observatories has this character that it forms, at the same time, a constant process of verification of existing discoveries and a strict search for any new discoverable laws. The observations made are immediately referred to the best tables, and 482 corrected by the best formulae which are known. And if the result of such a reduction leaves anything unaccounted for, the astronomer is forthwith curious and anxious to trace this deviation from the expected numbers to its rule and its origin. Until the first, at least, of these things is performed, he is dissatisfied and unquiet. The reference of observations to the state of the heavens as known by previous researches implies a great amount of calculation. The exact places of the stars at some standard period are recorded in catalogues. Their movements, according to the laws hitherto detected, are arranged in tables. And if these tables are applied to predict the numbers which observation on each day ought to give, they form ephemerides. Thus the catalogues of fixed stars of Flamsteed, of Piazzi, of Maskelyne of the Astronomical Society, are the basis of all observation. To these are applied the corrections for refraction of Bradley or Bessel, and those for aberration, for nutation, for precession of the best modern astronomers. The observations so corrected enable the observer to satisfy himself of the delicacy and fidelity of his measures of time and space, his clocks and his arcs. But this being done, different stars so observed can be compared with each other, and the astronomer can then endeavor further to correct his fundamental elements, his catalogue, or his tables of corrections. In these tables, though previous discovery has ascertained the law. Yet the exact quantity, the constant or coefficient of the formula, can be exactly fixed only by numerous observations and comparisons. This is a labor which is still going on, and in which there are differences of opinion on almost every point. But the amount of these differences is the strongest evidence of the certainty and exactness of those doctrines in which all agree. Thus Lindenau makes the coefficient of nutation rather less than 9 seconds, which other astronomers give as about 9 seconds and 3/10. The tables of refraction are still the subject of much discussion and of many attempts at improvement. And after or amid these discussions, arise questions whether there be not other corrections of which the law has not yet been assigned. The most remarkable example of such questions is the controversy concerning the existence of an annual parallax of the fixed stars, which Brinkley asserted, and which Pond denied. Such a dispute between two of the best modern observers only proves that the quantity in question, if it really exist, is of the same order as the hitherto unsurmounted errors of instruments and corrections. The belief in an appreciable parallax of some of the fixed 483 stars appears to gain ground among astronomers. The parallax of 61 Cygni, as determined by Bessel, is 0.34, about 1/3 of a second or 1/10,000 of a degree. That of Alpha Centauri, as determined by Maclear, is 0.9 or 1/4000 of a degree. But besides the fixed stars and their corrections, the astronomer has the motions of the planets for his field of action. The established theories have given us tables of these, from which their daily places are calculated and given in our ephemerides, as the Berliner Jahrbuch of Encke or the Nautical Almanac, published by the government of this country, the Connaissance des Temps which appears at Paris, or the Ephemeridi di Milano. The comparison of the observed with the tabular place gives us the means of correcting the coefficients of the tables, and thus of obtaining greater exactness in the constants of the solar system. But these constants depend upon the mass and form of the bodies of which the system is composed. And in this province, as well as in sidereal astronomy, different determinations, obtained by different paths, may be compared, and doubts may be raised and may be solved. In this way, the perturbations produced by Jupiter on different planets gave rise to a doubt whether his attraction be really proportional to his mass, as the law of universal gravitation asserts. The doubt has been solved by Nicolai and Encke in Germany and by Airy in England. The mass of Jupiter, as shown by the perturbations of Juno, of Vesta, and of Encke's comet, and by the motion of his outermost satellite, is found to agree, though different from the mass previously received on the authority of Laplace. Thus also Burckhardt, Littrow, and Airy have corrected the elements of the solar tables. In other cases, the astronomer finds that no change of the coefficients will bring the tables and the observations to a coincidence, that a new term in the formula is wanting. He obtains, as far as he can, the law of this unknown term. If possible, he traces it to some known or probable cause. Thus Mr. Airy, in his examination of the solar tables, not only found that a diminution of the received mass of Mars was necessary, but perceived discordances which led him to suspect the existence of a new inequality. Such an inequality was at length found to result theoretically from the attraction of Venus. Encke, in his examination of his comet, found a diminution of the periodic time in the successive revolutions, from which he inferred the existence of a resisting medium. Uranus still deviates from his tabular place, and the cause remains yet to be discovered. But see the additions to this volume. 484. Thus it is impossible that an assertion, false to any amount which the existing state of observation can easily detect, should have any abiding prevalence in astronomy. Such errors may long keep their ground in any science which is contained mainly in didactic works, and studied in the closet, but not acted upon elsewhere, which is reasoned upon much, but brought to the test of experiment rarely or never. Here, on the contrary, an error, if it arise, makes its way into the tables, into the ephemeris, into the observer's nightly list, or his sheet of reductions. The evidence of sense flies in its face in 1,000 observatories. The discrepancy is traced to its source, and soon disappears forever. In this favored branch of knowledge, the most recondite and delicate discoveries can no more suffer doubt or contradiction than the most palpable facts of sense which the face of nature offers to our notice. The last great discovery in astronomy, the motion of the stars arising from aberration, is as obvious to the vast population of astronomical observers in all parts of the world as the motion of the stars about the pole is to the casual night wanderer. And this immunity from the danger of any large error in the received doctrines is a firm platform on which the astronomer can stand and exert himself to reach perpetually further and further into the region of the unknown. The same scrupulous care and diligence in recording all that has hitherto been ascertained has been extended to those departments of astronomy in which we have as yet no general principles which serve to bind together our acquired treasures. These records may be considered as constituting a descriptive astronomy. Such are, for instance, catalogues of stars and maps of the heavens, maps of the moon, representations of the appearance of the sun and planets as seen through powerful telescopes, pictures of nebulae, of comets, and the like. Thus, besides the catalogue of fundamental stars, which may be considered as standard points of reference for all observations of the sun, moon, and planets, there exist many large catalogues of smaller stars. Flamsteed's Historia Celestis, which much surpassed any previous catalogue, contained above 3,000 stars. But in 1801, the French Histoire Céleste appeared, comprising observations of 50,000 stars. Catalogues or charts of other special portions of the sky have been published more recently. And in 1825, the Berlin Academy proposed to the astronomers of Europe to carry on this work by portioning out the heavens among them. Before Flamsteed, the best catalogue of the stars was 485 Tycho Brahe, containing the places of about 1,000 stars determined very roughly with the naked eye. On the occasion of a project of finding the longitude, which was offered to Charles Roman II. In 1674, Flamsteed represented that the method was quite useless, in consequence, among other things, of the inaccuracy of Tycho's places of the stars. Flamsteed's letters being shown King Charles, he was startled at the assertion of the fixed stars' places being false in the catalogue, and said, with some vehemence, he must have them anew observed, examined, and corrected for the use of his seamen. This was the immediate occasion of building Greenwich Observatory and placing Flamsteed there as an observer. Flamsteed's Historia Celestis contained above 3,000 stars, observed with telescopic sights. It has recently been republished with important improvements by Mr. Bailey. See Bailey's Flamsteed, p. 38. The French Histoire Céleste was published in 1801 by Lalande, containing 50,000 stars, simply as observed by himself and other French astronomers. The reduction of the observations contained in this catalogue to the mean places at the beginning of the year 1800 may be effected by means of tables published by Schumacher for that purpose in 1825. In 1807, Piazzi's catalogue of 6748 stars, founded on Maskelyne's catalogue of 1700, was published, afterwards extended to 7646 stars in 1814. This is considered as the greatest work undertaken by any modern astronomer, the observations being well made, reduced, and compared with those of former astronomers. Piazzi's catalogue is the standard and accurate catalogue, as the Histoire Céleste is the standard approximate catalogue for small stars. But the new planets were discovered mostly by a comparison of the heavens with Bode's Berlin catalogue. I may mention other catalogues of stars which have recently been published. Pond's catalogue contains 1112 northern stars, Johnson's 606, Wriothesley's 1318 in right ascension only, Airy's first Cambridge catalogue 726, his Greenwich catalogue 1439. Pearson's has 520 zodiacal stars, Groombridge's 4243 circumpolar stars as far as 50 degrees of north polar distance. Santini's a zone 18 degrees north of the equator. Besides these, Mr. Taylor has published, by order of the Madras government, a catalogue of 11,000 stars observed by him at Madras. And Rumker, who observed in the observatory established by Sir Thomas Brisbane at Parramatta, in Australia, has commenced a catalogue which is to contain 12,000. Mr. Bailey, 486, published two standard catalogues, that of the Royal Astronomical Society, containing 2881 stars, and that of the British Association, containing 8377 stars. I omit other catalogs, as those of Argelander and C, and catalogs of southern stars. Of the Berlin maps, 14 hours in right ascension have been published, and their value may be judged of by this circumstance, that it was in a great measure by comparing the heavens with these maps that the new planet Astrea was discovered. The zone observations made at Königsberg by the late illustrious astronomer Bessel deserve to be mentioned as embracing a vast number of stars. The common mode of designating the stars is founded upon the ancient constellations as given by Ptolemy, to which Bayer of Augsburg in his Uranometria added the artifice of designating the brightest stars in each constellation by the Greek letters alpha, beta, gamma, and C, applied in order of brightness, and when these were exhausted, the Latin letters. Flamsteed used numbers. As the number of observed stars increased, various methods were employed for designating them, and the confusion which has been thus introduced, both with regard to the boundaries of the constellations and the nomenclature of the stars in each, has been much complained of lately. Some attempts have been made to remedy this variety and disorder. Mr. Argelander has recently recorded stars, according to their magnitudes as seen by the naked eye, in a new uranometry. Among representations of the moon, I may mention Hevelius's Selenographia, a work of former times, and Beer and Madler's Map of the Moon, recently published. I have already said something of the observations of the two Herschels on double stars, which have led to a knowledge of the law of the revolution of such systems. But besides these, the same illustrious astronomers have accumulated enormous treasures of observations of nebulae, the materials, it may be, hereafter, of some vast new generalization with respect to the history of the system of the universe. A few measures of double stars are to be found in previous astronomical records, but the epoch of the creation of this part of the science of astronomy must be placed at the beginning of the present century, when Sir William Herschel, in 1802, published in the Phil. Trans. A catalogue of 500 new nebulae of various classes, and in the Phil. Trans 1803, a paper on the changes in the relative situation of the double stars in 25 years. In succeeding papers, he pursued the subject. In one in 1814, he noticed the breaking up of the 487 Milky Way in different places, apparently from some principle of attraction. And in this, and in one in 1817, he published those remarkable views on the distribution of the stars in our own cluster as forming a large stratum, and on the connection of stars and nebulae, the stars appearing sometimes to be accompanied by nebulae, sometimes to have absorbed a part of the nebula, and sometimes to have been formed from nebulae, which have been accepted and propounded by others as the nebular theory. Sir William Herschel's last paper was a catalogue of 145 new double stars communicated to the Astronomical Society in 1822. In 1827, M. Struve, of Dorpat, in Russia, published his Catalogus Novus, containing the places of 3112 double stars. While this was going on, Sir John Herschel and Sir James South published, in the Phil. Trans. 1824 accurate measures of 380 double and triple stars, to which Sir J. South afterwards added 458. Mr. Dunlop published measures of 253 southern double stars. Other observations have been published by Capt. Smythe, Mr. Dawes, and C. The great work of Struve, Mensury Micrometricae, and C. contains 3134 such objects, including most of Sir W. Herschel's double stars. Sir J. Herschel in 1826, 7, and 8 presented to the Astronomical Society about 1,000 measures of double stars, and in 1830, good measures of 1236 made with his 20-feet reflector. His paper in Volume V of the Ast. Soc. Mem. Besides measures of 364 such stars, exhibits all the most striking results as to the motion of double stars which have yet been obtained. In 1835, he carried his 20-feet reflector to the Cape of Good Hope for the purpose of completing the survey of double stars and nebulae in the southern hemisphere with the same instruments which had explored the northern skies. He returned from the Cape in 1838 and is now, 1846, about to give the world the results of his labors. Besides the stars just mentioned, his work will contain from 1,500 to 2,000 additional double stars, making a gross number of above 8,000. in which, of course, are included a number of objects of no great scientific interest, but in which also are contained the materials of the most important discoveries which remain to be made by astronomers. The publication of Sir John Herschel's great work upon double stars and nebulae is looked for with eager interest by astronomers. Of the observations of nebulae, we may say what has just been said of the observations of double stars, that they probably contain the materials of important future discoveries. It is impossible not to regard these phenomena with reference to the nebular hypothesis, which has been propounded by Laplace, and much more strongly, 488, insisted upon by other persons, namely, the hypothesis that systems of revolving planets, of which the solar system is an example, arise from the gradual contraction and separation of vast masses of nebulous matter. Yet it does not appear that any changes have been observed in nebulae which tend to confirm this hypothesis. And the most powerful telescope in the world, recently erected by the Earl of Rosse, has given results which militate against the hypothesis, inasmuch as it has shown that what appeared a diffused nebulous mass is, by a greater power of vision, resolved, in all cases yet examined, into separate stars. When astronomical phenomena are viewed with reference to the nebular hypothesis, they do not belong so properly to astronomy, in the view here taken of it, as to cosmogony. If such speculations should acquire any scientific value, we shall have to arrange them among those which I have called paleontological sciences, namely, those sciences which contemplate the universe, the earth, and its inhabitants, with reference to their historical changes and the causes of those changes. 489. Additions to the third edition. Introduction. There is a difficulty in writing for popular readers a history of the inductive sciences, arising from this, that the sympathy of such readers goes most readily and naturally along the course which leads to false science and to failure. Men, in the outset of their attempts at knowledge, are prone to rush from a few hasty observations of facts to some wide and comprehensive principles, and then to frame a system on these principles. This is the opposite of the method by which the sciences have really and historically been conducted, namely, the method of a gradual and cautious ascent from observation to principles of limited generality, and from them to others more general. This latter, the true scientific method, is induction, and has led to the inductive sciences. The other, the spontaneous and delusive course, has been termed by Francis Bacon, who first clearly pointed out the distinction and warned men of the error anticipation. The hopelessness of this course is the great lesson of his philosophy. But by this course proceeded all the earlier attempts of the Greek philosophers to obtain a knowledge of the universe. Laborious observation, narrow and modest inference, caution, slow and gradual advance, limited knowledge, are all unwelcome efforts and restraints to the mind of man, when his speculative spirit is once roused. Yet these are the necessary conditions of all advance in the inductive sciences. Hence, as I have said, it is difficult to win the sympathy of popular readers to the true history of these sciences. The career of bold systems and fanciful pretenses of knowledge is more entertaining and striking. Not only so, but the bold guesses and fanciful reasonings of men unchecked by doubt or fear of failure are often presented as the dictates of common sense, as the plain, unsophisticated, unforced reason of man, acting according to no artificial rules, but following its own natural course. Such common sense, while it, 490, complacently plumes itself on its clear-sightedness in rejecting arbitrary systems of others, is no less arbitrary in its own arguments, and often no less fanciful in its inventions, than those whom it condemns. We cannot take a better representative of the common sense of the ancient Greeks than Socrates, and we find that his common sense, judging with such admirable sagacity and acuteness respecting moral and practical matters, offered, when he applied it to physical questions, examples of the unconscious assumptions and fanciful reasonings which, as we have said, common sense on such subjects commonly involves. Socrates, Xenophon tells us, Memorabilia, Roman 4:7, recommended his friends not to study astronomy so as to pursue it into scientific details. This was practical advice, but he proceeded further to speak of the palpable mistakes made by those who had carried such studies farthest. Anaxagoras, for instance, he said, held that the sun was a fire. He did not consider that men can look at a fire, but they cannot look at the sun. They become dark by the sun shining upon them, but not so by the fire. He did not consider that no plants can grow well except they have sunshine, but if they are exposed to the fire, they are spoiled. Again, when he said that the sun was a stone red hot, he did not consider that a stone heated by the fire is not luminous, and soon cools, but the sun is always luminous and always hot. We may easily conceive how a disciple of Anaxagoras would reply to these arguments. He would say, for example, as we should probably say at present, that if there were a mass of matter so large and so hot as Anaxagoras supposed the sun to be, its light might be as great and its heat as permanent as the heat and light of the sun are, as yet, known to be. In this case, the arguments of Socrates are at any rate no better than the doctrine of Anaxagoras. 491, Book 1. The Greek School Philosophy. Chapter 2. The Greek Schools. The Platonic Doctrine of Ideas. In speaking of the foundation of the Greek school philosophy, I have referred to the dialogue entitled Parmenides, commonly ascribed to Plato. And the doctrines ascribed to Parmenides, in that and in other works of ancient authors, are certainly remarkable examples of the tendency which prevailed among the Greeks to rush at once to the highest generalizations of which the human mind is capable. The distinctive dogma of the Eleatic school, of which Parmenides was one of the most illustrious teachers, was that all things are one. This indeed was rather a doctrine of metaphysical theology than of physical science. It tended to, or agreed with, the doctrine that all things are God, the doctrine commonly called pantheism. But the tenet of the Platonists, which was commonly put in opposition to this, that we must seek the one in the many, had a bearing upon physical science. At least, if we interpret it, as it is generally interpreted, that we must seek the one law which pervades a multiplicity of phenomena. We may, however, take the liberty of remarking that to speak of a rule which is exemplified in many cases, as being the one in the many, a way of speaking by which we put out of sight the consideration what very different kinds of things the one and the many are, is a mode of expression which makes a very simple matter look very mysterious, and is another example of the tendency which urges speculative men to aim at metaphysical generality rather than scientific truth. The dialogue Parmenides is, as I have said, commonly referred to Plato. Yet it is entirely different in substance, manner, and tendency, 492, from the most characteristic of the Platonic dialogues. In these, Socrates is represented as finally successful in refuting or routing his adversaries, however confident their tone and however popular their assertions. They are angered or humbled. He retains his good temper and his air of superiority, and when they are exhausted, he sums up in his own way. In the Parmenides, on the contrary, everything is the reverse of this. Parmenides and Zeno exchange good-humored smiles at Socrates' criticism when the bystanders expect them to grow angry. They listen to Socrates while he propounds Plato's doctrine of ideas, and reply to him with solid arguments which he does not answer, and which have never yet been answered. Parmenides, in a patronizing way, lets him off, and having done this, being much entreated, he pronounces a discourse concerning the one and the many, which, obscure as it may seem to us, was obviously intended to be irrefutable, and during the whole of this part of the dialogue, the friend of Socrates appears only as a passive respondent, saying yes or no as the assertions of Parmenides require him to do. Just in the same way in which the opponents of Socrates are represented in other dialogues. These circumstances, to which other historical difficulties might be added, seem to show plainly that the Parmenides must be regarded as an Eleatic, not as a Platonic dialogue, as composed to confute, not to assert, the Platonic doctrine of ideas. The Platonic doctrine of ideas has an important bearing upon the philosophy of science, and was suggested in a great measure by the progress which the Greeks had really made in geometry, astronomy, and other sciences, as I shall elsewhere endeavor to show. This doctrine has been recommended in our own time as containing a mighty substance of imperishable truth. It cannot fail to be interesting to see in what manner the doctrine is presented by those who thus judge of it. The following is the statement of its leading features, which they give us. Man's soul is made to contain not merely a consistent scheme of its own notions, but a direct apprehension of real and eternal laws beyond it. These real and eternal laws are things intelligible, and not things sensible. The laws, impressed upon creation by its creator and apprehended by man, are something equally distinct from the creator, 493, and from man, and the whole mass of them may be termed the world of things purely intelligible. Further, there are qualities in the supreme and ultimate cause of all, which are manifested in his creation. And not merely manifested, but in a manner after being brought out of his superessential nature into the stage of being which is below him. But next to him are then, by the causative act of creation, deposited in things, differencing them one from the other, so that the things participate of them, mu epsilon tau epsilon chi omicron epsilon sigma iota, communicate with them, kappa omicron iota nu omicron letter 1 fe6 sigma iota. The intelligence of man, excited to reflection by the impressions of these objects, thus, though themselves transitory, participant of a divine quality, may rise to higher conceptions of the perfections thus faintly exhibited. And inasmuch as the perfections are unquestionably real existences, and known to be such in the very act of contemplation, this may be regarded as a distinct intellectual apprehension of them, a union of the reason with the ideas in that sphere of being which is common to both. Finally, the reason, in proportion as it learns to contemplate the perfect and eternal, desires the enjoyment of such contemplations in a more consummate degree, and cannot be fully satisfied except in the actual fruition of the perfect itself. These propositions taken together constitute the theory of ideas. When we have to treat of the philosophy of science, it may be worth our while to resume the consideration of this subject. In this part of the history, the Timaeus of Plato is referred to as an example of the loose notions of the Greek philosophers in their physical reasonings. And undoubtedly, this dialogue does remarkably exemplify the boldness of the early Greek attempts at generalization on such subjects. Yet in this and in other parts, the writings of Plato contain speculations which may be regarded as containing germs of true physical science, inasmuch as they assume that the phenomena of the world are governed by mathematical laws, by relations of space and number, and endeavor, too boldly, no doubt, but not vaguely or loosely, to assign those laws. The Platonic writings offer, in this way, so much that forms a prelude to the astronomy and other physical sciences of the Greeks, that they will deserve our notice, as supplying materials for the next 2 books of the history in which these subjects are treated of. 494. Chapter 3. Failure of the Greek Physical Philosophy. Francis Bacon's remarks. Though we do not accept as authority even the judgments of Francis Bacon, and shall have to estimate the strong and the weak parts of his, no less than of other philosophies, we shall find his remarks on the Greek philosophers very instructive. Thus he says of Aristotle, Nov. Org. 1. APH. LZI. He is an example of the kind of philosophy in which much is made out of little, so that the basis of experience is too narrow. He corrupted natural philosophy by his logic and made the world out of his categories. He disposed of the distinction of dense and rare, by which bodies occupy more or less dimensions or space, by the frigid distinction of act and power. He assigned to each kind of body a single proper motion, so that if they have any other motion they must receive it from some extraneous source, and imposed many other arbitrary rules upon nature, being everywhere more careful how one may give a ready answer and make a positive assertion than how he may apprehend the variety of nature. And this appears most evidently by the comparison of his philosophy with the other philosophies which had any vogue in Greece. For the homoeomeria of Anaxagoras, the atoms of Leucippus and Democritus, the heaven and earth of Parmenides, the love and hate of Empedocles, the fire of Heraclitus, had some trace of the thoughts of a natural philosopher, some savor of experience and nature and bodily things, while the physics of Aristotle, in general, sound only of logical terms. Note 2:A, for these technical forms of the Greeks, see Sec 3 of this chapter. Nor let anyone be moved by this that in his books of animals, and in his problems, and in others of his tracts, there is often a quoting of experiments. For he had made up his mind beforehand, and did not consult experience in order to make right propositions and axioms, but when he had settled his system to his will, he twisted experience 495 round and made her bend to his system. so that in this way he is even more wrong than his modern followers, the schoolmen, who have deserted experience altogether. We may note also what Bacon says of the term sophist. Aph. LXXI. The wisdom of the Greeks was professorial and prone to run into disputations, which kind is very adverse to the discovery of truth. And the name of sophists, which was cast in the way of contempt, by those who wished to be reckoned philosophers, upon the old professors of rhetoric, Gorgias, Protagoras, Hippias, Polus, does, in fact, fit the whole race of them, Plato, Aristotle, Zeno, Epicurus, Theophrastus, and their successors, Chrysippus, Carneades, and the rest. Note 3:A. It is curious that the attempt to show that Plato's opponents were not commonly elusive and immoral reasoners has been represented as an attempt to obliterate the distinction of sophist and philosopher. See A. Butler's Lectures, I. 357. Note that these two classes of teachers, as moralists, were not different in their kind, has been urged by Mr. Grote in a very striking and amusing manner. But Bacon speaks of them here as physical philosophers, in which character he holds that all of them were sophists, that is, illusory reasoners. Aristotle's account of the rainbow. To exemplify the state of physical knowledge among the Greeks, we may notice briefly Aristotle's account of the rainbow, a phenomenon so striking and definite and so completely explained by the optical science of later times. We shall see that not only the explanations there offered were of no value, but that even the observation of facts, so common and so palpable, was inexact. In his Meteorologica, lib. Roman 3. C2, he says, the rainbow is never more than a semicircle. And at sunset and sunrise, the circle is least, but the arch is greatest. When the sun is high, the circle is larger, but the arch is less. This is erroneous, for the diameter of the circle of which the arch of the rainbow forms a part is always the same, namely 82 degrees. After the autumnal equinox, he adds, it appears at every hour of the day, but in the summer season it does not appear about noon. It is curious that he did not see the reason of this. The center of the circle of which the rainbow is part is always opposite to the sun. And therefore, if the sun be more than 41 degrees above the horizon, the center of the rainbow will be so much below the horizon that the place of the rainbow will, 496, be entirely below the horizon. In the latitude of Athens, which is 38 degrees, the equator is 52 degrees above the horizon, and the rainbow can be visible only when the sun is 11 degrees lower than it is at the equinoctial noon. These remarks, however, show a certain amount of careful observation, and so do those which Aristotle makes respecting the colors. 2 rainbows at most appear, and of these, each has 3 colors, but those in the outer bow are duller, and their order opposite to those in the inner. For in the inner bow the first and largest arch is red, but in the outer bow the smallest arch is red, the nearest to the inner, and the others in order. The colors are red, green, and purple, such as painters cannot imitate. It is curious to observe how often modern painters disregard even the order of the colors, which they could imitate if they attended to it. It may serve to show the loose speculation which we oppose to science if we give Aristotle's attempt to explain the phenomenon of the rainbow. It is produced, he says, see Roman 4. By reflexion, letter 1F00 nu alpha kappa lambda alpha sigma iota sigma, from a cloud opposite to the sun, when the cloud forms into drops. And as a reason for the red color, he says that a bright object seen through darkness appears red, as the flame through the smoke of a fire of green wood. This notion hardly deserves notice, and yet it was taken up again by Goethe in our own time, in his speculations concerning colors. 497, Book 2,